Tonight is not about doomsday. It's about bookkeeping. Imagine the universe as a very large account, the kind maintained by a patient, methodical clerk who never takes a day off. Every process that occurs, every star that ignites, every ice cube that melts, every breath you take, adds a small, irreversible line to this ledger. The entries accumulate slowly, filling page after page, and they all point in the same direction. This direction is what we call entropy, and it tracks something simple: how spread out and unavailable energy becomes over time. Entropy is not a villain. It carries no moral weight, no emotional charge. It's just a number, a measure that tends to go up in isolated systems. Think of it as cosmic bookkeeping, a way of recording the universe's transactions. Each time energy moves from a concentrated form to a more dispersed one, the ledger records a small increase. The ice melts into water. The hot coffee cools to room temperature. The drop of dye spreads through the glass until the water is uniformly tinted. These are not dramatic events, but each one leaves a permanent mark in the account books. To understand what entropy actually measures, we need to think about the difference between what we see and what's really happening at the smallest scales. Consider a cup of coffee sitting on your desk. You observe a single thing. A cup of liquid at a certain temperature, maybe 70 degrees Celsius. That's the macrostate, the big picture description. But at the molecular level, there are countless ways to arrange the water molecules, caffeine molecules, and heat energy to produce that same observable cup of coffee. Each specific arrangement is a microstate. There might be trillions upon trillions of different microstates that all correspond to the same macrostate you're looking at. Now here's the key insight. There are usually many, many more microstates that look mixed up or spread out than ones that look organized or concentrated. If you have a container with hot water on one side and cold water on the other, there are relatively few microstates that maintain that sharp temperature difference. But there are vastly more microstates where the energy is evenly distributed and the temperature is uniform throughout. Over time, as molecules collide and exchange energy randomly, the system naturally drifts toward the macrostates that correspond to the most microstates, simply because those are the most probable destinations. The ledger entry, entropy increased, is just a shorthand way of saying the system moved into a state that could be realized in more ways. This is not a law that prevents any particular molecular motion. Water molecules don't know about entropy. They just bounce around according to the basic rules of physics. But when you have enormous numbers of them, say 10 to the power of 23 molecules in a glass of water, the statistics become overwhelming. It's not impossible for all the fast-moving molecules to spontaneously gather on one side of the glass and all the slow ones on the other, recreating a hot-cold divide. It's just so stupendously unlikely that you could wait longer than the age of the universe and never see it happen. The probabilities are so lopsided that the direction of change becomes, for all practical purposes, one way. Let's walk through some everyday examples to make this concrete. Take an ice cube from the freezer and drop it into a glass of warm water. The ice is a low-entropy configuration in a certain sense. The water molecules are locked into a rigid crystal structure, and the thermal energy is concentrated in the liquid surrounding it. Over the next few minutes, heat flows from the warm water into the ice. The crystal structure breaks down, the water molecules in the ice gain kinetic energy and start moving freely, and eventually the entire system reaches a uniform temperature somewhere between the original temperature of the ice and the original temperature of the water. The energy that was localized in the warm water has spread out. The entropy of the combined system has increased. The ledger records this transaction. Energy dispersed, gradient flattened, entropy up. Or consider a hot cup of coffee left on the counter. The coffee starts out much warmer than the surrounding air. Heat flows from the cup into the room, carried away by air currents and infrared radiation. After an hour, the coffee has cooled to room temperature. The energy that was concentrated in the hot liquid is now distributed throughout a larger volume of air and has been radiated away as low-energy photons into the walls, the floor, the ceiling. The total energy is conserved. None of it vanished, but it's now spread out in a way that makes it much less useful for doing organized work. The coffee's high temperature was a gradient you could have harnessed in principle to run a tiny heat engine. Once the coffee and the room are at the same temperature, that opportunity is gone. The entropy of the room plus coffee system has increased. Another line in the ledger. One more, drop a single droplet of food colouring into a glass of still water. At first, you can see exactly where the dye is, a concentrated blob of colour. But even without stirring, the dye molecules begin to diffuse. They spread out, driven by random thermal motion. After a while, the entire glass is uniformly tinted. The dye molecules are now distributed evenly throughout the water. The macrostate, all the dye in one small region, corresponded to relatively few microstates. The macrostate dye evenly distributed corresponds to an astronomically larger number of microstates. The system moved from the less probable configuration to the more probable one. Entropy increased. The ledger notes it. These everyday processes all illustrate the second law of thermodynamics, which says that in an isolated system, entropy never decreases over time. It either stays the same if the system is already in equilibrium, or it increases. The law doesn't forbid energy from moving around, it just says that, on average, energy will spread out and gradients will flatten. The second law is statistical. It's not that every individual microstate has an arrow painted on it pointing forward in time. It's that the sheer number of high-entropy microstates is so much larger than the number of low-entropy ones that the direction of change becomes effectively irreversible. Now, why does this matter for doing useful work? Machines, engines, and even living organisms all rely on differences: temperature differences, pressure differences, chemical concentration differences, to drive organised processes. A car engine works because there's a difference between the hot, high-pressure gases produced by burning fuel and the cooler, lower-pressure environment of the exhaust. A hydroelectric dam works because there's a difference in height, and thus gravitational potential, between the water in the reservoir and the water downstream. Your body works because there's a chemical difference between the energy-rich molecules in food and the lower-energy waste products you excrete and exhale. In every case, when work is done, some of the input energy is inevitably converted into a lower-quality, more spread-out form, typically waste heat. No engine can be perfectly efficient. No process can convert all of the energy from a high-grade source into useful output without some loss. This is another way of stating the second law. You can't build a machine that continuously converts heat from a single reservoir into work without any other effect. Some energy always ends up increasing the entropy of the surroundings. In accounting terms, entropy is like a mandatory transaction fee. Every time you use energy to do something organised, you pay a small, unavoidable cost in the form of increased entropy somewhere. It's important to note the role of isolation here. The second law applies strictly to isolated systems that don't exchange energy or matter with their surroundings. Earth, for instance, is not an isolated system. It receives a steady stream of low-entropy energy from the sun in the form of visible light, and it radiates higher entropy energy back into space in the form of infrared radiation. This influx and outflow allows the Earth to maintain and even increase its internal order. Trees grow, animals evolve, civilizations build cities, all of which are decreases in local entropy. But this is only possible because the Earth is exporting entropy to the rest of the universe. When you account for the Sun, the Earth, and the surrounding space altogether, the total entropy is still increasing. The second law doesn't forbid local pockets of order. It just requires that the overall ledger, when you include everything, still trends upward. So much for ice cubes and coffee. Now let's zoom out to the larger scales and the longest timescales, the entire universe and its ultimate fate. To understand where the cosmic ledger is heading, we need to first understand where it started. The early universe, shortly after the Big Bang, was hot, dense, and remarkably uniform. Matter and radiation were distributed very evenly across space, with only the tiniest fluctuations, variations of about 1 part in 100,000. The radiation field was in thermal equilibrium, corresponding to a very high entropy state for the photons. But here's the twist. In terms of gravitational structure, the universe actually started in a surprisingly low entropy configuration. All that matter was spread out smoothly. It had not yet clumped into stars, galaxies, or black holes. There was enormous potential for structure formation, for gradients to develop, and for entropy to grow as gravity did its work. Think of it this way. If you have a box of gas, and you start with all the particles evenly distributed, that seems like a high entropy state. But if gravity is important, if the particles attract each other, then the situation is different. For a self-gravitating system, the smooth uniform state is actually unstable and represents relatively low entropy. The particles can increase the system's entropy by clumping together, forming dense structures, releasing energy in the process. This is counterintuitive, but it's a crucial feature of how gravity works. As the universe expanded and cooled, those tiny initial fluctuations in density grew under the influence of gravity. Slightly denser regions attracted more matter, becoming denser still. Over millions of years, the smooth distribution of matter began to develop structure. Filaments, clusters, and eventually galaxies. Inside those galaxies, gas clouds collapsed further, heating up as gravitational potential energy was converted into thermal energy. When the cores of these collapsing clouds reached high enough temperatures and densities, nuclear fusion ignited and stars were born. Each of these processes, collapse, heating, radiation, increased entropy. When a gas cloud collapses under gravity, it doesn't just get denser, it also gets hotter. That heat is then radiated away into the surrounding space as infrared and visible light. The energy that was stored as gravitational potential energy in a diffuse cloud is converted into kinetic energy of the gas particles, heat, and then into radiation that spreads out into the cosmos. The radiation carries entropy away from the collapsing region, and the total entropy of the universe increases. The cosmic ledger records the transaction. Gravitational binding released energy. Structure formed, entropy rose. Stars themselves are magnificent. Long-lived engines that burn down gradients. A star like the Sun has a hot core where nuclear fusion converts hydrogen into helium, releasing energy. That energy works its way outward through the star, eventually radiating from the surface into the cold surrounding space. The temperature difference between the star's core, millions of degrees, and the surrounding interstellar medium, a few degrees above absolute zero, is an enormous gradient. The star is essentially a heat engine that slowly transforms low-entropy nuclear fuel into higher-entropy radiation. Over billions of years, the Sun will fuse most of the hydrogen in its core into helium. Eventually, it will exhaust its fuel, swell into a red giant, shed its outer layers, and settle down as a white dwarf, a dense hot ember that will cool over trillions of years. Every photon the Sun emits is a small step in this process. The concentrated energy stored in atomic nuclei is gradually converted into diffuse light and heat spreading out across space. The ledger notes each transaction: fuel consumed, light emitted, entropy increased. And the Sun is just one star among hundreds of billions in our galaxy, and there are hundreds of billions of galaxies in the observable universe. Each star is doing the same thing, converting low-entropy fuel into higher-entropy radiation. Across the cosmos, trillions of stars are contributing their entries to the ledger, day after day, year after year, eon after eon. On even larger scales, processes like star formation, supernova explosions, and the growth of supermassive black holes all contribute to increasing entropy. When a massive star exhausts its fuel, it can explode as a supernova, scattering heavy elements into space and releasing an enormous burst of energy. That energy heats surrounding gas, drives shock waves, and eventually radiates away into the cosmos. A supernova is a dramatic event, but in thermodynamic terms it's another entry in the ledger. Concentrated energy dispersed, gradients flattened, entropy up. Supermassive black holes lurking at the centres of most galaxies also play a role. As matter spirals into a black hole, it heats up and emits intense radiation, sometimes outshining the entire galaxy. This radiation carries away energy and entropy, further dispersing the energy that was once locked in the gravitational potential of the infalling matter. The accretion process is violent and energetic, but it's also a steady contributor to the universe's growing entropy account. Now, black holes themselves introduce a fascinating twist to the ledger. It turns out that black holes have entropy, a lot of it. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This means that a black hole represents an extraordinarily large number of microstates, even though from the outside it appears to be described by just a few parameters: mass, charge, and spin. When matter falls into a black hole, the entropy of the universe doesn't just stay the same, it increases significantly. The black hole is like a vast repository in the cosmic ledger, a compact object that carries an enormous entropy entry. A black hole with the mass of our Sun has an entropy of about 10 to the power of 54 in natural units. A supermassive black hole with 1 billion solar masses has an entropy roughly 10 to the power of 72. These numbers dwarf the entropy of ordinary matter. To put it in perspective, the entropy of all the stars, gas and planets in a galaxy is negligible compared to the entropy of the supermassive black hole at its centre. Black holes dominate the entropy budget of the universe. They are the major contributors to the ledger's running total. Meanwhile, the universe as a whole continues to expand. As space stretches, light gets redshifted, its wavelength increases, its energy decreases. The cosmic microwave background, the afterglow of the Big Bang, started out as high-energy radiation filling the early universe. Over billions of years, expansion has stretched those photons into the microwave range. Today, the cosmic microwave background has a temperature of about 3 degrees above absolute zero. In the far future, it will cool even further, redshifting into radio waves and beyond. This expansion and cooling is another way in which energy becomes more diluted and less available for doing work. High-energy photons can drive processes. Low-energy photons are much less useful. The expansion of the universe acts like a slow backdrop to all the other processes, a gradual spreading of energy across an ever larger volume. The ledger records this too. Energy diluted, temperature dropped, entropy increased. For now, the universe is still in a vibrant, active phase. Stars continue to form, galaxies continue to collide and merge, black holes continue to grow. But the rate of star formation has been declining for billions of years. Much of the universe's initial supply of hydrogen and helium has already been processed through stars. Some of it is locked up in long-lived low-mass stars that will burn for trillions of years. Some has been converted into heavier elements, locked in planets and stellar remnants. Some has been heated to such high temperatures that it no longer easily condenses into new stars. As time goes on, the raw materials for star formation become scarcer. Galaxies run out of cold gas. The rate at which new stars are born drops. Fewer and fewer new engines are started. The universe will continue to have stars in active regions for a very long time, many trillions of years. But each generation leaves less fuel in forms that are easy to use. The ledger shows a declining rate of new, low-entropy structures being created. The universe is not winding down suddenly. It's doing so very, very gradually. Eventually, star formation will cease almost entirely. The universe will enter an era dominated by stellar remnants. White dwarfs, neutron stars, and black holes. White dwarfs are dense, Earth-sized embers, the cooling cores of dead stars. Neutron stars are even denser, the collapsed remnants of massive stars that exploded as supernovae. Black holes are the endpoints for the most massive objects. These remnants will continue to radiate energy, but at ever lower rates and temperatures. A white dwarf, for example, starts out hot, tens of thousands of degrees, but it has no internal energy source. It simply cools by radiating its heat into space. Over trillions of years, white dwarfs will cool to the temperature of the surrounding universe, eventually becoming black dwarfs, cold, dark, inert lumps of matter. Neutron stars follow a similar trajectory, cooling from millions of degrees to near absolute zero. The fireworks of star formation and the bright glow of galaxies give way to a universe of dim, slowly fading embers. Entropy continues to rise as heat flows from these remnants into the surrounding space, flattening temperature differences bit by bit. Even black holes are not permanent. Quantum effects near the event horizon allow black holes to emit radiation, a process discovered by Stephen Hawking in the 1970s. This Hawking radiation is incredibly faint for large black holes. A black hole with the mass of the Sun would take about 10 to the power of 67 years to evaporate, far, far longer than the current age of the universe. A supermassive black hole would take even longer, perhaps 10 to the power of 100 years or more. But given enough time, even the largest black holes will evaporate. As they do, their enormous entropy is gradually converted into a sea of very low-energy photons and particles. The ledger's largest individual entries are, in effect, dissolved into a smoother, more uniform background. The black hole radiates away its mass energy, bit by bit, until nothing is left but a faint glow of radiation spreading out into the vastness of space. What does the universe look like in this far, far future? It is almost unimaginably large, cold, and dilute. Most matter has either decayed, been absorbed into black holes that have since evaporated, or been converted into low-energy radiation. The distance between any two remaining particles is enormous. Interactions are rare. Temperature differences are tiny, approaching zero. There is still activity in principle. Particles still move, photons still propagate. But there is very little free energy available to drive organised processes. In accounting terms, almost all the available gradients have been drawn down. The energy that once powered stars, drove galactic dynamics, and supported the evolution of complex structures is now so evenly distributed that not much more can happen. The universe has reached a state of near maximum entropy, sometimes poetically called heat death. It's not that everything is literally hot. In fact, everything is very, very cold. The term heat death simply means that the energy has been so thoroughly spread out that it can no longer sustain the kind of flows and gradients that make interesting processes possible. This is the endpoint the ledger has been recording, entry by entry, for billions upon billions of years. It's not a catastrophe in any immediate sense. It's just the logical conclusion of the second law of thermodynamics applied to a closed system. In this case, the universe as a whole. Every process that increases entropy, from the melting of an ice cube to the evaporation of a black hole, is a step along this path. But here's something worth noticing. The direction of this process gives time its arrow. We experience time as having a direction, past, present, future, and that direction is intimately tied to the increase of entropy. We remember the past but not the future. We see glasses break but never spontaneously reassemble. We watch ice cubes melt, never freeze out of warm water on their own. Why? The answer is that the past had lower entropy than the present. The early universe was in a low entropy state, with matter spread smoothly and enormous potential for structure formation. As time went on, entropy increased. The processes we observe, melting, mixing, aging, forgetting, are all manifestations of this increase. Our memories themselves are low-entropy structures, patterns encoded in neurons that require energy gradients to form and maintain. We remember the past because the past was a time when those gradients existed and could support the creation of records. We can't remember the future because the future hasn't happened yet, and also because the act of remembering requires accessing a low-entropy record created by a past event. Breaking a glass is easy. It's easy because there are vastly more microstates corresponding to broken glass than to intact glass. The broken pieces can be arranged in countless ways, different positions, orientations, fragment sizes, and they all count as broken. There's essentially only one microstate, or a very small set, corresponding to the intact glass sitting on the table. When you drop the glass, it shatters, and the system moves from a low-entropy configuration to a high-entropy one. Reversing this, having all the fragments spontaneously leap up, fit together perfectly, and seal themselves into a smooth, unbroken glass, is not forbidden by the fundamental laws of physics. It's just so stupendously improbable that it will never happen. The arrow of time, the felt asymmetry between past and future, is rooted in this statistical behaviour. Does this mean that life, complexity, and order are violations of the second law? Not at all. Life and other complex structures are not exceptions to the rule. They are local patterns sustained by exporting entropy to their surroundings. Earth is a wonderful example. The sun bathes the Earth in a steady stream of low-entropy, high-energy photons. Plants capture that energy through photosynthesis, building complex molecules and structures. Animals eat plants or other animals using the stored chemical energy to maintain their bodies, move, think, and reproduce. All of these processes require energy flows. But the Earth doesn't just absorb energy, it also radiates energy back into space. The key is that the outgoing radiation is at a lower temperature, longer wavelengths, and higher entropy than the incoming sunlight. The Earth receives low-entropy energy and returns high-entropy energy. The difference allows the biosphere, the atmosphere, the oceans, and the intricate systems of weather and climate to maintain and evolve complex order. The local decrease in entropy on Earth is more than compensated by the increase in entropy of the Sun and the surrounding space. The global ledger still shows an upward trend. These pockets of order, ecosystems, cities, individual organisms, are like small, temporary sub-accounts within the larger book. They exist because there are still strong gradients to tap. The Sun is much hotter than the Earth, and the Earth is much warmer than the cold of space. These differences drive flows of energy that can be harnessed to do work, to build structures, to sustain life. But as the universe ages and those gradients diminish, maintaining such pockets of order becomes harder. A universe in which stars have all burned out, black holes have evaporated, and energy is uniformly spread thin offers no gradients to exploit. The ledger still exists, but there are no more interesting transactions to record. It's worth pausing to appreciate the timescales involved here. The current age of the universe is about 14 billion years. The sun will continue to shine for another 5 billion years or so. The longest-lived stars, the small red dwarfs, will burn for trillions of years. White dwarfs will cool over timescales of 10 to the power of 15 years or more. Black hole evaporation takes place over timescales of 10 to the power of 60 to 100 years, depending on the mass. The approach to heat death is not a sudden event. It's an almost unimaginably slow fade that stretches across timescales that make the current age of the universe look like the blink of an eye. For all practical purposes, we live in an era rich with gradients and complexity. Stars shine, planets orbit, life evolves, civilizations rise. The cosmic ledger is still filling in its early pages, still recording active, interesting processes. There is no immediate cause for concern, no need to worry that the universe is about to run down tomorrow or in a million years or even in a trillion years. The slow drift toward higher entropy is a feature of the deepest laws of physics, but it plays out over timescales that are, for human purposes, effectively infinite. And yet there's something oddly comforting about this long view. The increase of entropy is not a malicious force or a design flaw. It's simply a reflection of how energy moves and redistributes itself when there are many, many particles involved. The second law of thermodynamics is not a prohibition. It's a statistical tendency, an accounting rule that describes the most likely direction of change. It allows for complexity, for structure, for life, as long as there are gradients to drive those processes. It even allows for local decreases in entropy, as long as the overall balance sheet tips upward. Think of the universe as that patient accountant, sitting at a vast desk, updating a ledger that stretches across billions of years. Each entry is small, a photon emitted, a molecule colliding, a star converting a bit more hydrogen into helium. The accountant doesn't hurry. There is no deadline, no rush. The work continues, entry after entry, page after page. Time's arrow is marked not by catastrophe, but by the gentle, ongoing spreading out of energy, from concentrated sources to diffuse backgrounds, from high-grade fuel to low-grade waste heat, from sharp gradients to smooth uniformity. The ledger itself is a curious object when you think about it. It has no physical form, no leather binding, no paper pages yellowing with age. It exists as a concept, a way of organizing our understanding of how the universe changes. Yet in another sense, it's the most real thing there is. Every atom, every photon, every quantum fluctuation is a participant in this grand accounting. The ledger is written in the language of thermodynamics, a language that describes not individual particles, but the collective behavior of inconceivably large ensembles. Consider what it means that the ledger is irreversible. When you add an entry, when entropy increases, you cannot erase it. You cannot undo the melting of the ice cube by simply reversing every molecular motion. In principle, the microscopic laws of physics are time reversible. If you could somehow reverse the velocity of every particle in a system, the process would run backward. The shattered glass would reassemble, the melted ice would refreeze, the mixed dye would unmix. But this requires an impossibly precise intervention, a godlike ability to control and manipulate every particle simultaneously. In practice, for any real system with more than a handful of particles, such reversal is beyond impossible. The irreversibility of the ledger entries is not because the fundamental laws forbid backward motion, it's because the starting conditions for backward motion are so extraordinarily specific and unlikely that they simply never occur naturally. Imagine trying to reassemble a shattered glass by throwing the pieces into the air with exactly the right velocities and spins so they collide, fuse, and form a perfect whole. The odds are not merely bad, they are so vanishingly small that the entire history of the universe, repeated countless times, would not be enough to see it happen even once. The ledger moves forward because forward is where the overwhelming majority of possible futures lie. This has profound implications for how we understand causality and time itself. In our everyday experience, causes precede effects. You drop the glass, then it breaks. You light the match, then the candle ignites. This temporal ordering feels fundamental, but it's actually a consequence of entropy. In a universe where entropy decreased instead of increased, the temporal ordering would appear reversed from our perspective. Events would seem to have effects that preceded their causes, but of course, inhabitants of such a universe would experience things as perfectly normal, with their own arrow of time pointing in the direction of their entropy increase. The arrow of time is not an external feature imposed on the universe. It emerges from the statistical behaviour of matter and energy. One of the more subtle aspects of the ledger is that different systems can have different rates of entropy increase. A hot object in cold surroundings will have its entropy increase rapidly as heat flows out. A system already near equilibrium will have very slow entropy increase, with only small fluctuations occurring. The universe as a whole has a certain average rate of entropy production, but this rate changes over cosmic time. In the early universe, when matter was clumping and stars were forming at high rates, entropy was increasing rapidly. In the far future, when most processes have run their course and the universe is cold and dilute, the rate of entropy increase will be much slower, though it will continue as long as any gradients remain. This varying pace of change means that the ledger doesn't fill up at a constant rate. Some epochs see many entries added quickly, others see a slow trickle of small adjustments. Right now, in the current epoch, we're in a moderately active period. Star formation is declining from its peak billions of years ago, but it's still happening, galaxies are still merging, black holes are still growing. The cosmic ledger is being filled at a steady pace, neither frantically nor languidly. One of the questions that sometimes troubles people when they first encounter these ideas is whether the eventual heat death makes everything meaningless. If the universe is ultimately heading toward a cold, dark, featureless state, does that render our current existence pointless? This is more a philosophical question than a scientific one, but it's worth addressing briefly. The heat death of the universe is so remote in time, so many orders of magnitude beyond our normal experience, that it bears no relationship to the meaning or value we find in our daily lives. The fact that a sandcastle will eventually be washed away by the tide doesn't make building it meaningless in the moment. The fact that a symphony ends doesn't negate the beauty of the music while it plays. Moreover, meaning and purpose are not properties written into the fundamental laws of physics. They are emergent features of complex systems like human consciousness, things that arise in particular contexts with particular structures. The universe doesn't care whether entropy increases or decreases. It simply follows its statistical tendencies. But within the universe, in the brief epochs and small regions where gradients exist and complexity can flourish, beings like us can create, experience, and value things. The second law of thermodynamics doesn't comment on any of that. It just describes how energy spreads out. In fact, one might argue that the temporary nature of order makes it more precious, not less. If structures lasted forever, if gradients never ran down, there would be no change, no evolution, no history. The fact that stars burn through their fuel and eventually die is what allows them to shine brightly while they live. The fact that organisms must continually work to maintain their organization, eating, breathing, repairing damage, is what makes them active participants in the world rather than static objects. The flow of entropy through a system is what enables life, thought, and action. The ledger also reveals something interesting about information. Information and entropy are closely related concepts, though the relationship can be counterintuitive. In a sense, information is negative entropy. It represents structure, pattern, and order. When you erase information, you necessarily increase entropy. This is not just a metaphor, it's a physical fact. A computer's hard drive storing data is in a lower entropy state than the same drive with the data scrambled randomly. Erasing the data requires dissipating energy as heat, which increases the entropy of the surroundings. This connection between information and entropy means that the cosmic ledger is also, in a way, tracking the loss of information. As the universe evolves toward higher entropy, detailed information about past states becomes harder to recover. The specific microstate of the early universe, the exact position and momentum of every particle, is information that has been effectively scrambled and dispersed by subsequent evolution. You can't look at the current state of the universe and work backward to determine exactly how things were arranged 14 billion years ago, except in broad statistical terms. The information has been, in a sense, erased into the growing entropy. This is related to why we can't remember the future. Memories are information structures, low-entropy patterns that encode details about past events. They exist because there were gradients available to create them. The future, by contrast, has not yet created such structures. When it does, when the future becomes the present and then the past, it will leave behind its own information traces, its own memory records. But from our current vantage point, looking forward, there are no such records to access. The asymmetry of memory is another manifestation of the arrow of time, another way the ledger's one-directional filling makes itself felt in our experience. The gradual dissipation of information as entropy increases also has implications for what the far future universe knows about its own past. In a state of maximum entropy, where energy is uniformly distributed and no gradients remain, there are no structures that encode historical information. The universe in heat death, if such a state is ever fully reached, would be in a sense amnesiac, unable to maintain records of its earlier, more structured epochs. This isn't a conscious forgetting, of course. It's simply that the physical basis for storing information, differences, structures, patterns, would no longer exist. But we are nowhere near that state, and won't be for incomprehensibly long times. The universe currently has abundant structure, abundant information, abundant memory. Rocks record geological history in their layers. Light carries information about distant stars and galaxies. DNA preserves information about evolutionary history. Human brains store memories. Culture stores knowledge, and civilization builds libraries and databases. All of these are temporary, local, low-entropy structures sustained by the flow of energy through the biosphere, maintained by the sun's steady output of low-entropy photons. The cosmic ledger permits these pockets of information to exist, as long as the gradients that support them remain. There's also a subtle point about what we mean by the universe when we talk about its entropy. We usually mean the observable universe, the region of space from which light has had time to reach us since the Big Bang. But the universe might be much larger than the observable portion, perhaps even infinite. If it's infinite, then the total entropy is also infinite, both now and at any other time. What matters for the second law is not the absolute value of entropy, but its rate of change. An infinite universe can still have entropy increasing everywhere, with the cosmic ledger growing without bound, even though it started and will remain infinite. Furthermore, we don't know with certainty what happens in the very, very far future. Our current understanding is based on extrapolating known physics forward, but there could be phenomena we don't yet understand that become important on extremely long time scales. Perhaps there are slow processes involving the decay of matter itself. Protons might be unstable, though if so, they have lifetimes vastly longer than the current age of the universe. Perhaps the vacuum of space itself is not in its lowest energy state, and over immense times it could undergo a transition that changes the fundamental properties of physics. Perhaps quantum fluctuations in a near-empty universe could spontaneously create new structures, though such events would be so rare as to be essentially irrelevant. These speculations don't change the basic picture of the ledger steadily filling with entropy entries, but they remind us that our knowledge has limits. The second law of thermodynamics, as we understand it, is one of the most solid and well-tested principles in all of physics. It has never been observed to be violated in any isolated system. But our understanding of the universe's ultimate fate involves extrapolating over timescales that dwarf anything we can test or observe directly. Kisa's degree of humility is appropriate. Still, within the framework of what we do know, the picture is clear. The ledger records the spreading of energy, the flattening of gradients, the movement from improbable, low-entropy states to probable, high-entropy ones. This is not a process that happens quickly or dramatically. It's a slow, steady statistical drift that plays out over scales that make geological time look instantaneous. The universe is patient. The ledger has room for countless entries. There is no rush, no urgency, no impending deadline. As you settle in for the night, imagine that accountant at work. Imagine the ledger growing slowly and steadily as stars burn, ice cubes melt, and black holes evaporate over timescales that dwarf comprehension. The universe is not collapsing into chaos. It's not falling apart. It's simply redistributing its energy, balancing its books, and moving from one macrostate to another in the most probable way possible. The process is peaceful, even beautiful in its inevitability. Entropy is not the enemy. It's just a number, a tally, a quiet record of how things change. And for now, in this era of stars and galaxies and planets teeming with life, the ledger still has plenty of room left to record the transactions of an active, vibrant cosmos. The arrow of time points steadily forward, but that forward direction is not toward doom. It's simply toward a different kind of balance, a state where energy is shared more evenly and gradients have gently, gradually flattened out. So rest easy. The universe's ledger is in good hands. The bookkeeping is meticulous. The entries are irreversible, but that's just how the accounting works. Time's arrow is steady, pointing from past to future, from order to greater probability, from concentration to diffusion. And in the meantime, there are stars shining, planets turning, and countless small moments of organized complexity playing out across the cosmos. The ledger records them all, one line at a time, with the patience of eternity, never rushed, never anxious, simply documenting the quiet, inexorable flow of energy from here to there, from then to now, from what was concentrated to what becomes shared, in a story written not in triumph or tragedy, but in the calm, steady arithmetic of thermodynamic law. The next story is about to begin. Please relax and enjoy. Tonight we're not dealing with explosions or catastrophic collisions. We're simply reviewing the maps, the quiet, methodical blueprints that explain how the universe arranged its galaxies across billions of light years. On the larger scales, galaxies are not scattered randomly like sand grains on a beach. Instead, they line up along elongated structures called filaments, gather in dense clusters at intersections, and spread across broad walls, all while leaving enormous empty regions called voids. Cosmologists call this arrangement the cosmic web, and it's exactly what it sounds like. A sprawling three-dimensional network that resembles a vast spider's web stretching across space. Think of it as the universe's zoning plan, survey marks, infrastructure maps, and development documents that show where matter ended up and why. The story begins long before any galaxies existed, back when the universe was almost perfectly smooth. Almost, but not quite. In those earliest moments, tiny differences in density existed. Variations so small, they amounted to only a few parts in 100,000. These weren't dramatic features. They were subtle ripples in the hot plasma that filled space, barely distinguishable from the background. But they were there, and they mattered. Today we can see these ripples as faint temperature variations in the cosmic microwave background, that ancient light that has travelled across the universe for nearly 14 billion years. These temperature differences are like the first surveyor's marks on a blank plot of land. Faint pencil lines indicating where the foundations would eventually be poured. They didn't look like much, but they told gravity where to begin its slow work. Gravity is patient, it doesn't rush. These tiny density fluctuations gave gravity something to work with, regions where matter was ever so slightly more concentrated than the surrounding space. Over time, these slightly denser patches would attract more matter, while slightly less dense regions would lose material. The ripples acted as seeds, quiet instructions embedded in the fabric of space that would eventually determine where galaxies would cluster and where they would be scarce. The universe had its initial survey complete, its first set of marks placed. Now the real construction could begin, though it would take hundreds of millions of years before anyone could see progress. Most of the universe's matter, however, is not the ordinary stuff we're familiar with. It's dark matter, material that doesn't emit, absorb or reflect light, making it invisible to telescopes. But dark matter does interact through gravity, and that's all gravity needs. While the early universe was still filled with hot plasma too energized for atoms to form, dark matter was already beginning to respond to those initial density ripples. It started to clump, slowly at first, forming concentrations in regions where the original fluctuations had been slightly more pronounced. These concentrations acted like invisible wells or depressions in the expanding universe. Gravitational pits that would grow deeper over time. Think of dark matter as invisible scaffolding, the hidden framework behind the visible universe. While ordinary matter was still too hot and energetic to settle down, dark matter was already laying foundations. These dark matter halos, as astronomers call them, were the first structures to form. They weren't galaxies yet. just regions of space where dark matter had accumulated in slightly higher densities, creating gravitational wells that would later trap gas and dust. Nothing flashy was happening, nothing you could see, even if you had been there with a telescope. Just gravitational depressions forming in the darkness, building plots marked out on the cosmic landscape where future neighbourhoods would eventually rise. Eventually, the universe cooled enough for ordinary matter, primarily hydrogen and helium gas, to respond to gravity's pull. This gas began to fall into the dark matter halos, following the paths that invisible scaffolding had laid out. Gravity guided the gas along routes carved by dark matter, like water flowing through a system of pre-dug channels. The gas didn't create its own pattern, it simply followed the blueprint that dark matter had already established. As the gas fell into these halos, it compressed and heated, and in the densest regions it eventually cooled enough to collapse further, forming the first stars and then the first galaxies. The overall pattern of where galaxies appear across the universe is therefore not determined by the luminous matter we can see, but by the underlying dark scaffolding that quietly organised the entire layout. As more matter accumulated in some regions, a larger pattern began to emerge. Dark matter didn't just form isolated clumps scattered evenly across space. Instead, it created a network, a web of connected structures. Elongated streams of dark matter and gas formed between the densest regions, creating what astronomers call filaments. These filaments are like the main supply corridors in a city's infrastructure plan, long, relatively broad routes that connect major hubs and through which material flows. They're not as densely packed as clusters, but they're far from empty. Gas streams along these filaments over cosmic time, gradually feeding the galaxy groups and clusters at the intersections. From a distance, filaments are subtle structures, easier to detect statistically across large surveys than to see as bright features in any one region, but they represent a core element of the cosmic web's architecture. Where multiple filaments intersect, gravitational wells become particularly deep. These intersections are where galaxy clusters form, the dense downtowns of the cosmic web, regions packed with hundreds or even thousands of galaxies all bound together by gravity. Clusters are immersed in massive dark matter halos and filled with extremely hot gas that emits X-rays. They represent the nodes of the cosmic network, the major hubs in a vast transport system, where everything nearby is gently funneled inward over billions of years. If you were to map the universe's matter distribution, clusters would stand out as the brightest, densest points, the places where the web's underlying design is most concentrated and most obvious. Between the filaments and clusters, you sometimes find even larger patterns, walls and sheets of galaxies spanning hundreds of millions of light years. These aren't solid structures in any sense. They're statistical patterns, regions where the density of matter is slightly elevated over enormous distances. Think of them as low-rise districts spreading between the densest hubs and the emptiest voids, transitional zones that help connect the web's various elements into a coherent whole. They're part of the universe's zoning map, showing how matter is distributed not just at individual points, but across vast volumes of space. These walls represent some of the largest known structures in the universe, yet they're also among the most difficult to perceive directly because their density contrast is so subtle. And then there are the voids, vast regions of space containing very few galaxies, stretching across hundreds of millions of light years. These aren't absolute vacuums, they contain dark matter, gas, and a scattering of isolated galaxies, but they're remarkably underdense compared to the rest of the universe. In the planning metaphor, voids are like large plots that simply never got developed. No highways were built through them, no major junctions formed within their boundaries. The same initial fluctuations that created dense regions necessarily left other regions underdense, and as gravity amplified these contrasts over time, the low-density regions expanded into voids. They provide the negative space that defines the cosmic web, the empty volumes that make the filaments and clusters stand out by contrast. This entire structure didn't spring into existence suddenly. The cosmic web grew gradually over billions of years through a process cosmologists understand quite well. As the universe expanded, gravity slowly amplified the original density ripples. Regions that started slightly overdense attracted more matter and became denser still. Regions that started slightly underdense lost matter to their surroundings and became emptier. Dark matter halos merged when they encountered each other, forming larger halos. Filaments thickened as more gas flowed along them. Clusters accreted more galaxies over time, growing from small groups into massive congregations. Voids expanded as matter drained from them into surrounding structures. Computer simulations show this as a gradual sharpening of patterns. What begins as a noisy, nearly uniform distribution of matter slowly evolves into a clearly defined network, like a faint sketch being traced over repeatedly, until the lines become bold and unmistakable. These numerical simulations are essential tools for understanding the cosmic web. Cosmologists set up virtual universes on supercomputers, starting with initial conditions that match the early universe: small density fluctuations in a mix of dark matter, ordinary matter, and dark energy, all expanding according to the equations of general relativity. Then they let the simulation run forward in time, allowing gravity and expansion to evolve the system. The results are remarkable. Three-dimensional structures of halos, filaments, and voids that closely resemble what telescopes observe in the real universe. These simulations act like model blueprints or proof-of-concept designs. If the input physics is correct, the large-scale pattern that emerges after billions of simulated years should match the actual cosmic web. And it does, providing strong confirmation that cosmologists understand the basic processes at work. Observationally, astronomers reconstruct the cosmic web through massive galaxy surveys. Modern telescopes can measure the positions and distances of hundreds of thousands, or even millions of galaxies. The position on the sky is straightforward to measure, but distance requires determining each galaxy's redshift, the stretching of light caused by the universe's expansion. Higher redshift generally means greater distance. When astronomers plot these galaxies in three-dimensional space using their coordinates and redshifts, the cosmic web emerges clearly from the data. Filaments, walls, clusters, and voids all become visible as patterns in the distribution of points. To astronomers, these surveys are completed site plans, collections of dots on a coordinate grid that trace the underlying structure in a way the human eye and brain can immediately recognize as organized rather than random. There's a complication, though. We don't see dark matter directly, we only observe its gravitational effects. The galaxies we count in surveys are traces of the underlying dark matter distribution, but they're not perfect traces. Galaxies form more readily in certain types of dark matter halos and certain environments, a property astronomers call bias. A galaxy survey doesn't show the dark matter web directly. It shows where galaxies chose to form within that web. Cosmologists calibrate this bias using simulations and observations, developing models that account for the relationship between visible galaxies and invisible dark matter. The result is a layered set of blueprints. One map showing the distribution of luminous matter, another inferred for the distribution of dark matter, and both carefully aligned to show how the visible universe reflects the invisible scaffolding beneath it. Dark energy also plays a role in shaping the cosmic web, though more subtly. Dark energy is a mysterious component of the universe that drives accelerated expansion, causing space itself to stretch faster and faster over time. While gravity works to pull matter together into structures, dark energy works against it by expanding the underlying space. In the universe's early history, gravity dominated and structures grew rapidly. But as dark energy's influence became more pronounced over billions of years, it became harder for new large-scale structures to form. In planning terms, it's as if the grid of space itself is stretching, making it increasingly difficult to build new neighborhoods or expand existing ones. Most of the cosmic web we see today was laid down before dark energy's influence became dominant, during the era when gravity could still effectively organize matter on the largest scales. Even today, the cosmic web is not a static structure. Gas continues to flow along filaments into galaxies and clusters, providing fresh material for ongoing star formation. This inflow isn't violent or dramatic. It's a slow, steady supply through cosmic pipelines. Simulations show cold gas streams feeding galaxies along filaments, while hot gas accumulates in the massive halos around galaxy clusters. The web supports these ongoing flows, acting as the infrastructure through which material is delivered to where stars can form. The pattern of the web itself doesn't change rapidly anymore. The major filaments and clusters are established, but matter still moves through the established channels, and galaxies still grow and evolve within their assigned neighborhoods. A galaxy's location in the cosmic web significantly affects its properties and evolution. galaxies in dense cluster environments tend to be older, redder, and depleted of gas. They've undergone numerous interactions with neighbours, experienced ram pressure stripping as they move through hot intra-cluster gas, and exhausted their reserves of star-forming material. Galaxies along filaments often show more active star formation, supported by fresh gas flowing in from the cosmic web. Void galaxies, isolated from the main flows of matter, evolve more slowly and independently. They experience fewer mergers, accumulate gas more gradually, and can maintain distinct star formation histories. In the zoning language we've been using, different districts of the cosmic web encourage different architectural styles. The environment a galaxy inhabits shapes what it becomes. Astronomers have multiple methods beyond simply counting galaxies to map the cosmic web. Weak gravitational lensing provides one powerful technique. The gravity of dark matter concentration subtly distorts the light from more distant galaxies, bending it along its path. By measuring these tiny distortions in the shapes of background galaxies across large areas of sky, cosmologists can create maps of the total mass distribution, including the invisible dark matter. X-ray telescopes reveal hot gas in galaxy clusters and along some filaments, while radio observations can detect the same gas and even trace magnetic fields. These different techniques provide complementary views, mass maps, gas maps, galaxy maps, all of which can be stacked together. When they are, they all show the same underlying web-like pattern, confirming that the structure is real and not an artifact of any single observational method. The cosmic web also has a history that astronomers can observe directly. Because light takes time to travel across the universe, looking at distant objects means looking back in time. By observing galaxies and structures at different redshifts, astronomers effectively see snapshots of the cosmic web at different ages. The youngest, most distant universes observable show a more uniform distribution of galaxies with less pronounced structure. The web is still forming, the patterns still emerging from the initial noise. Older universes, closer to our present day, display increasingly clear networks of filaments and clusters. Comparing these snapshots across cosmic time allows astronomers to test their models of structure formation, checking whether the theoretical blueprint model matches the actual construction schedule the universe followed. Despite the success of the cosmic web model, many details remain under active investigation. How feedback from supernovae and active galactic nuclei redistributes gas within and between halos is not fully understood, yet it significantly affects how galaxies form along the web. How the smallest dark matter halos, those too small to form bright galaxies, populate filaments and voids is still being mapped out. What the web looks like in extremely low-density regions, where finding and observing galaxies is difficult, requires better data. These are the fine print annotations in the planning documents, small notes and revisions added as new observations refine the existing maps. The broad picture is clear and well established, but the details continue to sharpen with each new survey and simulation. As you settle into sleep tonight, you can let your mind rest on this image. The cosmic web is not something visible to the naked eye, not something you could see even with the most powerful telescope if you looked at just one small patch of sky. But it underlies everything. Every galaxy, including our Milky Way, sits within this vast, mostly invisible framework. Dark matter halos provide the foundation. Filaments form the corridors. Clusters mark the intersections. Voids define the empty spaces. Together they create a structure of almost unimaginable scale, spanning billions of light years, connecting every part of the observable universe into a single coherent network. The universe is not random chaos. It's a large, slow construction project whose main plans were drawn up in the first moments after the Big Bang, when tiny quantum fluctuations were imprinted on space itself. Those fluctuations became the surveyor's marks, the initial guidelines that gravity would follow. Dark matter laid the invisible scaffolding. Ordinary matter filled in the visible structures. Dark energy stretched the canvas. And now, nearly 14 billion years later, the project is mostly complete. The cosmic web stands as it is, a faint, sprawling network of neighbourhoods, roads, and empty lots stretching farther than the mind can easily grasp, steadily expanding in the dark. This is the architecture of the universe on its largest scale. Not built by any intelligence, not designed by any mind, but assembled gradually through the simple, patient work of gravity acting on matter over cosmic time. The filaments connect clusters that are themselves made of galaxies, which contain billions of stars, some with planets, some perhaps with observers looking out and wondering about the structure they inhabit. From our vantage point within it, we can barely perceive the web, but with telescopes and surveys and simulations, we've learned to map it, to understand it, to see the underlying order that gravity created from those ancient tiny ripples. And so the universe is not a featureless expanse. It has texture, structure, organisation. It has neighbourhoods where galaxies crowd together and vast expanses where they are scarce. It has highways of dark matter along which gas flows, and intersections where matter accumulates into the densest structures known. It has a history, a present state, and a future. As dark energy continues to accelerate the expansion of space, the web will stretch further, new structures will become harder to form, existing structures will become more isolated from one another as the space between them grows. But the basic pattern is set now, the blueprint fully realised. The cosmic web as it exists today is the architecture we live within, the framework that holds galaxies in their places and channels matter through the universe. Close your eyes and picture it if you can, not the bright galaxies themselves, which are merely lights marking nodes and paths, but the invisible web of dark matter beneath them. Imagine pulling back farther and farther from our galaxy, from our local group, from our local supercluster, until you can see the full three-dimensional network. Filaments stretching in all directions, clusters glowing at junctions, voids opening as dark empty spaces, walls spanning distances that light takes hundreds of millions of years to cross. All of it connected, all of it grown from the same initial conditions, all of it slowly evolving as the universe ages and expands. This is the landscape on the larger scale, the final zoning map of the cosmos, showing where matter congregated and where it didn't, which routes gravity carved out and which regions remained sparsely populated. It's a quiet story, lacking drama or sudden events, but it's the story of how the universe organised itself into the structure we observe today. The blueprint was drawn long ago in those first moments. Gravity did the slow work of construction. Dark matter provided the foundation. Ordinary matter filled in the details. And now the cosmic web spans the observable universe, a testament to simple physical laws operating over immense scales of space and time. As the universe continues expanding and you drift towards sleep, let this thought settle. We are part of this structure, embedded in it, subject to its organisation. Our galaxy lies within a filament connected to a small cluster in a region between larger voids. We are not at a special location, but we are at a comprehensible one, a point within a vast network that has been mapped, studied and understood through observation and theory. The cosmic web is both the largest structure we know, and in some ways one of the simplest. It follows from basic principles: gravity, expansion, initial fluctuations, and time. From those ingredients, the universe built itself a framework, and within that framework everything else, stars, planets, and observers, emerged. Sleep well in this knowledge. The universe has structure, it has order on the larger scales, and that order, impersonal and vast though it is something we have learned to see, to map, and to understand. The cosmic web stretches across billions of light years, mostly invisible, forever expanding, quietly holding the visible universe in its gravitational embrace. It is the largest blueprint ever drawn, and we have learned to read it. As you rest with that image of the cosmic web in mind, consider how remarkable it is that we've come to understand this structure at all. For most of human history, the universe beyond Earth was a mystery written in lights that moved across the night sky, according to patterns we could observe but not explain. The idea that galaxies, entire islands of billions of stars, even existed is barely a century old. The realization that these galaxies are not scattered randomly, but arranged in an enormous web-like structure is younger still, emerging only in the last few decades as technology allowed us to map millions of galaxies across vast distances. We live in perhaps the first generation of humans who can look up at the night sky and understand, at least in broad strokes, the architecture that organizes everything we see. The discovery of the cosmic web was gradual, built on layers of observation and theory. Early hints came from galaxy surveys in the 1970s and 1980s, when astronomers began plotting the positions of galaxies in three-dimensional space. What they found surprised them. Galaxies weren't distributed uniformly or even in simple clusters. Instead, they formed elongated chains and sheets, with curious empty regions between them. One of the most famous early discoveries was the Great Wall, a vast sheet of galaxies stretching across hundreds of millions of light-years. Later surveys found similar structures, the Sloan Great Wall, even larger, the Hercules Corona Borealis Great Wall, larger still. Each new survey pushed the scale of known structures higher, revealing that the universe's architecture operated on scales far beyond what anyone had initially imagined. These observations presented a puzzle. Why would gravity create such patterns? Why filaments and walls and voids instead of a more uniform distribution or simple clustering? The answer came from understanding how structure grows from initial conditions. If you start with a perfectly uniform distribution of matter, gravity has nothing to work with. Every region pulls equally on every other region and nothing happens. But start with tiny variations, and gravity has something to amplify. Dense regions pull matter from their surroundings, growing denser while creating voids nearby. But the process isn't spherically symmetric, because the initial fluctuations aren't either. They have shape, orientation, and scale. Some regions are elongated, some are sheet-like, some are more compact. Gravity amplifies these shapes as it amplifies the density contrasts, leading naturally to filaments, walls, and nodes. Computer simulations made this clear in a way that mathematical equations alone could not. When cosmologists ran their first large-scale simulations in the 1980s and 1990s, feeding in the parameters of the universe and letting gravity evolve matter forward in time, they saw the cosmic web emerge spontaneously from the calculations. No one programmed in filaments or voids. These structures arose naturally from the physics. The simulations showed matter streaming along gravitational gradients, collecting in elongated patterns, forming dense nodes at intersections. When compared to actual galaxy surveys, the match was striking. The simulated universe and the real universe showed the same kinds of structures on the same scales. This was powerful confirmation that the theoretical framework was correct, but understanding the web requires understanding what fills it and what drives its evolution. Dark matter dominates the mass budget, making up about 85% of all matter in the universe. This invisible substance doesn't interact with light, which is why we call it dark, but it does interact gravitationally. In fact, in the early universe, dark matter was free to respond to gravity before ordinary matter could. While ordinary matter was still coupled to photons in a hot, opaque plasma, dark matter was already beginning to clump. This gave it a head start in forming structures. By the time ordinary matter finally decoupled from photons and could freely fall into gravitational wells, an event we observe as the cosmic microwave background, dark matter had already sketched out the basic pattern. Ordinary matter simply followed where dark matter led. This explains why the cosmic web is first and foremost a dark matter structure. The filaments, halos, and voids are primarily composed of dark matter. Galaxies trace this structure because they form where the dark matter is concentrated, but they represent only a small fraction of the total mass. If you could somehow see dark matter directly, the cosmic web would appear much more prominent and continuous than it does in galaxy surveys. The galaxies are like streetlights along highways. They show you where the roads are, but most of the road exists between the lights, invisible in the darkness. Dark energy enters the story later, becoming significant only when the universe was several billion years old. Before that, the universe's expansion was decelerating due to gravity. Matter was pulling back on the expansion, slowing it down, which allowed structures to grow efficiently. But as the universe expanded and matter became more dilute, the influence of dark energy, a property of space itself, began to dominate. Dark energy drives accelerated expansion, causing space to stretch faster over time. This has profound implications for structure formation. In an accelerating universe, it becomes progressively harder for gravity to pull matter together across large distances. The expansion works against gravity, pulling regions of space apart faster than gravity can draw them together. This means the cosmic web we see today is essentially frozen in its large-scale pattern. The major filaments and clusters formed during the era when gravity could still overcome expansion on those scales. New clusters can still form through mergers of existing structures, and galaxies can still fall into clusters along established filaments, but entirely new large-scale structures are no longer forming. The expansion has outpaced gravity's ability to organize matter on the larger scales. In a sense, the cosmic web is a fossil from an earlier epoch, a record of structure formation during the first several billion years of the universe's history, now preserved and slowly stretched by accelerating expansion. Yet within this frozen large-scale pattern, smaller-scale activity continues. Galaxies still form stars, still merge with neighbours, still evolve. Gas still flows along filaments, feeding new star formation. Galaxy clusters still accrete new members from surrounding regions. The web provides the infrastructure within which these processes occur, channeling matter and influencing evolution without itself changing dramatically. It's like a city whose major highways and districts were laid out long ago and now define how traffic flows and where development happens, even though individual buildings continue to rise and fall. The role of gas in the cosmic web deserves particular attention. While dark matter defines the overall structure, ordinary matter, primarily hydrogen and helium gas, is what we actually observe in most contexts. This gas behaves differently from dark matter. It can collide with itself, converting kinetic energy into heat. It can cool by radiating that heat away. It can collapse into dense clouds and form stars. All these processes affect how gas distributes itself within the dark matter scaffolding. In low-density regions like filaments, gas may remain diffuse and warm, detectable only through its absorption of light from background sources. In high-density regions like clusters, gas becomes extremely hot, millions of degrees, and emits brightly in X-rays. This hot intracluster gas is one of the most massive components of galaxy clusters, often outweighing all the stars in all the galaxies in the cluster combined. It fills the space between galaxies, trapped by the cluster's gravitational well, heated by the energy of galaxies falling in, and by shocks propagating through the gas. When new galaxies fall into a cluster, they plough through this hot gas, which strips away their own cooler gas through ram pressure. The same effect you feel when you stick your hand out a car window. This process transforms galaxies, shutting down their star formation and changing their appearance. A blue star-forming spiral galaxy that falls into a cluster can become a red, passive elliptical galaxy over time, its gas stripped away, its star formation choked off. The cosmic web doesn't just organize where galaxies are, it influences what kinds of galaxies they become. Filaments too contain gas, though it's harder to observe. The gas in filaments is typically warm, tens of thousands to hundreds of thousands of degrees, too cool to emit X-rays efficiently, but too hot to form stars. This gas remains largely invisible, except when illuminated by bright background sources or when observed through its subtle absorption signatures. Yet this filament gas represents a significant fraction of the universe's ordinary matter, perhaps as much as half of all the baryons that aren't locked up in stars or dense gas clouds. It's part of what astronomers call the missing baryon problem, the challenge of accounting for all the ordinary matter that should exist based on measurements of the early universe. Much of it appears to be hiding in the warm gas of cosmic filaments, too diffuse to easily detect but collectively massive. The flow of gas along filaments into galaxies is crucial for understanding how galaxies grow and form stars over cosmic time. Stars form from cold, dense gas, but galaxies can exhaust their internal gas supplies relatively quickly, within a billion years or so if star formation proceeds unchecked. Yet we observe galaxies forming stars continuously over much longer timescales. This means they must be replenishing their gas from external sources. Filament inflow provides that replenishment. Cold gas streams along filaments, funneled by gravity into galaxy halos, where it can cool further and eventually form stars. This process is most efficient for galaxies connected to filaments, which may explain why such galaxies show more ongoing star formation than similarly sized galaxies in voids. Void galaxies present an interesting contrast. These isolated systems, far from the main filaments and clusters, evolve in relative solitude. They experience fewer mergers, accumulate gas more slowly, and maintain lower star formation rates. Yet they're not entirely quiescent. Some void galaxies show recent star formation, suggesting they're not completely cut off from gas supply. Perhaps they're slowly accreting material from the diffuse gas that does exist in voids, or perhaps they're recycling gas from earlier generations of stars. The differences between void galaxies, filament galaxies, and cluster galaxies demonstrate how environment shapes evolution. The cosmic web provides different conditions in different regions, and galaxies adapt to those conditions in observable ways. This environmental dependence extends to galaxy properties beyond just star formation. Cluster galaxies tend to be larger, more massive, and older on average than field galaxies. They've had more opportunities to merge with neighbours, growing through accretion. They've undergone more interactions that can trigger bursts of star formation or feed supermassive black holes at their centres. Their shapes are affected. Cluster galaxies are more likely to be elliptical or lenticular, with smooth light distributions and little cold gas, while field galaxies are more often spirals with disks and active star formation. Even the dark matter halos around galaxies differ depending on location. Cluster galaxies sit in halos that have been tidally stripped and shaped by interactions, while isolated galaxies retain more extended, undisturbed halos. The cosmic web also affects galaxy spins and orientations in subtle ways. Studies have found weak correlations between galaxy properties and the direction of nearby filaments. Some galaxies seem to have their spin axes aligned with or perpendicular to filaments, depending on their mass and location. These correlations are statistical rather than deterministic. Not every galaxy follows the pattern, but they suggest that the large-scale structure imprints itself on smaller-scale properties. The way matter flows along filaments can influence how galaxies acquire angular momentum, which in turn affects their final shapes and spin directions. Even something as fundamental as which way a galaxy rotates may have been influenced by its position in the cosmic web. Observing the cosmic web across cosmic time has revealed how it evolved and continues to evolve. At high redshifts, looking back to when the universe was only a few billion years old, the web appears less mature, structures are less pronounced, filaments are thinner and less well defined, clusters are smaller and less rich in galaxies. This is exactly what models predict. The web grows over time as gravity amplifies initial density contrasts. By comparing observations at different epochs with simulations run to the same epochs, astronomers can test whether the growth rate matches expectations. So far, the agreement is good, providing yet more confirmation that the basic picture is correct. Yet there are puzzles. Some observations suggest that structures might be growing slightly slower than the simplest models predict, which could indicate something subtle about dark energy or gravity on large scales. Other observations hint at unexpectedly large structures that seem difficult to form in the available time given the measured density fluctuations in the early universe. These potential tensions are being investigated carefully. They could be statistical flukes, observational systematics, or genuine hints that the standard model needs refinement. This is how science progresses. The broad framework is established, but the details are continually tested and refined as data improves. The techniques for mapping the cosmic web continue to advance. Early surveys measured redshifts one galaxy at a time, a painstaking process that limited sample sizes. Modern surveys use spectrographs that can measure hundreds of galaxy redshifts simultaneously, covering large areas of sky in reasonable observing time. The Sloan Digital Sky Survey, one of the most influential projects in modern cosmology, mapped millions of galaxies, revealing the cosmic web in unprecedented detail. Newer surveys like the Dark Energy Spectroscopic Instrument are pushing even further, aiming to map tens of millions of galaxies across cosmic time. Each new dataset sharpens the picture, revealing finer structures and extending the map to earlier epochs. Complementary techniques add depth to the picture. Weak gravitational lensing surveys map the total matter distribution, both dark and luminous, across large areas. These mass maps show the cosmic web as seen through its gravitational effects, rather than through its luminous traces, providing an independent view. X-ray surveys reveal the hot gas in clusters and filaments, while radio surveys can detect cold gas, neutral hydrogen, and even magnetic fields threading through the web. Combining all these observations creates a multi-wavelength, multi-messenger picture of the cosmic structure, each technique sensitive to different components and physical conditions. The future promises even more detailed views. Upcoming telescopes and surveys will map the cosmic web at higher redshifts earlier times, revealing how the web looked when it was just beginning to form. They'll measure galaxy properties within the web in greater detail, tracking how environment influences evolution across billions of years. They'll measure the velocities of galaxies, not just their positions, revealing how matter flows through the web, and they'll map the web on smaller scales, down to individual galaxy groups and even smaller halos, connecting the largest cosmic structures to the scales where individual galaxies live. As these observations accumulate, they feed back into theory. Simulations become more sophisticated, including not just dark matter, but also gas physics, star formation, feedback from supernovae and black holes, magnetic fields, and cosmic rays. These advanced simulations can predict not just where structures form, but also what kinds of galaxies should populate them, what their properties should be, and how they should evolve over time. Comparing these predictions to observations tests our understanding of both the cosmic web and the galaxy formation processes that occur within it. When predictions and observations agree, confidence grows. When they disagree, it points to missing physics or incorrect assumptions that need to be addressed. One area of active research is the connection between the smallest dark matter halos and the galaxies that inhabit them. Dark matter theory predicts that halos should exist across a vast range of masses, from galaxy clusters down to masses far smaller than any visible galaxy. But not every dark matter halo contains a visible galaxy. Below certain mass thresholds, the gas in a halo may be too warm to collapse and form stars, or feedback from early stars may blow the gas out, preventing further star formation. Understanding exactly where the threshold lies and how it depends on environment and cosmic epoch is crucial for connecting the dark matter web to the visible galaxy distribution we observe. Another frontier is understanding the warm-hot intergalactic medium, the gas that fills filaments in the regions between structures. This gas contains a large fraction of the universe's baryons but is difficult to detect. It's too hot to form stars, too cool to emit X-rays efficiently, and too diffuse to show up in most observations. Yet it's there, predicted by simulations and detected through subtle absorption signatures in the spectra of distant quasars. Mapping this gas would complete our sensors of matter in the cosmic web, revealing the full extent of the structure, not just the parts traced by galaxies and hot cluster gas. The cosmic web also connects to fundamental questions about the nature of dark matter and dark energy. If dark matter is made of particles, those particles must have properties that allow structure formation to proceed as observed. Too much interaction between dark matter particles, for instance, would smooth out small-scale structure, contradicting observations. Too little, and we might see more small-scale structure than observed. The cosmic web thus constrains dark matter models. Similarly, the growth rate of structure over cosmic time depends on dark energy's properties. If dark energy has evolved over time rather than remaining constant, the cosmic web should show signatures of that evolution. Precision measurements of structure at different epochs can therefore test models of dark energy, turning the cosmic web into a laboratory for fundamental physics. There's something profoundly satisfying about the cosmic web as a concept. It represents order emerging from simplicity. The rules are straightforward. Gravity attracts, space expands, matter responds to both, but the consequences are rich and complex. From nearly uniform initial conditions, the universe constructs an intricate network spanning billions of light years. No intelligence designed it, no plan guided it, yet it has structure, regularity, and beauty. It's a reminder that nature, operating through physical law alone, can create complexity and organization on scales that dwarf human experience. Consider the path that matter took to arrive at its current distribution. In the beginning, in the unimaginably hot and dense state of the early universe, matter and energy were nearly uniform. Quantum fluctuations in the inflation field, tiny, random variations at the quantum scale, were stretched to cosmic sizes by exponential expansion. These fluctuations seeded all subsequent structure. As the universe cooled and expanded, these seeds grew under gravity's patient influence. Dark matter clumped first, forming halos. Gas followed, forming stars and galaxies. Over billions of years, small structures merged into larger ones. Halos joined into groups, groups into clusters, clusters into superclusters connected by filaments, and through it all, space continued expanding, stretching the web to its current vast dimensions. Your own atoms participated in this cosmic journey. The hydrogen in your body was forged in the Big Bang. part of that initial nearly uniform distribution. It spent billions of years flowing through the cosmic web, perhaps falling into a filament, then into a galaxy, then into a molecular cloud, and finally into a star. That star lived and died, returning enriched material to the interstellar medium. The carbon, oxygen, nitrogen, and other heavy elements in your body came from such stellar processing. These atoms drifted through space again, eventually collapsing into a new generation of stars and planets, including our Sun and Earth. You are made of matter that once flowed through the cosmic web, subject to the same gravitational forces, the same expansion, the same grand pattern that organizes the universe on its larger scales. In that sense, we're not separate from the cosmic web. We are part of it. Our galaxy is a node within it. Our local group a small cluster connected to larger structures. The matter we're made of came from it. Our evolution as a species occurred within a galaxy shaped by its location in the web. Everything about our existence is contextual to this structure, embedded in this framework. Understanding the cosmic web is, in part, understanding our own context within the universe, seeing the larger architecture that contains us. As you drift closer to sleep, let this awareness settle. The universe is vast beyond imagining, yet comprehensible. Its largest structures follow from simple principles, played out over enormous spans of time and space. The cosmic web, filaments, clusters, walls, voids, is the natural outcome of gravity, expansion, and initial fluctuations. We live within this structure, embedded in it at every scale, from the atoms in our bodies to the galaxy we inhabit to the supercluster within which that galaxy resides. And perhaps most remarkably, this structure is knowable. Through patient observation, careful measurement, and theoretical insight, we have learned to map the cosmic web, to understand how it formed, to predict how it will evolve. We can run simulations that recreate it. We can measure its properties across billions of light years. We can see it at different ages by looking at different distances. We can connect its largest features to tiny fluctuations in the infant universe. The cosmic web is not forever beyond our grasp. It is something we have come to understand in this brief moment of cosmic history through the application of human curiosity and intelligence. Rest now in this knowledge. The universe has architecture. It has order. It has a structure that connects everything within it into a single coherent whole. And you, small as you are, distant as you are from most of it, are part of that whole, made of its matter, subject to its laws, comprehensible within its context. The cosmic web stretches across the observable universe, vast and mostly invisible, forever expanding, quietly holding everything in its gravitational embrace. Sleep well, knowing that even the largest structures in existence follow patterns we have learned to understand. The next story is about to begin. Please relax and enjoy. Tonight's manifest runs longer than most, not because the cargo is unusual, quite the opposite. It's the sheer volume of sameness that fills these pages, entry after entry of particles so mundane in their behaviour that they barely deserve acknowledgement. Yet here we are, reviewing the logs for one of the universe's most persistent deliveries, neutrinos, the ghost particles that slip through everything as if nothing exists. Imagine a shipping clerk at the end of a long shift, flipping through records of packages that were never signed for, never inspected, never even noticed by their recipients. That's essentially what we're doing here. Neutrinos pass through your body by the billions every second, through the chair you're sitting in, through the floor, through the entire planet, and leave no mark whatsoever. They are the universe's most prolific shipment, yet they interact with so little that most of the manifest might as well be written in invisible ink. Still, on rare occasions, one bumps into something and leaves a signal, and those moments, sparse as they are, have taught us more about the cosmos than you might expect from particles that barely exist. Let's start with what a neutrino actually is, though "is" might be too strong a word for something so insubstantial. A neutrino is a fundamental particle, meaning it's not made of smaller pieces as far as we know. It carries no electric charge, so it doesn't interact with the electromagnetic fields. No pushing, no pulling, no response to magnets or light. Its mass is extraordinarily small, so small that for decades physicists assumed it was zero, and even now that we know better, the exact values remain difficult to pin down. If you could somehow place a neutrino on a scale, you'd find it weighs less than 1/1,000,000th the mass of an electron, which is already nearly nothing compared to everyday objects. There are 3 types, or flavors, of neutrinos, named after the charged particles they're associated with: electron neutrinos, muon neutrinos, and tau neutrinos. Each flavor is defined by the type of lepton it can produce when it interacts via the weak force. Think of them as 3 different kinds of unmarked packages in our shipping metaphor. Same basic packaging, different contents, though even the differences are subtle. They don't respond to the electromagnetic force because they have no charge. They don't feel the strong nuclear force because they're not quarks. They only interact through the weak nuclear force and gravity is so feeble at the particle scale that it's irrelevant. That leaves the weak force as the only interaction channel that matters, and as the name suggests, it's extraordinarily feeble. The weak nuclear force operates over distances smaller than an atomic nucleus. It's the interaction responsible for certain kinds of radioactive decay, like beta decay, where a neutron transforms into a proton and spits out an electron and an antineutrino. The probability of any given neutrino interacting via the weak force in a human-scale distance is vanishingly small. You could line up a light year of solid lead, roughly 6 trillion miles of dense metal, and a neutrino would still have a decent chance of passing through the entire column without hitting anything. This is not because neutrinos are clever or evasive. They simply exist in a realm where the forces that govern everyday matter barely apply. In the shipping log, they're packages that slip through every checkpoint, every security scanner, every inspection station, as if the infrastructure isn't even there. This weakness is both a problem and a feature. It makes neutrinos nearly impossible to detect, requiring enormous specialized equipment and years of patient waiting. But it also means that once a neutrino is created, it can escape from environments that trap everything else. Photons, particles of light, get absorbed and scattered by dense matter. Charged particles are deflected by magnetic fields and stopped by thin layers of material. Neutrinos, on the other hand, sail through stars, planets, and interstellar dust as if none of it exists. This makes them ideal messengers from places we can't see directly, carriers of information from the cores of stars and the hearts of exploding supernovae, regions so dense and opaque that light itself cannot escape until much later. This sun is the most familiar neutrino source, a steady exporter that has been shipping out ghost particles for billions of years. Deep in the solar core, where temperatures reach 15 million degrees and pressures are crushing, hydrogen nuclei fuse into helium through a series of nuclear reactions. These fusion processes are what power the sun, releasing energy that eventually makes its way to the surface and radiates into space as light. But before any of that light escapes, neutrinos are born in the core as byproducts of the reactions that convert protons into neutrons. When 2 protons fuse and one of them transforms via the weak force into a neutron, an electron neutrino is emitted. The neutrino immediately starts moving outward at nearly the speed of light, and because it interacts so weakly, it passes straight through the sun's immense bulk as if the star were hollow. From the sun's perspective, this is a high-volume shipping operation. Every second, the solar core produces about 2 × 10 to the power of 38 neutrinos, a number so large it's almost meaningless to write out. These neutrinos radiate in all directions, spreading through the solar system and beyond. By the time they reach Earth, 8 light minutes away, the flux has thinned out, but it's still enormous. Roughly 65 billion solar neutrinos pass through every square centimetre of your body every second. You don't feel them. They don't heat you or push you or leave any trace. They pass through your atoms, through the spaces between your nuclei and electrons like wind through a chain-link fence, and continue on their way through the planet and out the other side. For decades, this was just a theoretical prediction, a line item on the manifest that hadn't been confirmed. Then, starting in the late 1960s, physicists began trying to detect solar neutrinos directly, to check whether the shipping logs matched the actual deliveries. The first major experiment was led by Raymond Davis Jr., who built a detector deep underground in the Homestake gold mine in South Dakota. The detector was a large tank filled with cleaning fluid, perchloroethylene, a chlorine-rich liquid. The idea was that very occasionally, a solar neutrino would interact with a chlorine nucleus and convert it into a radioactive isotope of argon. After running the experiment for weeks, Davis would purge the argon from the tank and count the atoms to estimate how many neutrinos had interacted. The results were puzzling. Davis detected solar neutrinos, confirming that they were indeed arriving from the Sun, but the count was only about 1/3 of what solar models predicted. This discrepancy became known as the solar neutrino problem, and it persisted for years. The Sun's predicted output and the measured counts did not line up. It looked like the manifest was wrong, or the shipment was incomplete, or something strange was happening in transit. Some physicists wondered if the models of solar fusion were flawed, if the Sun's core was cooler or worked differently than expected. Others suspected the detector was missing something, perhaps only sensitive to certain energies of neutrinos. And a third group began to consider the possibility that the neutrinos themselves were changing somehow between the Sun and Earth. The answer, it turned out, was the third option, though it took decades to confirm. But before we get to that solution, it's worth noting that the Sun is not the only major neutrino source. Supernovae, exploding stars, are the universe's most dramatic neutrino shippers, releasing a staggering burst of ghost particles in a matter of seconds. When a massive star exhausts its nuclear fuel, its core collapses under its own gravity in a fraction of a second, compressing matter to neutron star densities and rebounding in a violent explosion. The energy released in this collapse is almost beyond comprehension, equivalent to the Sun's total output over its entire 10 billion year lifetime, but concentrated into a few moments. Most of this energy, about 99%, is carried away not by light or blast waves but by neutrinos. For a brief window, the collapsing core becomes a neutrino furnace, producing all three flavours in enormous numbers. These neutrinos stream outward through the star's outer layers, racing ahead of the shock wave that will eventually blow the star apart. Because they interact so weakly, they escape immediately, while the light and debris lag behind. In February 1987, a supernova occurred in the Large Magellanic Cloud, a small galaxy neighbouring the Milky Way, about 160,000 light-years from Earth. Supernova 1987A was visible to the naked eye from the southern hemisphere, the brightest supernova in nearly 4 centuries. But before the light reached Earth, the neutrinos arrived. Detectors in Japan and the United States recorded a brief burst of neutrino interactions. Just a handful of events, about 24 in total, spread over a window of about 13 seconds. This might not sound like much, but given the vast distance and the rarity of neutrino interactions, it was an extraordinary confirmation. For those few seconds, the dying star's core was the brightest neutrino source in the sky, and the detectors, sitting quietly underground, logged the arrival. One giant, short-lived entry on the cosmic shipping manifest. Supernovae are rare, at least from our perspective. On average, only a few occur per century in a galaxy like the Milky Way. But the universe has been producing neutrinos from countless sources for billions of years, and many of those sources are local and continuous. Nuclear reactors on Earth, for instance, are prolific neutrino producers. When uranium or plutonium undergoes fission in a reactor core, the resulting fragments are neutron-rich and unstable. They decay via beta decay, converting neutrons into protons and emitting electrons and electron antineutrinos in the process. A typical commercial reactor produces about 10 to the power of 20 antineutrinos per second, a colossal number. These neutrinos stream out of the reactor in all directions, passing through the containment structure, the ground, and anything else nearby without pause. Reactor neutrinos have become valuable tools for experiments, providing a controlled, well-understood neutrino source that can be used to measure properties and test theories. Particle accelerators also contribute to the neutrino traffic. By smashing protons into a target material, physicists can create showers of unstable particles called pions and kaons, which then decay into muons and neutrinos. By carefully tuning the accelerator and focusing the resulting particle beam, researchers can produce intense directed beams of neutrinos with known energies and flavours. These beams can be aimed at detectors hundreds of kilometres away, allowing controlled studies of neutrino behaviour over long distances. It's like setting up a dedicated shipping route between two warehouses, watching how the cargo changes in transit. Even Earth itself contributes to the neutrino background. Radioactive isotopes like uranium, thorium and potassium in the planet's crust and mantle decay slowly over geological timescales, releasing electron antineutrinos as they do. These geoneutrinos provide a faint but constant signal, a reminder that the planet beneath our feet is a dynamic radioactive body, heated in part by the decay of elements left over from the solar system's formation. Geoneutrino detectors can, in principle, map the distribution of radioactive elements inside the Earth, offering a new way to probe the planet's interior. Then there are atmospheric neutrinos, another steady diffuse source. High-energy particles from deep space, cosmic rays, mostly protons, constantly bombard Earth's atmosphere. When a cosmic ray collides with an air molecule, it creates a cascade of secondary particles, including pions and muons. These particles are unstable and decay within microseconds, producing neutrinos. The result is a continuous rain of atmospheric neutrinos coming from all directions, above, below, every angle, as cosmic rays strike the atmosphere from every part of the sky. These neutrinos are a natural background, a global shipment that never stops. They've been useful for studying neutrino properties because their production rates and energy distributions can be calculated and compared with what detectors actually observe. All of these sources contribute to a constant invisible neutrino flux that permeates everything. But detecting even a tiny fraction of this traffic requires extraordinary effort. Because neutrino interactions are so rare, detectors must be enormous and extraordinarily sensitive, and they must operate in environments where other signals, cosmic rays, natural radioactivity, don't overwhelm the faint neutrino events. This is why most neutrino detectors are built deep underground, inside mountains, old mines, or tunnels. The rock overhead acts as a shield, absorbing cosmic rays and other particles that would otherwise create noise in the detector. A kilometre or more of rock is enough to stop nearly all cosmic ray muons, leaving only neutrinos, which pass through the rock as easily as they pass through air. The detector sits in this shielded environment like a microphone in a soundproof room, waiting for the faintest click. Most of the time nothing happens. Hours, days, weeks pass with no signal. Then, very occasionally, a neutrino interacts with a particle inside the detector, and a brief tiny signal appears. That signal is logged, time-stamped, analysed, and added to the manifest. One common type of detector is the Cherenkov detector, which uses large volumes of water or ice to catch neutrinos. The principle is elegant. When a neutrino interacts with a nucleus in the water, say an oxygen nucleus, it can produce a charged particle, such as an electron or a muon, depending on the neutrino's flavour. If that charged particle is moving fast enough, it travels through the water faster than light can travel in water. This doesn't violate relativity. Light in a vacuum is still the universal speed limit, but in a medium like water, light is slowed down by interactions with the molecules. A charged particle, under the right conditions, can outrun this slowed light, and when it does, it produces a cone of faint blue light called Cherenkov radiation. It's the optical equivalent of a sonic boom. Arrays of sensitive light detectors, photomultiplier tubes, line the walls of the tank or are embedded in the ice. When Cherenkov light is produced, the sensors pick it up, recording the pattern, timing, and intensity of the flashes. From this information, scientists can reconstruct the direction and energy of the original neutrino, even though the neutrino itself left no direct trace. The neutrino is invisible, only its aftermath is seen. Most of the time, the tank sits dark and silent like a warehouse with no deliveries. Then, perhaps once a day or once a week, a single flash appears, a confirmed arrival logged in the system. One of the most famous Cherenkov detectors is Super Kamiokande in Japan, a cylindrical tank holding 50,000 tons of ultra-pure water, located a kilometre underground beneath Mount Akingno. Its walls are lined with over 11,000 photomultiplier tubes, sensitive enough to detect the faint glow of a single Cherenkov cone. Super Kamiokande has been running since the mid-90s, accumulating neutrino events from the sun, from the atmosphere, and from particle accelerator beams. It played a crucial role in solving the solar neutrino problem, and in establishing that neutrinos have mass, discoveries that earned the Nobel Prize in Physics. Another type of detector uses liquid scintillator instead of water. Scintillator is a material that emits light when energy is deposited in it. When a neutrino interacts inside the scintillator, the resulting particles lose energy as they move, exciting the scintillator molecules and producing a brief flash of light. This flash is detected by photomultiplier tubes surrounding the liquid. Scintillator detectors are often used for lower energy neutrinos, such as those from nuclear reactors or the sun, because the light output is more efficient and easier to detect than Cherenkov light at low energies. The principle is the same: wait in a quiet, shielded environment, and occasionally a flash confirms that a neutrino interacted. Each flash is a time-stamped entry in the log. With all this infrastructure in place, massive detectors, years of data collection, careful analysis, physicists have gradually filled in the details of the neutrino manifest. One of the most important entries concerns the three flavors: electron, muon, and tau neutrinos. These flavors are defined by the charged leptons they produce in weak interactions. An electron neutrino, when it interacts, tends to produce an electron. A muon neutrino produces a muon, a heavier cousin of the electron. A 2 neutrino produces a tau lepton, heavier still and very short-lived. At production, neutrinos are typically born as one specific flavor. Solar fusion produces electron neutrinos. Pion decay in the atmosphere produces mostly muon neutrinos. Experiments are designed to identify flavors by looking at the type of particle produced in the detector, checking not just how many packages arrive, but what labels they carry. Here's where the story takes an unexpected turn. As neutrinos travel, they can change from one flavor to another. This phenomenon is called neutrino oscillation, and it's the key to understanding the solar neutrino problem and much more. Imagine a shipment of packages leaving a warehouse, all labelled as Type A. Somewhere in transit, without any external interference, some of those packages spontaneously change their labels to Type B or Type C. When the shipment arrives, you count far fewer Type A packages than expected, not because any were lost, but because they transformed along the way. This is what happens to neutrinos. They don't disappear, they oscillate between flavors as they propagate through space. Neutrino oscillation arises from quantum mechanics. The flavor states, electron, muon, tau, are not the same as the mass states, the states with definite mass. Instead, each flavor is a quantum mixture of different mass states. When a neutrino is produced in a particular flavor, it's actually a superposition of 2 or more mass states with slightly different masses. As the neutrino travels, these mass states propagate at slightly different rates because they have different energies and their quantum phases shift relative to one another. Over time and distance, this interference can cause the original flavor to evolve into a different flavor. The probability of finding the neutrino in a particular flavor oscillates as a function of distance and energy, following a pattern determined by the differences in neutrino masses and the mixing angles between states. This has profound implications. For one thing, it means neutrinos must have non-zero mass. If all neutrinos were massless, there would be no mass differences, no interference, and no oscillations. The discovery of neutrino oscillations was therefore also the discovery that neutrinos have mass, something the original standard model of particle physics didn't account for. It required an update to the model, adding new parameters, the neutrino masses, or at least the differences between their squares, which is what oscillations measure, and the mixing angles that describe how the flavors blend. Neutrino oscillations solve the solar neutrino problem. Raymond Davis's detector was primarily sensitive to electron neutrinos, the flavor produced in the Sun. But as those electron neutrinos travelled the 93 million miles from the Sun's core to Earth, a large fraction oscillated into muon or tau neutrinos. Davis's detector couldn't see those other flavors, so it only counted the electron neutrinos that hadn't yet transformed. The missing neutrinos weren't missing at all. They were just wearing different labels. Later experiments, like the Sudbury Neutrino Observatory in Canada, were designed to detect all 3 flavors and confirmed that the total number of neutrinos matched predictions once all flavors were counted. The manifest was correct after all. The inventory system just needed an update. Atmospheric neutrinos provided further evidence. When physicists compared the number of muon neutrinos and electron neutrinos arriving from cosmic ray interactions overhead, they found fewer muon neutrinos than expected, especially those travelling long distances through the Earth from the opposite side of the planet. This deficit was also explained by oscillations. Muon neutrinos were transforming into tau neutrinos as they travelled, and the detectors couldn't identify tau neutrinos easily. The pattern of deficit as a function of distance fit the oscillation predictions beautifully, providing strong confirmation of the phenomenon. To study oscillations in detail, physicists built long baseline experiments, where a beam of neutrinos is produced at a particle accelerator and aimed at a detector hundreds of kilometers away. One example is the T2K experiment in Japan, which sends a beam of muon neutrinos from the J-Park Accelerator Complex on the east coast to the Super Kamiokande detector on the west coast, a distance of about 295 kilometers. By comparing the flavors and energies of neutrinos at the source and at the detector, scientists can measure how much oscillation occurred. These experiments are painstaking, running for years to accumulate enough events to map out the oscillation parameters with precision. It's like tracking how a shipment's composition changes between two warehouses, watching the labels shift in transit, and using that information to infer the properties of the packages themselves. The parameters measured by these experiments, mixing angles, mass-squared differences, are now well-established entries in the neutrino section of the particle physics databook. There are 3 mixing angles, usually labelled theta 1,2, theta 2,3, and theta 1,3, which describe how much the different mass states contribute to each flavour. There are 2 independent mass-squared differences, typically called delta m squared 21 and delta m squared 31, which quantify the tiny differences in neutrino masses. These numbers are small, but they've been measured with increasing precision over the past 2 decades, gradually filling in the blank fields on the manifest. Neutrinos are valuable not just for their intrinsic physics, but because they can probe environments that are otherwise inaccessible. Photons, the particles of light, are absorbed and scattered by dense matter, magnetic fields, and dust. By the time light from the sun reaches us, it has been jostled and redirected countless times, emerging from the sun's surface with almost no memory of its origin deep in the core. Neutrinos, on the other hand, escape immediately. They carry direct information about the fusion reactions happening in the solar core right now, not the average conditions over thousands of years of photon diffusion. Similarly, neutrinos from a supernova core can tell us about the conditions during collapse, the temperatures, densities, and dynamics of the innermost regions, information that light cannot provide because it's trapped in the explosion for hours or days. This ability to escape dense environments makes neutrinos priority messengers in the shipping metaphor. They're not carrying bulk cargo, they're carrying information tagged with energy and direction from places we can't see with ordinary telescopes. When a neutrino detector records an event, it's not just logging a particle interaction, it's recording a data packet from deep inside a star, from a supernova core, or from some other hidden process. In recent years, neutrino astronomy has expanded to cosmic scales. High-energy neutrinos with energies millions or billions of times higher than those from the Sun occasionally arrive at Earth from distant astrophysical sources. IceCube, a neutrino observatory buried in the Antarctic ice, has detected several of these ultra-high-energy neutrinos. IceCube consists of over 5,000 optical sensors deployed on strings drilled deep into the ice, covering a cubic kilometre of volume. When a high-energy neutrino interacts in or near the detector, it produces a long track of Cherenkov light, bright enough to be seen across large distances in the clear ice. By analysing the pattern of hits, scientists can determine the neutrino's direction and energy. Some of these cosmic neutrinos have been traced back to known astrophysical objects, such as blazars, active galaxies with jets of matter shooting out at nearly the speed of light. These extreme environments are thought to accelerate particles to immense energies, and neutrinos are produced as byproducts of those acceleration processes. Each detected cosmic neutrino is rare. IceCube sees only a handful per year at the highest energies, but they open a new window on the universe, a way to observe the most violent and energetic processes in nature. In the manifest, they appear as special deliveries from the deep cosmos, tagged with energy and direction, each one a clue to understanding phenomena we can't study any other way. Despite decades of progress, there are still blank fields in the neutrino manifest, questions that remain unanswered. One concerns the ordering of the neutrino masses. We know there are 3 mass states, and we know the differences between their squared masses, but we don't know the absolute values, or the ordering. Is the lightest neutrino the one that mixes most with the electron neutrino, or is it one of the others? This is called the mass hierarchy problem, normal hierarchy versus inverted hierarchy, and experiments are working to resolve it by measuring subtle differences in oscillation patterns. Another open question is whether neutrinos violate CP symmetry, a fundamental symmetry of physics that relates particles to their antiparticles and flips spatial coordinates. If neutrinos do violate CP symmetry, it could help explain why the universe contains more matter than antimatter, one of the great mysteries in cosmology. Current and future long baseline experiments are designed to search for CP violation by comparing oscillations of neutrinos and antineutrinos, looking for differences that would signal a CP asymmetry. Then there's the question of whether neutrinos are their own antiparticles. Most particles have distinct antiparticles. The electron has the positron, the proton has the antiproton. But neutrinos are neutral, and it's possible, though not certain, that a neutrino and its antineutrino are actually the same particle. If this is true, it would allow a rare process called neutrinoless double beta decay, where a nucleus emits 2 electrons and no neutrinos. Detecting this process would confirm that neutrinos are their own antiparticles, a property called being a Majorana fermion. Experiments are searching for this rare decay, sitting quietly underground, waiting for a signal that might not come for years or decades. Each of these unanswered questions represents a blank field in the shipping manifest, a line labelled but not yet filled in. The data trickles in slowly, event by event, as detectors around the world continue their long, patient vigil. While you rest tonight, neutrinos continue their silent passage. Solar neutrinos stream through your body at a rate of billions per second, most of them passing through the entire planet without slowing. Atmospheric neutrinos rain down from cosmic ray interactions in the sky above and below, a diffuse shower from all directions. Geoneutrinos drift up from the Earth's crust and mantle, carrying traces of radioactive decay from elements forged in ancient supernovae. Reactor neutrinos fan out from power plants scattered across the continents, a local background hum. And every so often, a high-energy neutrino from a distant galaxy slams into the Antarctic ice or the deep ocean, leaving a brief flash of Cherenkov light that sensors capture and log. Almost all of these neutrinos pass through without leaving a trace. They are the universe's quietest cargo, a constant invisible flow that has persisted for billions of years, since the first stars began fusing hydrogen and the first supernovae exploded. Detectors sit deep underground in mines, beneath mountains, buried in ice, waiting in darkness for the occasional interaction, the rare moment when a neutrino nudges a nucleus and produces a signal. Most shifts are empty. Hours pass with nothing. Then a single flash, a single event is recorded, time-stamped, and added to the manifest. Over years, these sparse entries accumulate into a dataset, a catalogue of arrivals that reveals patterns, oscillations, energy spectra, directional distributions, all the subtle features that tell us about the neutrinos themselves and the sources that produce them. The manifest is never complete. There are always more events to record, more parameters to measure, more questions to answer. But from this long, boring log of invisible deliveries, we've learned that the sun's core is powered by fusion as predicted, that neutrinos have mass and oscillate between flavors, that supernova cores release nearly all their energy in neutrinos, and that the universe is filled with neutrinos from countless sources, a background radiation of ghost particles that permeates everything. We've confirmed that the weak force operates exactly as quantum field theory describes, and we've opened a new channel of astronomy, one that doesn't rely on light but on particles that interact so rarely they can carry information from the most hidden corners of the cosmos. Tonight's manifest is closed. The neutrinos will keep flowing, most of them unnoticed, a steady stream of nearly nothing passing through everything. The detectors will keep watching, logging the rare exceptions, the moments when something almost invisible leaves the faintest mark, and from that sparse record we'll continue filling in the details, one time-stamped event at a time, gradually assembling a picture of the universe's quietest, most persistent shipment. The peculiar thing about neutrinos, when you sit with the idea long enough, is how they reframe what we mean by substance. We walk through the world assuming that matter is, in some fundamental sense, solid, that the chair supports you because its atoms are genuinely there, occupying space, repelling your atoms through electromagnetic forces, and this is true as far as everyday experience goes, but neutrinos remind us that being there is a matter of which forces you respond to. To a neutrino, your body isn't there at all. The electromagnetic forces that make you feel solid, that give you shape and texture and weight, are completely irrelevant to a particle with no charge. From the neutrino's perspective, you're a ghost, and it's the only real thing, passing through a universe of phantoms. This inverts our usual sense of what's substantial. We think of ourselves as the solid objects and neutrinos as the insubstantial wisps, but the truth is more symmetrical. Solidity is a relationship, not an intrinsic property. You feel solid to other electrically charged matter. Neutrinos feel solid, or at least present, only to the weak force, and the weak force barely notices them. In a very real sense, neutrinos and ordinary matter inhabit overlapping but separate worlds, two populations passing through the same space but rarely acknowledging each other's existence. The shipping manifest logs the rare moments when those worlds intersect, when the boundary between them becomes briefly permeable and a signal passes from one to the other. Consider the numbers again, because they're worth sitting with. 65 billion solar neutrinos pass through every square centimetre of your body every second. Your body has a surface area of roughly 2 square metres, or 20,000 square centimetres. That means about 1.3 trillion solar neutrinos pass through you every second. Over the course of a day, that's over 100 quadrillion neutrinos. In a year, it's tens of quintillions. Over a human lifetime of 80 years, the total number of solar neutrinos that pass through your body is a number with 27 digits, a quantity so large it loses meaning. And that's just from the Sun. Add in atmospheric neutrinos, geoneutrinos, reactor neutrinos, and the diffuse background of relic neutrinos left over from the Big Bang. Yes, those exist too, though they're even harder to detect, and the total flux is even more staggering. Yet in your entire lifetime, the probability that even one of those neutrinos will interact with an atom in your body is extremely small. The human body contains roughly 28 trillion cells, each with billions of atoms, for a total of about 7 times 10 to the power of 27 atoms. That sounds like a lot, and it is. But the interaction cross-section for a solar neutrino with an atom is so tiny that even with all those atoms, the chances of a single interaction are close to zero. You could live 1,000 lifetimes and never have a neutrino interaction inside your body that produced a detectable signal. The particles pass through you like you're not there, and from their perspective, you're not. This is why neutrino detectors must be so large. To catch even a handful of interactions per day, you need thousands of tons of material, water, ice, scintillator, whatever the detector uses, and even then the event rate is measured in single digits. Super Kamiokande, with its 50,000 tons of water, detects about 10 to 15 solar neutrino interactions per day. That's out of roughly 10 to the power of 39 solar neutrinos passing through the detector every second. The odds are something like 1 in 10 to the power of 23. It's not quite looking for a needle in a haystack. It's more like waiting for a needle to spontaneously appear in a haystack and then disappear again before you can grab it, leaving only a faint shimmer in the air to confirm it was ever there. The patience required for neutrino physics is immense. Experiments run for years, sometimes decades, accumulating data event by event. The Homestake experiment, Raymond Davis's pioneering solar neutrino detector, ran from 1967 to 1994, 27 years of continuous operation. Every few weeks, Davis and his team would extract the argon atoms produced by neutrino interactions, count them, and record the number. The total count over nearly 3 decades was only about 2,000 argon atoms, an average of 1 every few days. Each atom represented a single neutrino interaction, a single confirmed delivery. The entire dataset that revealed the solar neutrino problem and hinted at neutrino oscillations fit on a few pages of paper. The manifest was sparse, but it was enough. This patience extends to the analysis as well. When a detector records an event, it's not immediately obvious what happened. The data is a pattern of light flashes in photomultiplier tubes, or a sequence of charge deposits in electronics, or some other indirect signature. Physicists must reconstruct the event, using simulations and models to infer what kind of particle interaction could have produced that particular pattern. Was it a neutrino, or was it background radiation, a cosmic ray that slipped through the shielding, a spontaneous decay of some trace radioactive contaminant in the detector? Each event must be scrutinized, classified, and either accepted as a likely neutrino or rejected as something else. The process is meticulous and statistical. You never know for certain that any individual event was a neutrino. You can only say that the ensemble of events taken together is consistent with neutrino interactions and inconsistent with background alone. The manifest is built from probabilities and patterns, not certainties. Yet despite these challenges, the accumulated data has painted a remarkably detailed picture of neutrino behavior. The mixing angles that describe neutrino oscillations are now known to within a few percent. Theta 1-2, the angle that governs solar neutrino oscillations, has been measured precisely by experiments like SNO and Borac-Xeno. Theta 23, which dominates atmospheric oscillations, is known from Super Kamiokande and long baseline experiments like T2K and NOVA. Theta 13, the smallest of the three angles and the last to be measured, was pinned down in 2012 by reactor experiments like Daya Bay, which detected the disappearance of electron antineutrinos from nuclear reactors. Each of these measurements required years of data collection, thousands of events, careful background subtraction, and systematic uncertainty analysis. But now they're part of the standard reference tables, printed in textbooks, treated as established facts. The mass squared differences are similarly well measured. Delta M squared 21, which affects solar and long baseline oscillations, is about 7.5 times 10 to the minus 5 electron volts squared. Delta M squared 31, relevant for atmospheric oscillations, is about 2.5 times 10 to the minus 3 electron volts squared. These numbers are absurdly small in everyday units, but they're precisely what's needed to explain the oscillation patterns observed across different experiments and energy scales. They're also small enough that even after decades of measurement, we still don't know the absolute masses of the neutrinos, only the differences between the squares of the masses. If you think of the masses as three numbers on a number line, we know the spacings between them, but not where the whole set sits on the line. That's the mass hierarchy problem. We don't know if the pattern goes light medium heavy or light heavy medium, or some other ordering. This might seem like an obscure detail, but it matters for cosmology. Neutrinos were produced in vast numbers in the early universe, during the first second after the Big Bang, when the cosmos was hot and dense enough for weak interactions to occur frequently. As the universe expanded and cooled, these primordial neutrinos decoupled from other matter and have been streaming freely through space ever since, now cooled to a temperature of about 2 Kelvin, just slightly above absolute zero. These relic neutrinos, sometimes called the cosmic neutrino background, are predicted to exist in enormous numbers, about 330 per cubic centimetre on average, filling the universe as thoroughly as the cosmic microwave background radiation. But because they're so cold, their energies are far too low to detect with current technology. No experiment has ever directly observed a relic neutrino. Still, their existence affects cosmology indirectly. Neutrinos have mass, so they contribute to the total mass energy budget of the universe. They also move at nearly the speed of light, even today, which makes them hot dark matter, a component that was relativistic during the era of structure formation. Hot dark matter doesn't clump efficiently under gravity on small scales, because the particles are moving too fast. They smooth out small-scale density fluctuations. This means the abundance and masses of neutrinos affect how galaxies and clusters formed. By studying the large-scale structure of the universe, the distribution of galaxies, and the patterns in the cosmic microwave background, cosmologists can infer constraints on the sum of neutrino masses. Current data suggests the sum is less than about 1/10 of an electron volt, which means each individual neutrino mass must be less than a few hundredths of an electron volt. This is a cosmological measurement of particle physics, a way of weighing neutrinos by looking at the largest structures in the universe. It's an entry in the manifest filled in not by a detector deep underground, but by surveys mapping billions of galaxies across cosmic time. The interplay between neutrino physics and cosmology goes even deeper. One of the great mysteries of cosmology is why the universe contains matter, but almost no antimatter. According to the known laws of physics, the Big Bang should have produced matter and antimatter in equal amounts, and they should have annihilated each other, leaving behind only radiation. Yet here we are, living in a universe made of matter. Protons, neutrons, electrons, with antimatter only appearing fleetingly in particle collisions or cosmic ray interactions. Something must have tipped the balance, creating a small asymmetry between matter and antimatter in the early universe, enough that a tiny fraction of matter survived the annihilation and went on to form stars, planets, and people. One possible explanation involves CP violation, the phenomenon where the laws of physics treat particles and antiparticles slightly differently. CP violation has been observed in quarks, but the amount is too small to explain the matter, antimatter asymmetry. Neutrinos, however, might exhibit much larger CP violation, enough to account for the imbalance. If neutrinos and antineutrinos oscillate differently, if, for example, the probability of an electron neutrino turning into a muon neutrino is different from the probability of an electron antineutrino turning into a muon antineutrino. It could signal CP violation. Current long baseline experiments are searching for exactly this difference, comparing neutrino and antineutrino beams to look for asymmetries. The results so far hint at possible CP violation, but the uncertainties are still too large to be certain. Future experiments with more intense beams and larger detectors will refine the measurements and may finally determine whether neutrinos hold the key to why we exist. Then there's the question of Majorana versus Dirac neutrinos, another blank field on the manifest. For most particles, there's a clear distinction between particle and antiparticle. An electron has negative charge, a positron has positive charge. A proton is made of up and down quarks, an antiproton is made of up and down antiquarks. But neutrinos are electrically neutral, and their interactions are so rare that it's difficult to distinguish a neutrino from an antineutrino by direct observation. It's possible that neutrinos are their own antiparticles, a type of particle called a Majorana fermion. If this is true, it would have profound implications for the theory of mass, and might even explain why neutrino masses are so much smaller than other particle masses. The way to test this is to look for neutrinoless double beta decay, a process where a nucleus emits 2 electrons and nothing else. No neutrinos. Ordinary double beta decay, where 2 neutrons in a nucleus simultaneously convert to protons, emitting 2 electrons and 2 antineutrinos, is rare but has been observed. Neutrinoless double beta decay, where the 2 neutrinos somehow cancel each other out internally, is even rarer and has never been confirmed. If it exists, it would mean a neutrino and an antineutrino, both virtual particles produced inside the nucleus, met and annihilated, confirming they're the same particle. Experiments like Gerda, Quarre, and EXO are searching for this process using isotopes like germanium-76, tellurium-130, and xenon-136, which could in principle undergo neutrinoless double beta decay. These experiments sit in underground labs, surrounded by layers of shielding to block background radiation, and measure the energy of electrons emitted from decays. If neutrinoless double beta decay occurs, it would produce a distinctive spike in the energy spectrum at a very specific value. So far, no confirmed signal has been seen, but the experiments continue, slowly accumulating data, tightening the constraints, waiting for a delivery that may or may not come. All of this, oscillations, mass hierarchies, CP violation, Majorana versus Dirac, might sound esoteric, but it's part of a larger effort to understand the fundamental rules of the universe. Neutrinos are messengers not just from distant astrophysical sources, but from the underlying structure of physical law. The standard model of particle physics, which describes all known particles and their interactions, has been spectacularly successful, predicting phenomena that were later confirmed to extraordinary precision. But it's also incomplete. It doesn't explain why neutrinos have mass, or why their masses are so much smaller than those of quarks and leptons. It doesn't account for dark matter, the invisible substance that makes up most of the matter in the universe. It doesn't explain the matter-antimatter asymmetry, and it doesn't incorporate gravity in a quantum framework. Neutrinos sit at the boundary of these open questions. Their masses suggest physics beyond the standard model, perhaps involving new particles or interactions at energies far higher than we can reach with accelerators. Their oscillations probe the structure of flavor and mass in ways that might reveal deeper symmetries. Their possible role in the matter-antimatter asymmetry connects particle physics to cosmology. And their status as the only fermions that might be Majorana particles hints at new principles in the theory of mass. In the shipping manifest, neutrinos are entries that don't quite fit the standard categories, anomalies that point toward extensions of the catalogue, new sections that haven't been written yet. The cosmic neutrino sources extend beyond the familiar ones. In addition to the Sun, supernovae, reactors, and the atmosphere, there are likely neutrinos produced in the jets of active galactic nuclei, powered by supermassive black holes accreting matter at the centres of galaxies. There may be neutrinos from gamma-ray bursts, the most luminous explosions in the universe, which occur when massive stars collapse into black holes or when neutron stars merge. There could be neutrinos from dark matter annihilation or decay if dark matter particles occasionally destroy each other and produce standard model particles, including neutrinos. Each of these sources is speculative or only partially confirmed, but they represent potential entries in the cosmic shipping manifest, deliveries we haven't fully logged yet. IceCube's detection of high-energy neutrinos has opened this new frontier. In 2013, the collaboration announced the discovery of 2 neutrino events with energies above 1 peta-electronvolt, more than 1,000,000 times the energy of a proton at rest. These were clearly not atmospheric neutrinos, which don't reach such high energies. They had to come from cosmic sources, from processes involving particle acceleration far more powerful than anything on Earth. Since then, IceCube has detected dozens more high-energy neutrinos, building up a catalogue of cosmic events. A few have been traced back to candidate sources, like the Blazar TXS 0506+056, which was in an active flaring state when a neutrino from its direction arrived. This was the first time a high-energy neutrino was associated with a specific astrophysical object, a milestone in multi-messenger astronomy, the practice of observing cosmic events using multiple types of signals: light, gravitational waves, and now neutrinos. Multi-messenger astronomy is transforming how we study the universe. Gravitational waves, detected by LIGO and Virgo, reveal the collisions of black holes and neutron stars. Electromagnetic telescopes observe the light from these events across the spectrum, from radio waves to gamma rays. Neutrinos add another dimension, probing the densest, most opaque regions where light cannot escape. In 2017, when LIGO detected gravitational waves from a neutron star merger, and telescopes observed the resulting kilonova explosion, neutrino detectors were also watching, hoping to catch neutrinos from the event. None were detected. The source was either too far away or didn't produce many neutrinos. But the effort demonstrated the readiness of the neutrino network. Future events may produce detectable neutrino signals, adding another line to the manifest, another piece of the puzzle. The vision for the next generation of neutrino detectors is even more ambitious. Plans are underway for massive upgrades and new facilities. Hyper Kamiokande, a successor to Super Kamiokande, will hold about 260,000 tons of water, more than 5 times larger, with improved photosensors. The Deep Underground Neutrino Experiment, or DUNE, will place enormous liquid argon detectors a mile underground in South Dakota, receiving neutrino beams from Fermilab in Illinois, over 800 miles away. The longer baseline and larger detectors will measure oscillation parameters with unprecedented precision, potentially resolving the mass hierarchy and discovering CP violation if it exists. In Antarctica, plans for IceCube Gen 2 envision expanding the detector to encompass about 8 cubic kilometers of ice, improving sensitivity to cosmic neutrinos and allowing more detailed studies of high-energy sources. These future experiments will add thousands of new entries to the manifest, refining the parameters, discovering new sources, and perhaps revealing surprises we haven't anticipated. Because that's one of the lessons of neutrino physics: expect the unexpected. The solar neutrino problem was unexpected. Neutrino oscillations were unexpected, or at least not predicted by the original standard model. The fact that neutrinos have mass at all was unexpected. Each surprise led to new insights, new questions, and ultimately a richer understanding of the universe. The manifest is never just a list of confirmed deliveries, it's a record of anomalies and patterns that challenge our assumptions and point toward deeper truths. Meanwhile, the neutrinos keep coming, indifferent to our efforts to catch them. They stream from the sun, from dying stars, from cosmic accelerators at the edge of the observable universe. They pass through planets, through stars, through galaxies, as if none of it matters. In a sense, they're the ultimate travellers, unimpeded by the structure of the cosmos, moving from source to detector in nearly straight lines, carrying their messages intact. They don't care about magnetic fields, dust clouds, intervening matter, or the expansion of space. They simply propagate, quantum mechanical wave packets spreading and oscillating, until occasionally, by chance, one interacts and delivers its payload. And when that happens, when a neutrino nudges a nucleus in a detector, producing a flash of light or a charged particle, it's a moment of contact between two realms. The neutrino, which has travelled for 8 minutes from the sun's core, or 160,000 years from a supernova, or billions of years from a distant galaxy, finally touches ordinary matter and leaves a mark. The detector records the event, a timestamp, an energy, a direction, a flavour if it can be determined. The data is stored, analysed, published. Another line is added to the manifest, and the long, quiet work of understanding continues, one invisible delivery at a time. The next story is about to begin. Please relax and enjoy. Tonight's case file sits on the desk, a manila folder labelled gravastars, theoretical alternative to black holes, status, speculative. There's no urgency here, no cosmic catastrophe waiting to unfold, just a quiet review of what happens when physicists take the standard model of an ultra-dense object and ask, very politely, whether there might be another way to build something that looks almost the same from the outside, but avoids certain mathematical difficulties on the inside. Black holes work extraordinarily well as models. They match observations, they emerge naturally from Einstein's equations, and they've become the default answer when astronomers spot something extremely massive and compact. But in the filing cabinets of theoretical physics, there's always room for a backup design, a secondary blueprint that addresses some of the lingering discomforts that show up in the margins of the standard story. Gravastars occupy that space. Not a replacement, not a revolution, just an alternative sketch that some researchers find worth keeping around. Before opening the Gravastar folder, it helps to recall what the baseline model looks like. A black hole, in the language of general relativity, is what you get when matter collapses so thoroughly that it warps space-time into a configuration with two defining features. First, there's the event horizon, a boundary in space-time that marks the point of no return. Outside the horizon, you can still escape if you fire your rocket engines hard enough. Cross the horizon going inward, though, and every possible future trajectory points further inward. Light itself cannot escape, not because it lacks speed, but because the geometry of space-time has been bent into a shape where outward simply ceases to exist as a direction once you're inside. Second, there's the singularity at the centre, a region where the equations predict that density, curvature and tidal forces all climb to infinity. From far away, none of this internal drama is directly visible. The outside universe sees only a simple object characterised by three numbers: mass, spin and electric charge. No hair, as the physicists say, meaning no other details stick out. This simplicity is part of what makes black holes so mathematically elegant and observationally successful. Yet simplicity has its costs. The singularity is one of them. When a mathematical model predicts an infinity, physicists often interpret this as a sign that the model is reaching the edge of its applicability, like a map that labels a distant region with "Here be dragons," because the cartographer ran out of reliable information. General relativity is a classical theory, meaning it doesn't incorporate quantum mechanics, and most researchers expect that quantum effects become important at the extreme densities near a singularity. Perhaps the true picture involves quantum gravity, a framework that no one has fully worked out yet, which would smooth over the singularity into something less pathological. But in the classical black hole model, the singularity is there, sitting in the equations like an error flag. Then there's the information paradox, a subtler headache. Quantum mechanics insist that information about the state of a physical system should be preserved as the system evolves. You might scramble the information, spread it out, hide it in correlations, but you shouldn't be able to destroy it completely. Black holes, at least in their classical form, seem to violate this principle. Matter falls past the horizon, carrying detailed information about its quantum state. That information becomes inaccessible to external observers. Worse, when you add quantum field theory to the picture, black holes can evaporate through Hawking radiation, a slow leak of particles that carries away energy and eventually leaves nothing behind. If that radiation is completely thermal and random, as it appears to be, then the detailed information about what fell in seems to have vanished. Some progress has been made on this puzzle in recent years, especially through ideas about how information might be encoded in subtle correlations in the radiation, but the question is not fully settled. For decades, this tension has motivated some physicists to wonder whether the classical black hole picture might need modification, or whether there might be objects that look like black holes from the outside but have a different internal structure that avoids an event horizon altogether. Enter the folder labelled Exotic Compact Objects. This is a collection of theoretical proposals for things that are almost as dense and compact as black holes, but differ in key ways. The idea is to find configurations that can form from gravitational collapse, or other processes, that have strong gravitational fields that would be hard to distinguish from black holes in most observations. but that sidestepped the singularity and perhaps the horizon as well. Gravastars are one entry in this folder. Alongside them are boson stars, hypothetical objects held up by the quantum pressure of scalar fields instead of by ordinary matter, fuzzballs, a string theory proposal where the horizon is replaced by a massive tangle of strings and brains, and various other speculative designs. None of these alternatives have been confirmed by observation, and many face theoretical challenges of their own, but they serve a purpose. They map out the space of what might be possible, and they provide benchmarks against which to test the black hole model. If you only ever consider one possibility, you might miss a subtle signal that the universe is doing something more interesting. Gravastars, short for gravitational vacuum stars, are built around a specific architectural idea. Instead of letting collapse proceed all the way to a singularity and form an event horizon, you halt the process just shy of that point and create a three-layered structure. On the very outside, space-time looks essentially the same as it would around a black hole of the same mass. The gravitational field, the orbits of nearby objects, the bending of light, all of these match the black hole solution almost perfectly. But as you move inward toward where the event horizon would be, you encounter something different. A very thin, extremely dense shell of matter or exotic energy. This shell is not made of ordinary atomic matter in any conventional sense. It's a surface layer that carries enormous energy density compressed into a narrow radial range. Inside this shell, the core of the gravastar is not a singularity, not even ordinary matter. Instead, it's filled with something that behaves like a vacuum with repulsive properties, similar in some ways to the dark energy that drives the accelerated expansion of the universe. This interior region exerts outward pressure, counterbalancing the inward pull of gravity on the shell, and the whole configuration is designed to be stable without ever forming a horizon or a singularity. The interior of a gravastar deserves a closer look. In many of the proposed models, the core is characterized by an equation of state where the pressure is large and negative, or where the energy density corresponds to something like a cosmological constant confined to a small region. This is not a gas of particles in the usual sense, not a fluid sloshing around. It's a state of space-time and fields that produces a kind of tension, an outward push. The mathematics comes from solutions to Einstein's field equations, where the stress-energy tensor has unusual properties. If you imagine the universe's dark energy as a diffuse component spread across all of space, the gravastar's interior is a localized pocket of something with similar properties, but much more intense and confined. The equations describe a smooth, static geometry inside the shell, one where space-time is curved but not catastrophically so, and where there are no singularities hiding anywhere. The shell that wraps around this vacuum-like core is where most of the action is, at least from a structural point of view. This shell must be thin, often modelled as having a thickness that is a tiny fraction of the overall size of the object, but it must also carry almost all of the mass that an outside observer would attribute to the gravastar. It's the transition layer between the interior vacuum-like region and the exterior gravitational field. In the mathematical description, you match the interior solution and the exterior solution across this shell by demanding that certain quantities, like the curvature and the energy content, change in a consistent way. The shell has to have very specific properties to make this matching work. Its equation of state, the relationship between its pressure and energy density, is constrained by the requirement that the configuration be stable and that it produce the right external gravitational field. In some models, the shell might involve exotic matter, meaning matter with an equation of state that doesn't correspond to any known particles or fields. In other models, it might involve phase transitions in space-time itself, or quantum effects that become important at these extreme densities. The details vary from one gravastar proposal to another, but the common thread is that this thin layer does the heavy lifting, literally and figuratively, in holding the structure together. From the perspective of a distant observer, a gravastar and a black hole of the same mass would appear nearly identical. The exterior space-time geometry is described by the Schwarzschild solution, or, if the object is spinning, the Kerr solution, both of which are the standard geometries for black holes. This means that if you're orbiting the object at a safe distance, you can't tell which one it is just by measuring the gravitational field. The orbital periods, the precession of elliptical orbits, the deflection of starlight passing nearby, all of these are determined by the mass and spin, not by the internal structure. To someone mapping the gravitational landscape from afar, the file labelled gravastar and the file labelled black hole contain nearly identical data. The differences only show up when you zoom in very close to the would-be horizon, where the presence of a surface, the shell, instead of a horizon might lead to subtle, observable effects. How might such an object form in the first place? The standard story for black holes is straightforward. A massive star exhausts its nuclear fuel, the pressure supporting it against gravity disappears, and the core collapses. If the core is massive enough, nothing can stop the collapse, and it proceeds to form a singularity and an event horizon. The gravastar story has to diverge from this script at some point during the collapse. One proposal is that as the collapsing matter approaches densities and curvatures where quantum gravitational effects become important, something happens that halts the collapse just before a horizon forms. Perhaps there's a phase transition, a sudden change in the state of the matter or space-time that converts the interior into the vacuum-like phase, while pushing the remaining mass energy outward into the thin shell. Alternatively, quantum vacuum fluctuations or modifications to the equations of general relativity at very high curvature might provide a repulsive force that stops the collapse. The specifics are murky because we don't have a complete theory of quantum gravity to guide us. What's clear is that the formation of a gravastar requires something to intervene in the collapse process at a very precise moment, which makes it a more delicate and less generic outcome than the black hole formation process. This is one reason why many physicists are skeptical. Black holes form naturally from a wide range of initial conditions, while gravastars seem to require special circumstances. For a gravastar to exist as a stable object, over long time scales, the internal pressures and gravitational forces have to be in careful balance. The outward push from the vacuum-like interior must exactly counteract the inward pull of gravity on the shell. If this balance is disturbed, say by infalling matter, or by perturbations from gravitational waves, or by small quantum fluctuations, the object might become unstable. Stability analyses of gravastar models involve solving the equations of general relativity with various perturbations and checking whether the perturbations grow over time or decay away. Some models turn out to be stable under certain conditions, while others are unstable and would collapse into a black hole or expand and disperse. The mathematical landscape here is intricate with many parameters that can be adjusted: the equation of state of the shell, the thickness of the shell, the properties of the interior, and so on. The case file contains many pages of calculations exploring these parameter spaces, looking for regions where stable solutions exist. The upshot is that stable gravastars are possible in principle, but they occupy a narrow range of conditions, and it's not obvious that nature would naturally produce objects in that range. One of the motivations for considering gravastars is the information paradox. If a gravastar has no true event horizon, then infalling matter never crosses a point of no return. Instead, it might reach the shell, interact with it in some way, and leave some trace of its quantum information in the shell's structure, or in the fields around it. This is very different from the black hole case, where classical reasoning suggests that information disappears behind the horizon and is lost when the black hole evaporates. With a gravastar, the information could be stored in the shell itself, perhaps encoded in subtle patterns or excitations that would be extremely difficult to observe, but not fundamentally inaccessible. This offers a potential resolution to the paradox, though the details are far from worked out. You'd need a full quantum theory of the shell and the surrounding fields to describe exactly how the information is preserved and how it might eventually be recovered. Still, the absence of a horizon is a conceptually significant difference, one that changes the nature of the problem from a strict no-go result to a difficult but possibly solvable puzzle. Gravitational waves offer a potential way to test whether gravastars might exist. When two compact objects merge, they produce ripples in space-time that detectors like LIGO and Virgo can measure. The waveform from a black hole merger has a characteristic structure: a chirp as the objects spiral together, a peak at the moment of merger, and then a ring-down phase where the newly formed black hole settles into a stable state by emitting gravitational waves at specific frequencies, like a struck bell. If the merging objects were gravastars instead of black holes, the ring-down phase might be different. Because a gravastar has a surface, the shell, gravitational waves could reflect off that surface and bounce back and forth between the shell and the surrounding space-time. This could produce faint echoes in the gravitational wave signal, arriving a short time after the main ring down. The time delay between echoes would depend on the size of the object and the precise location of the reflecting surface. Detecting such echoes would require extremely sensitive measurements and careful analysis to separate them from noise and instrumental artifacts. Some researchers have looked for echoes in the LIGO-Virgo data from observed mergers, and a few have claimed tentative detections, but these claims are controversial and not widely accepted. The consensus so far is that the data are consistent with black hole mergers and do not require any alternative model. But the search continues, and future detectors with better sensitivity might be able to place stronger constraints on gravastar-like structures. Another potential signature comes from the interaction of matter and light with the gravastar's surface. A black hole has no surface in the usual sense. Matter that crosses the horizon simply keeps falling inward. A gravastar, by contrast, has a shell that in falling matter would eventually encounter. What happens at that encounter depends on the properties of the shell. If the shell is a solid or fluid-like structure, infalling gas might crash into it, heat up, and radiate energy in X-rays or other wavelengths, before settling onto the surface. This could produce emission signatures different from the smooth accretion flows onto a black hole. Alternatively, if the shell has exotic properties, matter might be reflected or absorbed in unexpected ways. Light rays that graze very close to the surface might also behave differently if there's a reflective boundary rather than an absorbing horizon. These effects would be strongest very close to the object, making them hard to observe, but in principle they could show up as small anomalies in the spectra of accreting compact objects or in the detailed shapes of emission lines. So far, no such anomalies have been confirmed, but the data are not yet precise enough to rule out all gravastar models. The Event Horizon Telescope has produced images of the supermassive objects at the centres of the M87 galaxy and our own Milky Way, showing dark regions surrounded by bright rings of glowing gas. These images are consistent with the silhouettes of black hole event horizons, where light rays that come too close are captured and never escape, creating a shadow. If the central objects were gravastars, would the images look different? In many gravastar models, the answer is not much. Because the external spacetime is almost identical to that of a black hole, the bending of light rays far from the object proceeds in the same way, and the apparent size and shape of the shadow would be very similar. Only extremely fine details, perhaps related to how light behaves in the last fraction of a radius above the surface, might differ. The current resolution of the Event Horizon Telescope is not sufficient to detect such tiny differences. Future improvements in the array, or new techniques for analysing the data, might eventually provide a test, but for now the images we have support the black hole model and do not require any alternative. Despite the theoretical interest in gravastars, many physicists remain sceptical. The main criticisms fall into a few categories. First, the formation mechanism is unclear and seems to require special conditions that may not occur in realistic astrophysical collapse. Second, the stability of gravastars is delicate, and many models face instabilities under perturbations that would naturally occur in the universe. Third, the shell and interior require exotic equations of state that don't correspond to any known form of matter or energy, which makes the models feel ad hoc. Fourth, and perhaps most importantly, black holes already provide a simple, universal model that fits all the available observations without needing extra assumptions. Occam's razor suggests sticking with the simpler explanation unless observations force you to complicate things. Gravastars are kept around as interesting theoretical possibilities, useful for exploring the boundaries of what general relativity allows, but they have not earned a place in the standard astrophysical toolkit. The case file remains open, but it's not the active file on the top of the desk. It's worth placing gravastars in the broader context of exotic compact object proposals. Each alternative model comes with its own motivations and theoretical underpinnings. Boson stars, for example, arise from the idea that there might exist scalar fields, fundamental fields with no spin, that clump together under their own gravity, balanced by quantum pressure. These would be held up not by nuclear forces or degeneracy pressure, but by the uncertainty principle applied to the scalar field. If such fields exist in nature, they could in principle form compact objects that mimic black holes. Fuzzballs come from string theory, where the event horizon is replaced by a complicated structure made of strings and higher dimensional branes, all in a highly excited quantum state. The idea is that the interior of a black hole is not empty space falling toward a singularity, but a dense tangle of stringy degrees of freedom. Graver stars, by contrast, stay closer to classical general relativity, but modify the equation of state and interior structure. Each of these proposals tries to avoid the singularity and often the event horizon, but they do so in very different ways, invoking different physics. The existence of this whole drawer of ideas reflects the fact that physicists are not entirely comfortable with black holes, despite their success, and are willing to explore alternatives in the hope that one might eventually connect with observations or with a deeper theory of quantum gravity. Why do physicists bother with graver stars and similar concepts if there's no direct evidence for them? One reason is that these models serve as thought experiments, stress testing the assumptions and predictions of general relativity and quantum field theory. By constructing an alternative that almost mimics a black hole, you can ask, what exactly are the features that would allow us to distinguish them? This clarifies what aspects of black hole behaviour are robust and universal, and what aspects might be vulnerable to modification if the underlying physics changes slightly. Another reason is preparedness. If future observations from better gravitational wave detectors, higher resolution imaging, or unexpected discoveries show small but persistent deviations from black hole predictions, having a library of alternative models ready will speed up the process of interpreting the data. Instead of starting from scratch, researchers can pull out the graver star file, or the boson star file, or the fuzzball file, and see which one fits the anomaly. Even if none of these models turn out to be correct, the exercise of building and analysing them improves our understanding of what is possible and what is ruled out. There's also a philosophical dimension. Black holes are strange enough. Regions of space-time where the normal rules break down, where singularities lurk, where information might be lost. Graver stars and their cousins remind us that our current theories might not be the final word, that nature could have chosen a different design, one that looks almost the same from the outside but resolves some of the internal difficulties in an unexpected way. This kind of humility is healthy in science. It's easy to become attached to a model that works well, and to forget that the model is an approximation, a map rather than the territory. Alternative models, even speculative ones, keep the door open to surprise. They prevent us from declaring victory prematurely. The Gravastar case file, then, is neatly organised and thoroughly documented. The equations are written out, the stability analyses are completed, the possible observational signatures are listed, and the criticisms are acknowledged. The file sits in a cabinet alongside other speculative ideas, ready to be pulled out and reviewed if new data warrant. For now, the standard black hole model remains the simplest and best supported explanation for the ultra-compact objects we observe in the universe. Black holes fit the gravitational wave signals from mergers. They match the shadows imaged by the Event Horizon Telescope. They are consistent with the orbits of stars around the supermassive object at the centre of our galaxy, and they emerge naturally from the well-understood physics of stellar collapse. No observation has yet required us to invoke graver stars or any other exotic alternative. But the universe has a history of surprising us. As telescopes and detectors improve, astronomers will quietly compare new data against both the standard model and these backup designs. Perhaps gravitational wave detectors will one day see echoes that can't be explained away as noise. Perhaps future imaging will reveal subtle features near the shadows of supermassive objects that don't match black hole predictions. Perhaps in falling matter we'll produce emission lines with strange properties that hint at a surface rather than a horizon. Or perhaps, as quantum gravity is better understood, theorists will find that something like gravastars emerges naturally from the fundamental equations, not as a contrived alternative but as a genuine prediction. Any of these developments would elevate gravastars from the maybe column to the investigate seriously column. Until then, the case file remains where it is, a backup blueprint filed away in the archives of theoretical physics. There's no drama in this, no race against time, no looming cosmic mystery that gravastars are urgently needed to solve. It's just the routine work of keeping options open, of maintaining a diverse portfolio of ideas so that when, or if, observations eventually show that the universe is doing something unexpected, we have a place to start. The listener can rest easy knowing that the question has been thought through, that the mathematics has been checked, that the alternatives have been carefully constructed and analysed. Black holes work, and they work well, but somewhere in the background, other designs wait quietly on the shelf just in case. The technical details in the Gravistar folder run deep, and it's worth spending a moment with some of the more intricate pages that lie beneath the summary sheets. One set of calculations deals with the boundary conditions at the shell, the mathematical requirements that must be satisfied to smoothly join the interior and exterior spacetimes. In general relativity, spacetime is described by a metric, a mathematical object that tells you how to measure distances and times. When you have different regions with different properties, like the vacuum-like interior and the Schwarzschild-like exterior, you need to specify how the metric changes as you cross from one region to the other. If the transition happens across a surface with negligible thickness, you can use what are called junction conditions, which relate the jump in certain geometric quantities to the energy and pressure in the surface layer. These conditions, worked out decades ago by physicists studying thin shells and curved spacetime, constrain the allowed properties of the Gravistar shell. They ensure that spacetime doesn't develop kinks or discontinuities that would signal a breakdown of the model. Working through these junction conditions for various proposed equations of state is a standard exercise in the Gravistar literature, and the results determine whether a given model is mathematically consistent. Another set of pages in the file deals with rotating gravastars. Real astrophysical objects almost always have some spin, and incorporating rotation into the model complicates things significantly. For black holes, rotation is handled by the Kerr solution, which describes a spinning black hole in terms of its mass and angular momentum. A rotating Gravistar would need to match the Kerr solution on the outside, but the interior structure and the properties of the shell would be affected by the rotation. The centrifugal forces from the spin would push outward, altering the balance between the internal vacuum pressure and the gravitational pull on the shell. Some studies have explored rotating Gravistar models and found that, in principle, they can be constructed, but the parameter space of stable solutions becomes even narrower. The shell has to be structured in a way that accommodates the frame-dragging effects of the rotating spacetime, and the stresses within the shell become more complicated. These rotating models are less well studied than their non-rotating counterparts, in part because the mathematics is significantly harder, but they are a necessary part of the file if Gravistars are to be taken seriously as alternatives to real astrophysical objects. There's also a section on charged Gravistars, even though astronomers generally expect compact objects in nature to be electrically neutral. The reason for studying charged models is not realism but completeness. If you want to understand the full space of solutions to Einstein's equations, you explore all the possibilities that the math allows, including ones that may not occur in nature. A charged Gravistar would match the Reissner-Nordström solution on the outside, which describes a black hole with both mass and electric charge. The interior vacuum-like region and the shell would have to accommodate the electromagnetic field, and the junction conditions would involve contributions from both the gravitational and electromagnetic stress energy. These models are mostly of academic interest, but they appear in the file because theoretical physics values systematic exploration. You never know when a seemingly unrealistic scenario might turn out to be relevant in some unexpected context, or when the techniques developed for one problem might apply to another. Thermodynamic properties also occupy a page or two in the Gravistar folder. Black holes have a well-defined temperature, known as the Hawking temperature, which is inversely proportional to their mass. They also have an entropy, given by the Bekenstein-Hawking formula, which is proportional to the area of the event horizon. These thermodynamic properties are not just analogies, they satisfy the laws of thermodynamics in a precise mathematical sense. Do Gravistars have similar properties? The answer depends on the details of the model. Because a Gravistar has no event horizon, the usual derivation of Hawking, radiation doesn't directly apply. However, some researchers have explored whether the shell itself might have associated entropy, or whether quantum effects near the surface could produce a thermal emission analogous to Hawking radiation. The results are model-dependent and not as universal as the black hole case. This is another area where the Gravistar framework feels less complete. Black holes come with a package of well-defined thermodynamic properties that fit into a broader structure connecting gravity, quantum mechanics, and statistical mechanics. Gravistars, by lacking a horizon, lose some of that elegant structure, and it's not clear what replaces it. The thermodynamics section of the file is marked with question marks and marginal notes, indicating that this is an area where more work is needed. There's also a discussion of observational campaigns that might, in the future, provide more stringent tests of the Gravistar hypothesis. One possibility involves pulsar timing arrays, which use networks of precisely timed pulsars to detect low-frequency gravitational waves. If supermassive objects at the centres of galaxies were gravastars rather than black holes, mergers of such objects might produce gravitational wave signals with subtle differences from black hole mergers, differences that could accumulate over the long in-spiral phase before the objects merge. Pulsar timing arrays are most sensitive to these low-frequency waves, which correspond to the orbital motion of massive objects over months or years. Another possibility involves future space-based gravitational wave detectors, which would observe a different frequency range than ground-based detectors and could measure the properties of compact objects with much higher precision. A third possibility involves next-generation radio telescopes that could image the environments around compact objects in unprecedented detail, looking for the faint glow or scattered emission from material interacting with a surface rather than disappearing into a horizon. None of these campaigns are specifically designed to look for gravastars, but they are part of the broader effort to test general relativity and explore the nature of compact objects, and any anomalies they find would naturally be compared against the gravastar models in the file. The historical context is worth noting as well. The gravastar concept was formalized in the early 2000s, though some of the underlying ideas go back further. It emerged during a period when physicists were actively grappling with the information paradox and exploring various resolutions, and when advances in observational astronomy were beginning to provide detailed data on compact objects. The idea was to take seriously the possibility that quantum effects or exotic matter might fundamentally alter the endpoint of gravitational collapse. The initial papers laid out the basic structure, 3-layer model, vacuum interior, thin shell, and showed that such configurations could satisfy Einstein's equations. Subsequent work explored stability, rotation, observational signatures, and connections to other areas of physics. The concept has never gained mainstream acceptance, but it has remained a fixture in the literature, cited and discussed in review articles on exotic compact objects and alternatives to black holes. It represents a particular style of theoretical physics, taking the equations seriously, exploring what they allow, and constructing explicit models even when the physical realization is uncertain. One of the recurring themes in the gravastar literature is the question of fine-tuning. The models that work, that are stable, that match observations, that avoid obvious pathologies, tend to require very specific choices of parameters. The equation of state of the shell needs to fall within a narrow range. The thickness of the shell, though small, cannot be arbitrarily small, or the junction conditions fail. The properties of the interior vacuum-like phase need to be chosen carefully to produce the right amount of outward pressure. When a model requires many such specific choices, physicists start to worry that it's not a natural outcome of fundamental physics, but rather an artifact of the construction, a solution that exists on paper but would never arise in the real universe. Black holes, by contrast, form generically from gravitational collapse with no fine-tuning required. You start with a sufficiently massive object, let gravity do its work, and you get a black hole, regardless of the details of the initial configuration. The gravastar's need for special conditions is one of the main reasons for skepticism. It suggests that even if the model is mathematically consistent, it might be too fragile to be realized in nature. Yet there's a counter-argument, one that appears in the margins of the case file. Perhaps the fine-tuning is not a bug, but a feature. Perhaps nature does sometimes produce structures that require delicate balances, and we only discover them when we look carefully enough. The solar system, after all, is in some sense fine-tuned. The Earth sits at just the right distance from the Sun for liquid water to exist, and the Moon has just the right size and distance to produce spectacular solar eclipses. These facts don't require deep physical principles, they're contingent outcomes of the formation history of our planetary system. Similarly, maybe some fraction of compact objects form under conditions that happen to produce gravastar-like configurations, not because it's the generic outcome, but because the right circumstances occasionally occur. This line of reasoning doesn't rescue the gravastar from its main problem, which is the lack of observational evidence, but it suggests that the fine-tuning objection shouldn't be regarded as fatal. The universe is a big place, and rare events happen. The connection between gravastars and cosmology is another thread worth pulling. The interior of a gravastar, with its vacuum-like properties and repulsive pressure, bears a resemblance to the early universe during the inflationary epoch, when a similar kind of vacuum energy drove exponential expansion. Some researchers have speculated about whether there might be a deeper connection, whether the physics that produces inflation on cosmological scales could also, under extreme conditions, produce localized regions of vacuum energy inside compact objects. This is highly speculative, and the energy scales involved are vastly different, but it's an example of how exotic compact object models can sometimes point toward unexpected links between different areas of physics. If gravastars exist, understanding them might shed light on the nature of vacuum energy and the cosmological constant problem, one of the major unsolved puzzles in fundamental physics. Conversely, progress in understanding dark energy and the vacuum energy of the universe might provide insights into whether the kind of interior posited for gravastars is physically plausible. Another page in the file considers the possibility of observing gravastars indirectly, through their effects on surrounding matter. Suppose a gravastar is part of a binary system, orbiting a normal star. As the two objects orbit each other, the gravastar's gravitational field will pull on the companion star, causing it to wobble. The precise pattern of the wobble depends on the mass and compactness of the gravastar, and for distant observations, a gravastar and a black hole of the same mass would produce indistinguishable wobbles. But if the companion star is close enough, or if the system evolves to the point where mass is being transferred from the star to the gravastar, then differences might emerge. Mass falling onto a gravastar would hit the shell and release energy, potentially producing different spectral features than mass falling into a black hole. Some X-ray binaries, systems where a compact object accretes matter from a companion star, have been studied intensively for decades, and their spectra are generally consistent with matter falling into black holes. But the data are not always perfect, and there are occasional systems with features that are not fully understood. The gravastar hypothesis hasn't been needed to explain any of these systems so far, but it remains in the toolkit as a possible explanation if future observations reveal something that doesn't fit the standard picture. The file also contains a section on the role of magnetic fields. Astrophysical compact objects are often embedded in strong magnetic fields, either from the surrounding environment or generated by processes in accretion disks. Black holes themselves are not magnetic, but the plasma around them can carry magnetic fields that play a crucial role in launching jets and driving accretion. Would a gravastar interact with magnetic fields differently than a black hole? If the shell has physical properties, if it can support electric currents or have a conductivity, then yes, there could be differences. Magnetic field lines might anchor to the shell, or currents in the shell might generate magnetic fields, leading to observable effects in the emission from the accretion flow or the structure of jets. These ideas are sketched out in the file but not worked out in detail, partly because the electromagnetic properties of the exotic shell material are not well defined. It's another entry in the long list of things that might be different if gravastars exist, a list that is useful for observers to keep in mind but not yet actionable in the sense of planning specific observations. Finally, the case file includes a brief note on the sociological and epistemological aspects of maintaining speculative models. Science is a social process, and decisions about which ideas to pursue, which models to develop, and which observations to prioritize are influenced by community norms, funding structures, and the preferences of senior researchers. Black holes are a mature, well-funded field with a large community of researchers and access to cutting-edge observational facilities. Gravastars and other exotic alternatives are niche topics, pursued by a much smaller number of researchers, often on the side while doing more mainstream work. This disparity is justified by the evidence. Black holes have the data on their side, but it also creates a feedback loop. If fewer people work on alternatives, fewer theoretical tools are developed, fewer predictions are made, and fewer observational tests are proposed. The models remain underdeveloped compared to the standard picture, which in turn makes them less attractive to new researchers and less likely to be included in major observational campaigns. The note in the file acknowledges this dynamic without advocating for any particular solution. It's simply a recognition that the scientific process involves choices about resource allocation, and those choices can affect which ideas get thoroughly explored and which remain perpetual underdogs. The gravastar file, with all its pages of equations, stability analyses, observational proposals, criticisms, historical context, and speculative connections, paints a picture of a theoretical idea that is complete enough to be taken seriously, but not compelling enough to challenge the dominant paradigm. It's a well-constructed model that addresses real concerns about singularities and information loss, but it does so at the cost of introducing exotic ingredients and fine-tuned configurations that have no independent evidence supporting them. The file represents years of careful work by researchers who wanted to explore an alternative path, to see where it led, to check whether nature might have chosen a different solution to the problem of extreme gravitational collapse. The answer so far is that nature probably didn't, but the question remains open, and the file remains ready for consultation. There's something almost comforting about the existence of this file sitting in its cabinet. It represents a kind of intellectual insurance policy, a hedge against the possibility that our current understanding is incomplete in ways we haven't fully appreciated. Science progresses not just by accumulating evidence for the dominant theory, but also by maintaining awareness of what the alternatives would look like, what they would predict, and how we would recognize them if they turned out to be correct. The gravastar file serves this function. It's not there to compete with black holes in the day-to-day work of astrophysics. It's there to remind us that the equations of general relativity, combined with quantum considerations and exotic matter, permit other solutions, and that we should remain alert to the possibility that observations might someday point us toward one of those alternatives. One of the more subtle aspects of the gravastar proposal involves the nature of time near the surface. In a black hole, time dilation becomes extreme as you approach the event horizon. A distant observer watching something fall toward a black hole would see it slow down, redshift, and effectively freeze at the horizon, though from the perspective of the infalling object, it crosses the horizon in finite proper time and continues inward. This asymmetry between different observers' perspectives is one of the more counterintuitive features of black hole physics. With a gravastar, the situation is somewhat different. There is no horizon to cross, so there's no sharp boundary where time appears to stop for distant observers. Instead, time dilation increases smoothly as you approach the shell, becoming very large near the surface, but there's no point of no return. An object approaching the shell would slow down from the perspective of a distant observer, but eventually it would interact with the shell itself, either bouncing off, sticking to it, or being absorbed in some way. The absence of the horizon means that the causal structure of space-time around a gravastar is fundamentally different from that around a black hole, even if the gravitational field at large distances is nearly the same. This difference is encoded in the global geometry, in the way light cones tilt and in which events can influence which other events. Physicists who work on causality and the foundations of general relativity find these differences conceptually important, even if they're difficult to probe observationally. The question of what happens to the shell over cosmological timescales is another entry in the file. Even if a gravastar forms and is stable on astrophysical timescales, millions or billions of years, what happens over even longer times? Does the shell gradually evaporate through some quantum process? Does it slowly accumulate in falling matter from the surrounding environment, thickening or gaining mass? Does the balance between the interior pressure and the gravitational attraction shift over time, causing the object to evolve? Black holes have a clear long-term fate. They evaporate through Hawking radiation, though for stellar mass or larger black holes, this process takes far longer than the current age of the universe. Gravastars lacking a horizon might not have the same Hawking radiation mechanism, but they could have their own slow evolution driven by quantum effects in the shell or interactions with the surrounding medium. The timescales for these processes are highly uncertain, and in many cases they would be so long that they're effectively irrelevant for any observational program. But from a theoretical standpoint, understanding the ultimate fate of a gravastar is part of constructing a complete model. The file includes some preliminary estimates and a list of open questions, acknowledging that this is an area where the physics is too poorly understood to make definitive predictions. There's also a brief discussion of the possibility that gravastars might exist in a spectrum, not as a single type of object, but as a family of configurations with varying properties. Just as stars come in a wide range of masses, compositions, and evolutionary states, perhaps compact objects could come in varieties beyond just black holes and neutron stars. Some configurations might be very close to black holes, with shells so close to the would-be horizon that they're nearly indistinguishable. Others might have thicker shells, or different interior properties, leading to more pronounced deviations from black hole behaviour. The parameter space of possible gravastars is large, and exploring it systematically is a daunting task. But if future observations ever provide evidence for something that doesn't quite fit the black hole model, one of the first questions will be, where in the gravastar parameter space does this object sit? Having the framework already developed, having the calculations already done for a range of configurations, would make answering that question much faster. This is the value of preparatory theoretical work, even in the absence of immediate observational motivation. The role of numerical simulations deserves mention as well. Much of the gravastar literature is based on analytical calculations, solving Einstein's equations in simplified settings, where symmetries make the problem tractable. But the real universe is messy. Compact objects spin, they wobble, they accrete matter in complicated ways, they collide and merge. To fully understand how gravastars would behave in these realistic scenarios, you need numerical simulations, computer codes that solve Einstein's equations on a grid, evolving the spacetime geometry forward in time as matter and energy move around. Simulating black holes is already a major computational challenge, requiring sophisticated algorithms and supercomputers. Simulating gravastars would be even harder, because you'd need to model the thin shell with its exotic equation of state, track how it responds to perturbations, and ensure numerical stability throughout. Some preliminary simulations of gravastar-like objects have been done, but they're far from comprehensive. The file contains a note that this is an area where progress depends on both theoretical advances in formulating the models in a form suitable for numerical evolution and computational advances in solving the resulting equations. If gravastars ever become a serious competitor to black holes based on observations, there will be a rush to develop better simulation tools. For now, the lack of detailed simulations is one more reason that the gravastar model feels incomplete compared to the black hole model, which benefits from decades of intensive numerical work. Educational outreach is another small note tucked into the file. Black holes have captured the public imagination in a way that few scientific concepts have. They appear in popular books, documentaries, science fiction, and casual conversation. Gravastars, by contrast, are known only to specialists. This disparity reflects not just the difference in observational support, but also the difference in narrative appeal. Black holes are dramatic, cosmic monsters with inescapable pull, regions where the laws of physics break down, objects that devour stars and warp time. Gravastars, by design, are the anti-drama. They're constructed specifically to avoid the most extreme features of black holes, replacing singularities and horizons with carefully balanced structures. From a storytelling perspective, they're harder to make exciting. But there's a lesson here about the nature of scientific understanding. The universe doesn't care about our preference for dramatic stories. If gravastars turn out to exist, science communicators will need to find ways to convey their significance, to explain why an object without a singularity or horizon is just as worthy of wonder as a black hole, perhaps more so because it represents a solution to some of the deepest puzzles in physics. The file includes a few drafts of popularizations, attempts to frame gravastars in compelling terms, experiments in finding the right metaphors and analogies. It's a small section, but it reflects the reality that scientific ideas, especially speculative ones, need advocates who can communicate them clearly and persuasively. Another thread in the file explores the connection between gravastars and other areas of modified gravity. Some researchers have proposed changes to Einstein's equations at very high curvatures or very large scales, modifications designed to address cosmological puzzles or to avoid the need for dark matter. In some of these modified theories, the endpoint of gravitational collapse might naturally be something other than a black hole. The modifications might provide the repulsive forces or exotic matter properties needed to stabilize a gravastar-like object without fine-tuning. Exploring these connections is part of a broader effort to understand how different proposed modifications to general relativity relate to each other, and whether they make distinctive, testable predictions. If a particular theory of modified gravity predicts the existence of gravastars with specific properties, and if those properties could be tested observationally, that would tie the gravastar hypothesis to a larger theoretical framework, making it less ad hoc and more predictive. So far, these connections remain exploratory, but they're part of the intellectual landscape that the gravastar concept inhabits. The file also includes a section on the philosophical implications of the choice between black holes and gravastars. Both types of objects push the boundaries of our understanding, but they do so in different ways. Black holes confront us with singularities, regions where the theory predicts its own breakdown, and with horizons that divide space-time into regions that can never communicate. These features raise questions about determinism, the nature of space-time, and the limits of scientific knowledge. Gravastars, by avoiding singularities and horizons, sidestep some of these issues but introduce others. They require us to accept exotic matter with properties unlike anything we've encountered, to believe in phase transitions or quantum effects at energy scales we can't directly probe, and to explain why the universe would go to the trouble of constructing such delicately balanced objects. In a sense, the choice between the two models reflects a choice about which kinds of mysteries we find more palatable. Do we prefer a theory that's simple and universal but contains infinities and information paradoxes, or a theory that's more complex but avoids the most pathological features? There's no objective answer to this question. It's a matter of aesthetic preference and research strategy. The file acknowledges this without taking sides, presenting both perspectives as legitimate ways to think about the problem. The possibility of hybrid objects, configurations that share features of both black holes and gravastars, occupies a few pages near the end of the file. Perhaps the transition from ordinary matter to the gravastar state is not instantaneous or complete. Perhaps some collapsing objects form partial horizons, or develop gravastar-like shells that are unstable and eventually collapse further, or oscillate between different configurations. The universe might contain a continuum of compact objects, with black holes and neutron stars at the endpoints and various exotic structures in between. Observationally, this would make the task of classification more difficult, but it would also provide a richer landscape to explore. If we eventually observe something that's clearly not a standard black hole or neutron star, but also doesn't quite fit any single alternative model, it might be a hybrid or transitional object, and understanding it would require drawing on insights from multiple theoretical frameworks. The hybrid section of the file is speculative even by the standards of gravastar research, filled with sketches and question marks, but it's there because completeness demands, considering not just the clean cases but the messy ones too. There's a reference to the role of gravitational lensing as well, though it's brief. Black holes act as gravitational lenses, bending the paths of light rays that pass nearby. The resulting patterns of multiple images, distorted arcs, and time delays have been studied extensively in the context of galaxies and galaxy clusters, where the lensing is done by large distributions of mass. For a single compact object like a stellar mass black hole passing in front of a distant star, the lensing produces a characteristic brightening curve called a microlensing event. If the object doing the lensing were a gravastar instead of a black hole, would the microlensing curve look different? In most cases, probably not, because the lensing is determined primarily by the total mass and the distance scales involved, both of which would be nearly the same. But there might be subtle differences if the light passes extremely close to the surface of the gravastar, where the presence of a boundary rather than a horizon could affect the bending. These differences would be tiny and hard to detect with current instruments, but they're noted in the file as another potential observational handle, another line item on the checklist of ways to test the hypothesis. The question of observational bias is worth considering too. When astronomers discover a compact object, they typically assume it's a black hole if it's above a certain mass threshold, and lacks the characteristic signatures of a neutron star. This assumption is reasonable given the lack of evidence for alternatives, but it also means that we might be systematically misclassifying objects. If gravastars exist and look very similar to black holes in most observations, they would be labelled as black holes in catalogues and databases, and no one would think to look more closely. This kind of confirmation bias is a risk in any field. If you don't look for alternatives, you won't find them, even if they're there. The gravastar file includes a reminder to observers to remain open to anomalies, to follow up on unexpected features rather than smoothing them over, and to consider alternative interpretations when the standard model doesn't quite fit. It's a small point, but an important one. The discovery of a new phenomena often begins with someone noticing that the data are just a bit stranger than they should be. Finally, the file closes with a summary of the current state of play. Black holes remain the standard model, supported by a wealth of observations and deeply integrated into our understanding of astrophysics. Gravastars are a theoretical alternative, mathematically consistent but physically speculative, with no direct observational support. The path forward involves continued observations with increasing precision, ongoing theoretical work to refine the models and explore their consequences, and a willingness to revisit the question if new data provide reasons to do so. The tone is calm and measured, neither dismissive nor overly optimistic. The file is complete as it needs to be for now, ready to be consulted if circumstances change, but not demanding immediate action. And so, the Gravestar case file sits in its place, one folder among many in the archives of theoretical physics. It represents a particular kind of scientific work, careful, thorough, speculative, and patient. It's the work of exploring alternatives, of asking what if, of preparing for possibilities that may never materialize. There's no urgency, no crisis, no pressing need to resolve the question immediately. The universe will reveal its secrets in its own time, through observations that accumulate slowly, through patterns that emerge gradually, through anomalies that eventually demand explanation. Until then, the file waits. The equations are ready. The predictions are documented. The observational signatures are listed. If the universe has indeed chosen to build gravastars, we'll recognize them when we see them. If it hasn't, the exercise of thinking through the possibility will still have been worthwhile, clarifying what we know, sharpening our predictions, and reminding us that our current understanding, however successful, is always provisional. That's the nature of science, confident in its conclusions but humble about its completeness, always ready to update the files when new evidence arrives. For now, though, the Gravastar file rests quietly, a neatly labelled maybe, in a cabinet full of questions that humanity is slowly, patiently working to answer. The next story is about to begin. Please relax and enjoy. Tonight is not about explosions. Tonight is about inventory. Look around you. The walls, the floor, the air between your fingers, the device in your hand. Every single object is built from a remarkably limited set of ingredients pulled from the periodic table. Astronomers and physicists treat these elements the way warehouse managers treat stock. They track where they come from, how their quantities change, and how they flow through the universe. The cosmos has a supply chain, and it's been running for 13 billion years, quietly converting simple materials into everything you see. We're going to walk through it step by patient step, no drama, just the slow mechanics of how atoms get made. In the very beginning, the universe was hot and dense, packed so tightly that space itself was opaque. This wasn't a place you could stand or observe. It was more like a condition, a state of extreme compression spreading outward faster than anything would ever move again. During the first few minutes of this expansion, temperatures were high enough, and particles were close enough together that protons and neutrons could stick when they collided. They combined into the first atomic nuclei, mostly hydrogen, a significant fraction of helium, and trace amounts of lithium and beryllium. This window lasted only minutes. As the universe expanded further, it cooled. The density dropped. Nuclear fusion stopped. What remained was a simple inventory, roughly 75% hydrogen nuclei by mass, 25% helium, and barely anything else. That was the starting catalogue. Everything more complex would have to be manufactured later, somewhere else, under different conditions. For hundreds of millions of years after that brief production run, nothing much happened. The universe continued expanding and cooling, and its contents, mostly hydrogen and helium gas, spread out into vast and nearly uniform clouds. No stars existed yet, no planets, no heavy elements. The gas was neutral, transparent, and cold. This era is sometimes called the Dark Ages, not because it was frightening, but because there were no light sources. Gravity was active, though. Tiny variations in density, slight clumps in the distribution of matter, began to grow. Where the gas was even a little denser, gravity pulled in more gas from the surroundings. Slowly, over millions of years, these regions condensed. They were like gathering points in an empty warehouse, places where raw material began to accumulate without any plan or schedule, just the patient pull of mass on mass. Eventually, some of these collapsing regions became dense enough and hot enough at their centres that something new happened. Gravity compressed the hydrogen gas until the core temperatures reached millions of degrees. At that point, hydrogen nuclei, protons, started moving fast enough to overcome their electrical repulsion and fuse together. This was the birth of the first stars, and it marked the activation of the universe's first factories. A star is essentially a self-regulating production line. It takes the abundant hydrogen from the initial inventory and processes it into helium, releasing energy in the process. That energy radiates outward, creating the pressure that holds the star up against its own gravity. As long as fuel remains, the process continues steady and predictable, converting raw hydrogen into a slightly more complex product. The core of a star is where hydrogen fusion happens. 4 hydrogen nuclei combine through a series of steps to form one helium nucleus. The helium nucleus weighs slightly less than the 4 hydrogens that went into it, and that missing mass is converted into energy, according to the principles worked out in the early 20th century. This energy moves outward through the star, sometimes by radiation, sometimes by convection, depending on the star's internal structure. What matters is that the process is stable. The star reaches an equilibrium. Gravity tries to squeeze it smaller, fusion energy pushes outward, and the two forces balance. A star like the Sun can maintain this balance for billions of years, slowly working through its hydrogen supply, steadily adding to the universe's stock of helium. In supply chain terms, this is the basic transformation step, the simplest upgrade from raw material to a processed product. Different stars run their production lines at different speeds. Massive stars have stronger gravity pressing inward, so their cores run hotter and fusion proceeds faster. They burn through their hydrogen in millions of years, not billions. Small stars with less mass and cooler cores fuse hydrogen slowly and can keep running for tens of billions of years. The universe is full of these varying production rates, from fast and intense to slow and steady, all converting hydrogen into helium but on vastly different timescales. The result is that the universe's helium fraction increases gradually over time, but the process is spread out across countless individual stars, each operating independently. When a star exhausts the hydrogen in its core, the equilibrium shifts. Without fusion generating energy, the core contracts under gravity. As it contracts, it heats up. Meanwhile, hydrogen in a shell around the core is now hot enough to fuse, so fusion continues but in a different location. The star's outer layers, feeling the increased energy output from the shell, expand outward. The star becomes a red giant, cooler on the surface but much larger in volume. Inside, the contracting core eventually reaches temperatures high enough for a new process to start. Helium nuclei can now fuse together. 3 helium nuclei combine to form carbon. Further reactions convert helium and carbon into oxygen. This is an upgrade in the manufacturing process. The star is no longer limited to producing helium. It can now create heavier elements. Not all stars reach this stage. Low-mass stars may never get their cores hot, enough for helium fusion to begin efficiently. But stars with enough mass move through this phase, adding carbon and oxygen to the cosmic inventory. In very massive stars, the process continues further. After the core converts helium into carbon and oxygen, the core contracts again, heats up again, and initiates another round of fusion. Carbon fuses into heavier elements like neon and magnesium. Then oxygen fuses, producing silicon and sulfur. Each stage requires higher temperatures and pressures than the last. Each stage also proceeds faster. Hydrogen fusion might last millions of years, helium fusion thousands of years, carbon fusion a few hundred years, oxygen fusion months. By the time silicon is fusing into iron, the process is measured in days. The star develops a layered structure like a multi-floor factory, with each shell fusing different elements. At the center is iron and nickel. Surrounding that, shells of silicon, oxygen, carbon, helium, and finally hydrogen, each at the temperature and density needed for its particular reaction. Iron is where the process stops, and the reason is straightforward. Fusion releases energy only when it produces nuclei that are more tightly bound than the ones you started with. For elements lighter than iron, fusion moves toward more stable nuclei and releases energy. For elements heavier than iron, fusion moves away from stability and requires energy input. Iron sits at the peak of nuclear stability. A massive star's core, full of iron, cannot generate energy by fusing further. The fusion assembly line has reached a dead end. The core is inert, and without energy to support it, gravity takes over. The collapse is rapid. In less than a second, the iron core implodes, compressing to incredible densities. The collapse halts suddenly when the core reaches the density of an atomic nucleus, and the infalling material rebounds. the shockwave tears through the star's outer layers, ejecting them into space. This is a supernova, and while the event is dramatic, it's useful to think of it in logistical terms, a sudden, massive shipping event. All the elements the star produced during its life, carbon, oxygen, silicon, iron, and many others, are expelled into the surrounding interstellar medium. The explosion also creates conditions extreme enough that elements heavier than iron can be produced. Neutrons are abundant in the collapsing core, and they can be captured rapidly by existing nuclei, building up heavy elements like gold, platinum, and uranium through a process called rapid neutron capture. The supernova doesn't just distribute what the star made over its lifetime, it also manufactures new products in its final moments. Neutron stars, the dense remnants left behind by some supernovae, can also contribute to the supply chain. When two neutron stars orbit each other, they gradually spiral inward, losing energy to gravitational waves. Eventually they merge, and the collision is violent enough to eject neutron-rich material into space. In these conditions, the rapid neutron capture process operates at full capacity, producing the heaviest elements on the periodic table. Neutron star mergers are much rarer than supernovae, but they appear to be responsible for a significant fraction of elements like gold and platinum. They are specialty factories, rare but essential for manufacturing the most complex items in the catalogue. There's also a slower route to building heavy elements, operating inside certain types of stars over long periods. In stars that have become red giants and are fusing helium in their cores, free neutrons are occasionally produced through specific nuclear reactions. These neutrons can be captured by existing atomic nuclei, but the process is slow, hence the name slow neutron capture, or the S process. After capturing a neutron, a nucleus may undergo beta decay, converting a neutron into a proton and shifting the element to a higher atomic number. This gradual stepwise assembly builds up elements heavier than iron over thousands of years. It's a patient process, adding components one by one rather than in sudden bursts, and it accounts for about half of the heavy elements in the universe. Once heavy elements are ejected into space, whether by supernova, stellar winds, or neutron star mergers, they don't remain isolated. They mix with the surrounding gas, the hydrogen and helium that still make up the bulk of the interstellar medium. This enriched gas can cool, accumulate, and eventually collapse under gravity to form new stars. These second-generation stars start with a different composition than the first generation. They contain not just hydrogen and helium, but also carbon, oxygen, silicon, iron, and traces of heavier elements. When these stars form planetary systems, the planets inherit this enriched mixture. The universe doesn't constantly create entirely new atoms from scratch. Instead, it recycles existing ones, blending them into new configurations. The supply chain is circular, production in stars, distribution through explosions and winds, mixing in interstellar clouds, and reassembly into new stars and planets. The formation of a planetary system is essentially a sorting process. Around a young star, a disk of gas and dust rotates and gradually clumps together. Different materials condense at different temperatures. Close to the star, where it's hot, only metals and rocky materials, elements like iron, silicon, magnesium, and oxygen, can remain solid. These materials stick together to form the cores of terrestrial planets. Farther out, where temperatures are lower, volatile compounds like water, methane, and ammonia can freeze. These ices combine with rock and metal to build the cores of gas giants, which then attract huge envelopes of hydrogen and helium. The composition of a planet depends on where it forms and what materials are available in the disk. But the underlying ingredients, the elements, themselves are the same ones produced by stellar nucleosynthesis and distributed by stellar explosions. Planets are assemblies of cosmic products, sorted by temperature and distance from the star. On a planet like Earth, further chemistry takes place. Hydrogen and oxygen combine to form water. Carbon bonds with hydrogen, oxygen, and nitrogen to create organic molecules. Nitrogen becomes a major component of the atmosphere. Iron sinks to the core, contributing to the planet's magnetic field. Silicon and oxygen form the silicate minerals that make up the crust and mantle. Trace elements, phosphorus, sulfur, calcium, potassium, serve specialized roles in geological and potentially biological processes. None of these combinations are random. They depend on the relative abundances produced by the cosmic supply chain, which elements stars make in what quantities, and how those elements are distributed and mixed in space. The atmosphere and oceans of a planet are particular mixtures of delivered products, processed further by planetary chemistry, but still constrained by the underlying inventory. Astronomers have a way to read this inventory directly. Each element produces a unique pattern of spectral lines, specific wavelengths of light that the element absorbs or emits. These patterns are like barcodes. When light from a star passes through its outer atmosphere, the atoms there absorb certain wavelengths, leaving dark lines in the spectrum. When gas clouds emit light, the atoms produce bright lines at those same wavelengths. By analysing these spectral lines, astronomers can determine which elements are present and in what proportions. Over decades of observation, they've built detailed abundance tables. How much hydrogen, helium, carbon, oxygen, iron, and dozens of other elements exist in different stars, gas clouds, and galaxies. This is the record-keeping side of the supply chain, the careful documentation of which products are where, based on the light they interact with. Galaxies change their chemical composition over time. Early in a galaxy's history, the gas is mostly hydrogen and helium, with very few heavy elements. Astronomers call this metal poor, using metals to mean anything heavier than helium. As stars form, live and die, they enrich the gas with heavier elements. Successive generations of stars incorporate more metals, and their planets do too. Astronomers track this chemical evolution by measuring the abundances in stars of different ages. Old stars formed billions of years ago have low metal content. Young stars formed more recently have higher metal content. The galaxy's composition is like a ledger that's been updated over time, with each generation of stars adding a bit more inventory to the heavy element columns. This means that the atoms in your body, in the ground beneath you, in the air you breathe, all pass through this long chain of events. The carbon in your cells was fused from helium in the core of a red, giant billions of years ago. The oxygen you inhale was produced in a massive star and ejected in a supernova. The calcium in your bones, the iron in your blood. These elements were forged in stellar interiors or in the shock waves of stellar explosions. The silicon in your phone, the gold in jewellery, the uranium in nuclear reactors, all manufactured through the same processes, then mixed into the gas cloud that collapsed to form the sun and the planets. Nothing about these atoms is recent. They're old products, cycled and recycled, used and redistributed, drifting through space for billions of years before ending up here. The timescales are almost incomprehensible. Stars take millions or billions of years to exhaust their fuel. Galaxies evolve over 10 billion years, slowly building up their chemical complexity. Planets form over tens of millions of years from the debris of earlier stellar generations. Human civilizations are barely visible on these timescales, a brief moment in which some of the recycled atoms have arranged themselves into self-aware structures capable of tracing their own origins. The universe did not rush to create complex chemistry. It followed a patient, rule-bound process. Hydrogen fuses into helium, helium into carbon and oxygen, and so on through the periodic table, with each step determined by temperature, pressure, and nuclear physics. Each step leaves measurable traces in the abundances of elements, in the light from stars, in the composition of planets. As you settle in for the night, consider that the universe's supply chain is still running. Stars are still fusing hydrogen into helium, still building up heavier elements in their cores. Supernovae are still exploding, distributing processed material into space. New stars and planets are still forming from enriched gas. The inventory is constantly being updated, recycled, and redistributed. The process is mostly invisible, operating on scales too large and too slow for direct observation, but the evidence is all around you. Every element, every atom is a product of this system. The periodic table is not a random assortment of substances. It's a catalogue of what the universe has manufactured over billions of years, using gravity, heat, and nuclear forces as its tools. The factory is always open, always processing, quietly building the material world one fusion reaction at a time, in the deep interiors of stars scattered across billions of light years, most of them too distant to see, but all contributing to the same vast, patient, orderly system that made everything, including you. Think about what this means for the objects in your immediate surroundings. The screen you're looking at contains silicon, processed from ancient supernovae, and sorted into semiconductor-grade purity through human refinement. The glass is silicon dioxide, oxygen, and silicon that were once separate atoms floating in different stellar shells before a supernova mixed them together. The metals, in the device, copper in the wiring, small amounts of gold in connectors, rare earth elements in the electronics, each have their own origin stories stretching back through the cosmic supply chain. Copper likely came from both supernovae and the slow neutron capture process in aging stars. The gold was almost certainly produced in a neutron-star merger, one of those rare, violent collisions that briefly outshine entire galaxies and scatter heavy elements across space. The water you drink has its own deep history. The hydrogen atoms in water are primordial, formed in the first minutes after the Big Bang, unchanged for 13 billion years except for being shuffled from one molecule to another. The oxygen atoms are younger, manufactured in massive stars that lived fast and died in supernovae perhaps 5 to 10 billion years ago. These atoms drifted through the galaxy, became incorporated into the molecular cloud that formed the solar system, and eventually ended up in Earth's oceans. Some of those water molecules evaporated, fell as rain, flowed through rivers, were absorbed by plants, consumed by animals, and cycled through countless organisms before arriving in your glass. But the atoms themselves, those particular hydrogen and oxygen nuclei, have been travelling for billions of years, following the path laid out by the cosmic supply chain. The same is true for the air you breathe. Nitrogen, which makes up most of the atmosphere, is produced primarily in massive stars through a combination of processes during their lives and explosive deaths. The oxygen in the air comes from the same stellar factories, ejected into space by supernovae and stellar winds. The tiny fraction of argon in the atmosphere has a different origin. Much of it is argon-40, produced by the radioactive decay of potassium-40 in Earth's rocks over billions of years. That potassium was itself made in supernovae, delivered to the early solar system, and incorporated into the planet during its formation. Even the trace amounts of carbon dioxide in the atmosphere connect to this story. The carbon was fused in red giants, the oxygen in more massive stars, and they were brought together in the molecular clouds that built the solar system. Consider your own body in this context. An average human contains roughly 28 elements in significant quantities, and traces of many more. About 65% of your body mass is oxygen, 18% is carbon, 10% is hydrogen, and 3% is nitrogen. These four elements alone account for 96% of your mass. The oxygen and carbon were manufactured in stars. The hydrogen is primordial. The nitrogen came from massive stars. The remaining 4% includes calcium for bones, phosphorus for DNA and cellular energy, potassium for nerve signals, sulfur for proteins, sodium and chlorine for fluid balance, magnesium for enzyme function, and iron for oxygen transport in blood. Every single one of these elements followed the same route, produced in a star or stellar explosion, ejected into space, mixed with interstellar gas, incorporated into the solar nebula, gathered into the planet, and eventually cycled through geological and biological processes until it ended up as part of you. The iron in your hemoglobin, the molecule that carries oxygen in your blood, was almost certainly produced in a supernova. Iron is created in the final stages of massive star evolution, in those last days before the core collapses. When the star explodes, the iron is scattered into space along with all the other elements the star produced. That iron drifted for millions or billions of years, eventually becoming part of the dust and gas that formed the solar system. It was incorporated into the rocky material that built Earth, cycled through the planet's geology, weathered out of rocks, absorbed by plants, consumed through the food chain, and now it sits in your bloodstream, binding to oxygen molecules and releasing them to your cells. The journey from the core of a dying star to the interior of a living organism took billions of years and involved countless intermediate steps, but the connection is direct and unbroken. The calcium in your bones has a similar story. Calcium is produced in massive stars through a combination of processes, particularly during explosive nucleosynthesis in supernovae. It's one of the products created when silicon fuses in the final stages of a massive star's life, or when intense heat and neutron flux during a supernova drives rapid nuclear reactions. Once ejected into space, calcium becomes part of the interstellar medium, mixes with other elements, and eventually gets incorporated into new planetary systems. On Earth, calcium cycles through rocks, soil, water, and living organisms. The particular calcium atoms in your skeleton right now have been through this cycle many times, locked in minerals, dissolved in ancient oceans, precipitated into shells and reefs, subducted into the mantle, returned to the surface through volcanism, weathered out of rocks again, and finally absorbed by your body to build and maintain bone structure. Even elements present in trace amounts tell the same story. Your body contains tiny amounts of copper, zinc, selenium, iodine, and other elements essential for various biological functions. Copper helps with energy production and iron metabolism. Zinc is crucial for immune function and wound healing. Selenium protects cells from oxidative damage. Iodine is necessary for thyroid hormone production. These trace elements, despite being present in such small quantities, are absolutely essential for life, and every single atom of them was produced in stars. Copper comes from supernovae and evolved stars. Zinc is made primarily in supernovae. Selenium is produced through neutron capture processes in massive stars. Iodine, being quite heavy, likely formed through rapid neutron capture in supernovae or neutron star mergers. The cosmic supply chain didn't just provide the bulk materials for life, it also delivered the precise trace components necessary for complex biological chemistry. This perspective extends to everything humanity has ever built or created. The metals in ancient bronze tools, copper and tin, were mined from Earth's crust, but they originated in stellar explosions billions of years ago. The iron in medieval swords, the lead in Roman plumbing, the silver in coins, all followed the same path from stellar cores to human hands. The aluminum in modern aircraft was produced in massive stars and is now one of the most common metals in Earth's crust. The titanium in spacecraft was forged in supernova explosions. The tungsten in light bulb filaments, the platinum in catalytic converters, the chromium in stainless steel, all products of the cosmic supply chain, delivered to this planet billions of years ago and now extracted, refined, and shaped by human industry for human purposes. The rare earth elements that make modern technology possible, neodymium in hard drives and electric motors, europium in display screens, terbium in solid-state devices, are among the more exotic products of stellar nucleosynthesis. Their production requires specific conditions, likely involving multiple processes including neutron capture in evolved stars and rapid neutron capture in supernovae or neutron star mergers. These elements are called rare not because they're genuinely scarce in the cosmic sense, but because they're dispersed and difficult to extract in concentrated form on Earth. Yet without them, much of our technology wouldn't function. The supply chain that delivered these elements to Earth billions of years ago made possible the technological civilization that emerged here much later. Even radioactive elements, which decay over time, connect to this story. Uranium, thorium, and potassium-40 are slowly decaying in Earth's interior, producing heat that drives plate tectonics and maintains the planet's magnetic field. These radioactive elements were produced in the most extreme nucleosynthesis events, supernovae and neutron star mergers, and delivered to the early solar system. They've been decaying ever since, but there's still enough left after 4.5 billion years to keep Earth's interior hot and geologically active. Without this residual heat from radioactive decay, Earth would be a cold, geologically dead world, with no plate tectonics, no volcanic activity, and probably no magnetic field to protect the atmosphere from solar wind. The fact that we live on an active planet is directly connected to the delivery of heavy radioactive elements by the cosmic supply chain. The distribution of elements in the solar system reflects the temperature gradient in the early solar nebula. Close to the young sun, only refractory materials, metals and rocky silicates, could condense. This is why Mercury, Venus, Earth and Mars are rocky planets with metallic cores. Farther out, beyond what's called the frost line, water ice could condense along with other volatile compounds. This allowed the formation of much larger planetary cores, which then attracted massive envelopes of hydrogen and helium to become Jupiter and Saturn. Even farther out, where temperatures were even lower, other ices like methane and ammonia could condense, contributing to Uranus and Neptune. The moons, asteroids and comets in the solar system also reflect this sorting. Rocky and metallic bodies in the inner system, icy bodies in the outer system, but all of it, from the innermost to the outermost, is built from the same set of elements delivered by the cosmic supply chain. Consider the asteroid belt between Mars and Jupiter. These rocky and metallic bodies are leftover building materials from the solar system's formation, pieces that never assembled into a planet because Jupiter's gravity disrupted the process. Different asteroids have different compositions. Some are mostly metal, probably fragments of the cores of larger bodies that were shattered in collisions. Some are rocky, made of silicate minerals. Some are carbonaceous, rich in carbon compounds and water-bearing minerals. By studying asteroids, scientists can learn about the distribution and composition of materials in the early solar nebula. The elements in asteroids are the same ones produced in stars, but they're preserved in a relatively primitive state, not extensively processed by geological activity the way materials on Earth have been. Comets tell a similar story from a different part of the solar system. These icy bodies formed in the outer solar system, where temperatures were low enough for water, methane, ammonia, and carbon dioxide to freeze. When a comet approaches the Sun, these ices sublimate, creating the characteristic tail. Analysis of comet composition reveals a mix of water ice, frozen gases, rocky dust, and complex organic molecules. Some of the organic molecules found in comets are quite complex, including amino acids, the building blocks of proteins. These molecules formed through chemical reactions in the cold environment of the outer solar system, but the atoms they're built from, carbon, hydrogen, oxygen, nitrogen, were all delivered by the cosmic supply chain. Comets may have played a role in delivering water and organic compounds to Earth early in its history, seeding the planet with some of the raw materials for life. The interstellar medium, the gas and dust between stars, is where much of the recycling happens. When supernovae explode, stellar winds blow off outer layers, or neutron stars merge, the ejected material doesn't immediately form new stars. It expands into the surrounding space, cools, and mixes with existing gas. Over time, the kinetic energy from the explosion dissipates, and the material settles into equilibrium with the rest of the interstellar medium. This gas is not uniform. It has different phases with different temperatures and densities. There's hot ionized gas heated by supernova shocks. There's warm neutral gas. There's cold molecular gas where new stars can form. Elements produced in stars gradually spread through these different phases, mixing and blending until the gas reaches a more uniform composition. The mixing process is important because it ensures that new stars forming in a given region inherit a representative sample of all the elements produced by previous generations. If elements didn't mix well, some regions might be enriched in certain elements while being depleted in others. But observations show that, on large scales, the chemical composition of the interstellar medium is fairly uniform within a galaxy, though it does vary between different galaxies and between different regions within a galaxy. This uniformity is the result of billions of years of mixing, with supernova explosions and stellar winds stirring the interstellar medium and spreading elements throughout the galactic disk. Molecular clouds, the dense regions where new stars form, are particularly interesting from a chemical perspective. In these cold, dense environments, atoms and simple molecules can stick to dust grains and undergo chemical reactions on the grain surfaces. This surface chemistry can produce complex molecules that wouldn't easily form in the gas phase. Observations of molecular clouds have revealed hundreds of different molecules, ranging from simple two-atom molecules like carbon monoxide to complex organic molecules with dozens of atoms. Many of these molecules contain carbon, which is abundant thanks to stellar nucleosynthesis, and which has the chemical versatility to form a huge variety of compounds. The molecular clouds, where stars and planets form, are not just gravitational structures. They're chemically rich environments where the elements delivered by the cosmic supply chain begin combining into more complex forms. When a new star forms inside a molecular cloud, the process is gradual. Gravity causes a dense core within the cloud to contract. As the core shrinks, it heats up, but it also radiates energy away, so the contraction continues. Material from the surrounding cloud falls onto the growing protostar, and as it falls, it forms a rotating disk around the star. This disk is where planets will eventually form. The disk inherits the chemical composition of the molecular cloud, which means it contains all the elements produced and distributed by previous generations of stars. The composition of the disk, how much carbon, oxygen, silicon, iron, and other elements it contains, will determine what kinds of planets can form and what those planets will be made of. Different stars form in different environments with different chemical compositions, and this affects their planetary systems. A star forming in a region enriched by recent supernovae might have more heavy elements in its disk, potentially leading to larger rocky planets. A star forming in a relatively metal-poor region might have less material available for planet formation, potentially resulting in smaller planets or fewer planets overall. Observations of exoplanets, planets around other stars, have revealed a wide variety of planetary systems, and part of that variety is likely due to differences in the chemical composition of the disks from which the planets formed. The cosmic supply chain doesn't deliver the same mixture everywhere. There are variations, and those variations have consequences for the types of worlds that form. Earth's geological history is a story of chemical processing and recycling on a planetary scale. When the planet formed, it was hot and largely molten. Heavy elements like iron and nickel sank to the centre, forming the core. Lighter elements rose to form the mantle and crust. This differentiation created a layered structure with different chemical compositions at different depths. Over billions of years, plate tectonics has continued to process and recycle crustal material. Oceanic crust forms at mid-ocean ridges, spreads across the ocean floor, and eventually subducts back into the mantle at ocean trenches. When it subducts, it carries water and other compounds down with it. Some of this material melts and rises back to the surface through volcanism, completing the cycle. The elements in Earth's crust are constantly being recycled through this system, moved from one location to another, transformed from one mineral to another, but the atoms themselves, the nuclei that were produced in stars billions of years ago, remain unchanged through all these processes. The water cycle is another example of planetary scale recycling. Water evaporates from oceans, lakes and rivers, rises into the atmosphere, condenses into clouds, and falls as precipitation. It flows through rivers back to the ocean, infiltrates into groundwater, or gets locked in ice sheets. Over geological time, water has been subducted with oceanic crust, released by volcanic activity, and cycled between the surface and the interior. The hydrogen and oxygen atoms in water molecules are constantly being reshuffled, broken apart and recombined through chemical and biological processes, but the atomic nuclei themselves remain the same. The hydrogen is still primordial, 13 billion years old. The oxygen was made in a star billions of years ago. They've been paired and unpaired countless times, but their fundamental identity as hydrogen and oxygen hasn't changed. Living organisms add another layer of recycling. Plants absorb carbon dioxide from the atmosphere and water from the soil, using sunlight to synthesize sugars. Animals eat plants or other animals, breaking down complex molecules and using the atoms to build their own tissues. When organisms die, decomposers break down their remains, releasing elements back into the soil, water and atmosphere. The carbon cycle, nitrogen cycle, phosphorus cycle, and other biogeochemical cycles all describe how elements move through living and non-living systems on Earth. But underneath these cycles, the atoms themselves are unchanged. The carbon atom in a sugar molecule in a plant today might have been in a dinosaur's body millions of years ago, in ancient marine organisms hundreds of millions of years before that, and in the early Earth's atmosphere billions of years before that. Before arriving on Earth, it was in interstellar space. Before that, it was fused in the core of a red giant star. The cosmic supply chain delivered it here, and planetary processes have been shuffling it around ever since. The concept of chemical evolution applies not just to individual galaxies but to the universe as a whole. In the very early universe, immediately after the Big Bang, there were no heavy elements at all, just hydrogen, helium, and traces of lithium and beryllium. The first stars that formed, called population 3 stars, were made purely from this primordial gas. These stars have never been directly observed because they formed so long ago and were likely quite massive, living fast and dying in supernovae. But their existence is inferred from theoretical models and from the observation that even the oldest stars we can see contain at least tiny amounts of heavy elements, indicating they formed from gas that had already been enriched by earlier stars. Those first stars began the process of chemical enrichment, manufacturing heavy elements and distributing them through supernovae. Subsequent generations of stars continued the process, each one incorporating more heavy elements and producing even more. This means the universe is becoming chemically richer over time. The proportion of hydrogen is slowly decreasing as it gets converted into helium and heavier elements. The proportions of carbon, oxygen, silicon, iron, and all the other heavy elements are slowly increasing. This process will continue as long as stars keep forming and dying. Eventually, far in the future, if star formation continues and eventually ceases as the universe runs out of gas, the final state will be a universe where a significant fraction of the original hydrogen has been converted into heavier elements, locked up in cold stellar remnants, planets, and other dense objects. The supply chain will eventually shut down, not because it runs out of hydrogen entirely, but because the gas becomes too dispersed and the universe too cold for new stars to form. But that endpoint is trillions of years in the future. For now, the supply chain is still operating, and if you could somehow see it in action, you'd witness a vast distributed network of processes, all contributing to the same outcome: the gradual transformation of simple matter into complex chemistry. Every star is a production node in this network. Every supernova is a shipping event. Every molecular cloud is a mixing and storage facility. Every planet is an assembly of finished products. And every living organism, including you, is a temporary arrangement of atoms that have passed through this system, organized by biological processes into a structure capable of metabolism, growth, reproduction, and in some cases, awareness of its own existence and origins. The periodic table, that familiar chart hanging in classrooms and laboratories, is more than just a catalogue of elements. It's a record of what the universe can make, given enough time and the right physical conditions. The elements are not arbitrary. Their properties are determined by their atomic structure: how many protons and neutrons in the nucleus, how many electrons in the outer shells. This structure, in turn, is determined by nuclear and atomic physics. The universe doesn't create elements randomly. It creates them in a specific order, determined by how nuclear fusion proceeds in stellar cores and how neutron capture builds up heavy nuclei. The supply chain is rule-bound, constrained by the laws of physics, and the result is the periodic table, a systematic arrangement of elements that reflects the nuclear processes that made them. Understanding this supply chain has been one of the great achievements of 20th and 21st century science. It required bringing together nuclear physics, astronomy, geology, chemistry, and other disciplines. It required understanding how stars work, how they evolve, and how they die. It required careful spectroscopic measurements of stars and gas clouds to determine element abundances. It required computer models of stellar interiors and supernova explosions to predict how elements are produced. It required laboratory experiments to measure nuclear reaction rates under extreme conditions. And it required geological and meteoric analysis to determine the composition and age of the solar system and its components. The story of the cosmic supply chain is not speculation or mythology. It's a scientific reconstruction based on decades of careful observation, measurement, and calculation. The precision of this understanding is remarkable. Scientists can now predict with reasonable accuracy how much of each element a star of a given mass will produce during its lifetime and explosive death. They can calculate the yields from neutron star mergers and compare them to observations of these events, which have only been detected in recent years through gravitational wave observatories and electromagnetic follow-up. They can measure the composition of ancient stars and use that data to infer the production rates of elements in the early universe. They can analyze meteorites to determine the isotopic composition of the early solar system and use that information to constrain models of nucleosynthesis. The whole framework fits together with internal consistency, each piece of evidence supporting the others, each measurement refining the overall picture. Isotopes add another layer of detail to this story. Many elements exist in multiple forms with the same number of protons but different numbers of neutrons. These different isotopes are produced through different processes and in different proportions. For example, oxygen has 3 stable isotopes: oxygen-16, oxygen-17, and oxygen-18. Oxygen-16 is by far the most abundant, produced primarily in massive stars through helium burning. Oxygen-17 and oxygen-18 are produced in smaller quantities through different nuclear pathways. By measuring the ratios of these isotopes in various materials, meteorites, minerals, stellar atmospheres, scientists can learn about the specific conditions and processes that produce them. Isotope ratios serve as fingerprints, traceable markers that reveal the history of the material. Carbon has 2 stable isotopes, carbon-12 and carbon-13. Carbon-12 is produced directly during helium burning in stars when 3 helium nuclei fuse together. Carbon-13 is produced through different nuclear pathways, particularly in hydrogen-burning regions of stars, through a process called the CNO cycle, where carbon, nitrogen and oxygen serve as catalysts for hydrogen fusion. The ratio of carbon-13 to carbon-12 in a sample can indicate the conditions under which the carbon was produced and processed. On Earth, biological processes preferentially use carbon-12, so organic materials tend to have slightly lower carbon-13 ratios than inorganic carbonates. This isotopic signature can be used to identify ancient biological activity in rocks, a technique that has been applied to some of the oldest rocks on Earth to search for signs of early life. Iron has 4 stable isotopes, each with slightly different abundances. The most common is iron 56, which sits at the peak of nuclear binding energy, the most stable nucleus per nucleon. Iron 54, iron 57 and iron 58 are also stable but less abundant. These isotopes are produced in slightly different proportions depending on whether they form through normal stellar nucleosynthesis, explosive nucleosynthesis in supernovae, or neutron capture processes. By measuring iron isotope ratios in meteorites and in Earth materials, scientists can learn about the mix of sources that contributed to the solar system's iron inventory. Some of it came from multiple generations of stars, blended together in the molecular cloud that formed the Sun. The heavy elements beyond iron have even more complex isotope patterns. Gold, for instance, has only one stable isotope, gold 197. This isotope is produced almost exclusively through rapid neutron capture in extreme environments like neutron-star mergers. The fact that gold has only one stable isotope and requires such specific conditions to form is part of why it's relatively rare and valued. Lead has 4 stable isotopes, 3 of which are the end products of radioactive decay chains starting with uranium and thorium. Lead-204 is the only isotope not produced by radioactive decay, and its presence in a sample indicates primordial lead that was present when the solar system formed. By measuring the ratios of these lead isotopes, along with uranium and thorium, scientists can determine the ages of rocks and meteorites, a technique that has revealed the 4.567 billion year age of the solar system. Radioactive isotopes that haven't fully decayed yet provide additional clues. When the solar system formed, it incorporated various radioactive isotopes produced in stars and stellar explosions. Most short-lived isotopes have completely decayed by now, but their presence in the early solar system can be inferred from the daughter products they left behind. Aluminum-26, for example, has a half-life of only 720,000 years. Any aluminum-26 present when the solar system formed has long since decayed to magnesium-26. But by measuring excess magnesium-26 in meteorite samples and comparing it to aluminum-27, the stable isotope of aluminum, scientists can determine that aluminum-26 was indeed present in the early solar system. This indicates that the solar system incorporated material from a relatively recent supernova or stellar wind, delivered to the molecular cloud shortly before it collapsed to form the Sun. The presence of short-lived radioactive isotopes in the early solar system has another implication. It provided a heat source for small bodies like asteroids. As these isotopes decayed, they released energy, warming the interiors of asteroids and, in some cases, causing them to melt and differentiate into cores and mantles like miniature planets. This early heating affected the geological evolution of these bodies and influenced what kinds of meteorites would eventually reach Earth. The cosmic supply chain didn't just deliver raw elements, it delivered them in a particular isotopic mix that included radioactive components, and those components had active effects on how solid bodies formed and evolved. The study of presolar grains found in meteorites provides direct samples of material from individual stars. These are tiny dust particles, a few micrometers across, that formed in the atmospheres or outflows of stars before the solar system existed. They became incorporated into the molecular cloud that formed the Sun and were then included in asteroids and comets. When meteorites from these bodies fall to Earth, scientists can extract and analyze these presolar grains. Their isotopic compositions are wildly different from average solar system material, showing the unique signatures of the specific stars they came from. Some grains came from red giants rich in carbon, others came from supernovae. Each grain is a preserved sample of stellar nucleosynthesis, a tiny piece of a distant star carried across space and time. Analysing presolar grains is challenging because they're so small and rare, but the information they provide is extraordinary. They offer direct confirmation that different stars produce different isotopic patterns, exactly as models predict. They reveal details about the nuclear reactions happening in stellar interiors and explosions. They show that the solar system's material came from a mix of many sources, not just one or two, and they demonstrate that at least some stellar ejecta can survive intact for millions of years in the interstellar medium, retaining their distinct compositions even while being mixed with other material. These grains are messengers from the cosmic supply chain, tangible evidence of the processes that made the elements. The distribution of elements across the universe is not perfectly uniform, even though mixing in the interstellar medium tends to even things out. Some galaxies are more metal-rich than others, depending on their star formation history. Galaxies that have been actively forming stars for billions of years have higher abundances of heavy elements. Galaxies with low star formation rates remain more metal-poor. Within a single galaxy, there are also variations. The central regions, where star formation has been more intense, tend to be more enriched than the outer regions. Observations of element abundances in different parts of different galaxies allow astronomers to trace the history of star formation and chemical enrichment across cosmic time. Intergalactic gas, the thin material between galaxies, also contains heavy elements. These were likely ejected from galaxies by powerful outflows driven by supernova explosions and supermassive black hole activity. When many supernovae explode in a relatively small region, their combined energy can drive a galactic wind that pushes gas out of the galaxy entirely. This gas, enriched with heavy elements from the stars that produced it, spreads into intergalactic space. Over time, it may fall back into galaxies or remain dispersed in the vast spaces between them. This means the cosmic supply chain operates not just within galaxies but across intergalactic distances, redistributing elements on the larger scales. The ultimate fate of the elements depends on the future evolution of the universe. Current understanding suggests the universe will continue expanding forever, gradually cooling and thinning. Star formation will continue for many billions of years as long as gas remains available, but eventually the gas supply will be exhausted. Stars will burn out, leaving behind white dwarfs, neutron stars and black holes. Planets will orbit dead stars in cold, dark systems. The elements locked up in these cold remnants will no longer be accessible for recycling. The supply chain will have shut down, not because it ran out of hydrogen entirely, but because the remaining hydrogen is too dispersed to collapse and form new stars. In this far future, the universe will still contain all the elements that were ever made, but they'll be locked in static, unchanging forms, no longer cycling through stars and planets. But this endpoint is so far in the future, trillions of years, that it's almost beyond comprehension. For all practical purposes, on human timescales, and even on the timescales of current galactic evolution, the supply chain is permanent. It has been running for 13 billion years and will continue running for many billions more. The processes that made the atoms in your body are still operating right now, in stars throughout the universe. Somewhere a red giant is fusing helium into carbon. Somewhere a massive star is building up iron in its core, days away from collapse. Somewhere a supernova is ejecting freshly made elements into space. Somewhere, two neutron stars are spiraling toward merger, about to produce a burst of heavy elements. Somewhere, a molecular cloud enriched with these elements is collapsing to form new stars and planets. The cycle continues, indifferent to observers, driven by physics and gravity, slowly transforming the composition of the universe one atom at a time. This perspective changes how you might think about material objects, and even about yourself. The atoms you're made of are not merely old, they're ancient, older than the solar system, older than Earth, participants in a process that's been running since the universe's first stars ignited. You are not separate from the cosmos, you're an instance of it, a local concentration of atoms that have been cycling through the supply chain for billions of years, temporarily arranged in a pattern that can think and wonder about its own origins. The same is true for everything around you. Nothing is fundamentally separate. Everything is connected through the history of the elements, through the shared experience of having been processed in stellar cores, ejected through space, mixed in interstellar clouds, gathered into planets, and assembled into temporary forms. There's something deeply calming about this view. It removes the arbitrary boundaries we often draw between ourselves and the rest of existence. The carbon in your cells is not your carbon in any permanent sense. It's borrowed, temporarily organized into biological molecules, and it will eventually return to the environment when you die, to be used by other organisms or locked in sediments or released into the atmosphere. The same is true for every element in your body. You're not a fixed, permanent entity. You're a pattern, a process, a temporary configuration of atoms that have been here far longer than you and will be here far longer after you're gone. This isn't diminishing, it's grounding. It places you in the context of something vast, ancient, and ongoing. The fact that we can know this story, that we can trace the origins of atoms from the Big Bang through stellar cores to our own bodies, is itself remarkable. It required the development of physics, chemistry, astronomy, and geology as coherent scientific disciplines. It required powerful telescopes to observe distant stars and galaxies. It required particle accelerators to study nuclear reactions. It required space missions to analyze other planets and asteroids. It required careful, systematic, observation and theoretical work spanning more than a century. And the result is a coherent, evidence-based narrative that explains where everything came from. This knowledge is one of humanity's great intellectual achievements, a deep understanding of nature's manufacturing process. As you lie here tonight, the universe continues its work. Light from distant stars carrying spectral signatures of their elemental composition travels through space toward Earth. Some of that light, having journeyed for millions or billions of years, enters telescopes and spectrographs, where it's analysed to determine what those stars are made of. Other stars are in their final days, fusing silicon into iron, approaching the moment of collapse. Still others are in their prime, steadily converting hydrogen to helium, maintaining the equilibrium that will last for billions of years. And in molecular clouds scattered throughout galaxies, new stars are beginning to form from gas enriched by all the stars that came before. The inventory is being updated continuously, never static, always in motion. The same processes that made the elements made the conditions for life. Carbon-based chemistry is possible because stars produce abundant carbon. Water is abundant because stars produce abundant oxygen, which combines with primordial hydrogen. The elements essential for life, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, and various metal ions, are all products of stellar nucleosynthesis. Life as we know it is built from the inventory provided by the cosmic supply chain. If the universe had produced different proportions of elements, or if certain elements were missing entirely, the chemistry of life would be different or impossible. We exist because the supply chain operates the way it does, producing elements in the particular proportions that allow complex chemistry to emerge. This raises the question of whether life exists elsewhere. Given that the same supply chain operates throughout the universe, delivering roughly similar mixes of elements to planetary systems everywhere, the raw materials for life should be common. Every star forms from gas that contains carbon, oxygen, nitrogen, and other essential elements. Every planetary system should have access to these materials. Whether the specific conditions necessary for life, liquid water, stable climates, protection from radiation, are common or rare remains an open question, but the chemical prerequisites are definitely widespread. The periodic table is universal. The same elements exist everywhere, produced by the same processes. Any life elsewhere in the universe, if it exists, is built from the same catalogue of atoms we are, delivered by the same supply chain. Even the empty spaces between stars are not truly empty. The interstellar medium contains about 1 atom per cubic centimetre on average, mostly hydrogen, but with traces of heavier elements mixed in. This tenuous gas is what stars form from and what stellar explosions enrich. It's constantly being stirred and mixed by stellar winds, supernova shocks, and galactic rotation. Over time, this mixing ensures that the composition becomes relatively uniform, so that new stars forming in different parts of a galaxy have access to similar mixtures of elements. The interstellar medium is like the warehouse space in the cosmic supply chain, the storage area where materials wait between production and assembly, slowly mixing and homogenizing. Dust grains in the interstellar medium deserve special mention. These tiny solid particles, smaller than the particles in smoke, form when gas cools in stellar atmospheres and outflows. They're made of various materials depending on the composition of the gas: carbon grains, silicate grains, iron grains, ice-coated grains. These dust grains play several important roles. They absorb and scatter starlight, creating the dark lanes visible in images of galaxies. They provide surfaces where atoms and molecules can meet and react, enabling chemical processes that wouldn't occur efficiently in the gas phase, and they serve as condensation nuclei in collapsing molecular clouds, helping to grow larger solid particles that eventually become asteroids and planets. Dust grains are intermediaries in the supply chain, solid aggregates of heavy elements bridging the gap between stellar production and planetary assembly. When you look at a night sky in a dark location, away from city lights, you see stars scattered across the darkness. Each of those points of light is a stellar factory, processing hydrogen and helium, and, in many cases, producing heavier elements. The light you're seeing is the byproduct of fusion, the energy released when lighter nuclei combine into heavier ones. That light travels across space, sometimes for years or centuries or millennia, until it reaches your eye. In that moment of perception, there's a direct connection between you and that distant stellar core, mediated by photons that were produced by the same nuclear processes that made the atoms in your body. You are quite literally looking at the mechanism that created you, seeing the light from factories that made the materials you're built from, or ones very much like them. The Milky Way, our home galaxy, contains somewhere between 100 and 400 billion stars. Each is at a different stage in its life, from newly formed protostars still gathering mass to ancient white dwarfs that burned out billions of years ago. At any given moment, thousands of stars are being born from collapsing molecular clouds. Dozens are exploding as supernovae, ejecting their processed material into space. Trillions of planets orbit these stars, each made from the inventory available in their particular stellar neighborhood. The galaxy is a vast distributed production and recycling facility, operating continuously for over 13 billion years, and it will continue for billions more. Other galaxies, visible through telescopes, are similar systems, each with its own population of stars and its own history of chemical evolution. Some are more active, with high rates of star formation and frequent supernovae. Others are quieter, with most of their star formation in the past and an aging stellar population. But all operate according to the same physical principles, running the same cosmic supply chain, producing the same set of elements. The universe is full of these factories, numbering in the hundreds of billions of observable galaxies, each containing tens or hundreds of billions of stars. The scale is almost unimaginable, but the process is the same everywhere. Gravity gathers gas, fusion converts elements, explosions distribute the products, mixing homogenizes the composition, and new cycles begin. This is not a story about extraordinary events or miraculous processes. It's a story about ordinary physics playing out over extraordinary timescales. Gravity is not mysterious, it's a fundamental force that attracts mass. Fusion is not magical, it's a nuclear process governed by well-understood principles. Stellar evolution is not unpredictable. It follows patterns determined by mass, composition, and rotation. The whole supply chain is mechanistic, operating according to rules that can be written down and tested. And yet, from these simple rules, applied over billions of years, emerges everything. Galaxies, stars, planets, oceans, atmospheres, life, consciousness, civilizations, art, science, everything that has ever existed or will exist. The cosmos manufactures complexity from simplicity, not through design, but through patient, rule-bound processes operating at enormous scale. As the night deepens and you drift towards sleep, the atoms in your body remain in constant motion. Electrons orbit nuclei. Molecules vibrate and rotate. Chemical reactions proceed in your cells, breaking down nutrients, assembling proteins, repairing damage, maintaining the pattern that is you. The atoms themselves, the nuclei, are stable, unchanged by these chemical processes, ancient and durable. They have been through stellar cores, through explosive shock waves, through cold molecular clouds, through the hot early solar system, through billions of years of geological cycling on Earth, through countless organisms before you. They will continue long after you, cycling through other forms, other structures, other temporary arrangements. You're a moment in their journey, a brief configuration in the endless flow of matter through the universe's supply chain. The universe made atoms slowly, patiently, without urgency or intention, simply following the rules of physics wherever they led. The result is the periodic table, a catalogue of possible atomic structures, each produced through specific processes at specific times. From that limited catalogue, fewer than 100 naturally occurring elements, comes everything else. Minerals, crystals, metals, gases, liquids, complex molecules, biological structures, ecosystems, civilizations. The universe is remarkably efficient in what it can build from a small set of fundamental components. The diversity of matter, from neutron stars to butterflies, all emerges from different arrangements of the same basic atoms, produced by the same cosmic supply chain, distributed by the same mechanisms, assembled by gravity and chemistry into every structure that exists. Tonight is just an accounting exercise, an inventory check, a calm review of where things came from and how they got here. The universe has been running its supply chain for 13 billion years, converting hydrogen into everything else, one fusion reaction at a time, distributing products through space, recycling them into new generations of stars and planets, building complexity gradually from simple beginnings. The process continues, uninterrupted, indifferent to observers, driven by nothing more than gravity and nuclear physics. And you, lying here tonight, are one small result of that process, made from atoms that carry the entire history of the cosmos in their nuclei, temporary but connected, finite but part of something vast and ongoing. The warehouse never closes, the inventory keeps updating, and somewhere out in the darkness, another star is fusing elements right now, adding to the universal stock that made you and everything around you. The next story is about to begin. Please relax and enjoy. Tonight we're checking a very old signal, a faint background hum that fills all of space. Astronomers call it the cosmic microwave background, the CMB, and they treat it less like a mysterious omen and more like a carefully archived data set, full of maps and tables and graphs. It's simply the oldest light we can see, stretched out and cooled down over billions of years, waiting to be read like a long, slightly noisy report about how the universe began. There's nothing dramatic about it on the surface, just a persistent glow that's been travelling for so long that it's become part of the furniture of existence itself. But if you look at it closely enough, with the right instruments and enough patience, it tells you almost everything worth knowing about the early universe. The story begins shortly after the Big Bang, when the universe was hot and dense and filled with a mixture of photons, particles of light, along with electrons and atomic nuclei. Everything was packed together so tightly that light couldn't travel far before bumping into something. The photons kept scattering off free electrons, bouncing around constantly like someone trying to walk through a crowded room in the dark. The universe was like a thick fog where light existed everywhere, but couldn't move in a straight line. You could think of it as being trapped in a glowing, opaque soup, where every direction looked the same because nothing could see more than a tiny distance. The CMB existed then as trapped energy, part of that uniform brightness, unable to escape or travel freely. As the universe expanded, it cooled. That's just what happens when space gets bigger. The energy spreads out, temperatures drop, and things that were once too hot to settle down finally get a chance to organise themselves. Eventually, the universe reached a temperature where electrons could bind with nuclei to form neutral atoms, mostly hydrogen and helium. This process is called recombination, though that's a bit of a misnomer since the electrons and nuclei had never been combined before, but the name stuck. And what matters is that once recombination happened, most of those free electrons that had been scattering light were suddenly locked up inside atoms. Without all those free electrons in the way, photons could travel much farther without being deflected. The universe transitioned from opaque to transparent, not with a dramatic flash or sudden clearing, but with a gradual lifting of the cosmic fog. It's not that the light turned on, it's that the obstruction finally moved out of the way. The moment when this happened is called the surface of last scattering, which sounds technical, but just means the last time most of the CMB photons interacted strongly with matter. After recombination, these photons began streaming freely through space in all directions, and they've been travelling ever since. The light we see today as the CMB is essentially a snapshot of that moment, preserved and carried forward as the universe expanded around it. It's not a picture taken by a camera, but a fossil glow originating when the universe was around 380,000 years old, very young compared to its current age of nearly 14 billion years. Imagine taking a photograph of a room, and then watching that photograph age while the room itself continues to change. The CMB is like that photograph, except the room is the entire universe, and the photograph is made of light. Here's where things get interesting in a quiet, technical way. The photons released at last scattering started out in the visible or infrared range, glowing with the kind of light you might expect from something extremely hot. But as space expanded, it stretched the wavelength of the light itself. This isn't some metaphorical stretching, it's a real physical effect. As the fabric of space expands, it pulls the wavelengths along with it, making them longer and longer. Longer wavelengths mean lower energy, so over billions of years, those originally bright photons have been stretched into microwaves. Today, they correspond to a temperature of about 2.7 degrees above absolute zero. The photons didn't lose heat in the way a cup of coffee cools down by transferring energy to its surroundings. They cooled because the space carrying them grew larger, diluting their energy across a bigger volume. The discovery of the CMB was almost accidental, in the way many important discoveries are. Two engineers, Arno Penzias and Robert Wilson, were working with a radio antenna in New Jersey in the 1960s, trying to use it for satellite communications. They kept picking up a persistent noise they couldn't eliminate. It didn't matter what time of day it was, what season, or how much they cleaned the equipment, even scrubbing out the pigeon droppings that had accumulated in the antenna. The noise remained, a faint hiss coming from every direction in the sky. At first it was just annoying, the kind of problem you'd expect to solve with better shielding or by repositioning the antenna. Only later did they learn, after consulting with physicists, that they were picking up microwaves from the cosmic background itself. This annoying static turned out to be the universe's oldest, most widespread signal, a discovery made as much by troubleshooting as by grand theoretical design. Once scientists realized what they were looking at, they measured the CMB more precisely and found something remarkable. The spectrum of the radiation, the way its intensity varies with wavelength, matched almost perfectly with what's called a blackbody spectrum. A blackbody is a theoretical object that absorbs all radiation falling on it and emits radiation in a specific pattern depending only on its temperature. Real objects approximate this behavior to varying degrees, but the CMB turned out to be one of the most perfect blackbodies ever measured. Its temperature was about 2.7 Kelvin, and the smoothness of the spectrum across the sky was striking. This near-perfect blackbody curve confirmed that the early universe was once hot, dense, and extraordinarily uniform. In the scientific logbook, it became one of the cleanest entries. Background temperature around 2.7 Kelvin, blackbody-like, consistent with a hot Big Bang. By the late 20th century, scientists wanted better measurements. The Cosmic Background Explorer satellite, known as COBE, launched in 1989 with two major tasks. First, confirm the blackbody spectrum with high precision. Second, look for tiny variations in temperature across the sky. The spectrum measurement went extremely well, matching theoretical predictions so closely that it was almost eerie. The temperature map, though, was more challenging. At first, the sky looked almost perfectly uniform, with only a few large-scale features visible. One of these was a dipole pattern, a slight warming in one direction and cooling in the opposite direction, caused by our own motion through space. The Milky Way and the local group of galaxies are moving relative to the rest frame defined by the CMB, and this motion creates a Doppler shift that shows up as a temperature difference. Useful information, but not what cosmologists were most excited about. After subtracting the effects of our local motion and emissions from our own galaxy, COBE revealed something more subtle. Small temperature fluctuations in the CMB at the level of tens of microkelvin. These tiny ripples represented regions that were slightly denser or less dense in the early universe. If the universe had been perfectly uniform, gravity would have had nothing to work with, no seeds to grow into the galaxies and clusters we see today. But these small imperfections gave gravity something to grab onto. Over time, the denser regions attracted more matter, while the less dense regions became voids. Visually, the map looked like a mottled pattern of slightly warmer and cooler spots. Nothing dramatic to the untrained eye, but scientifically it was incredibly rich. It was the first clear indication that the early universe carried just enough structure, just enough departure from perfect smoothness, to eventually form the cosmic web of galaxies we observe. The next step in refining these measurements came with the Wilkinson Microwave Anisotropy Probe, WMAP, which launched in 2001. WMAP provided much higher resolution than COBE and collected data over several years, building up a detailed, high-quality map of the entire sky. The result was a pixelated temperature map where each pixel represented a small patch of sky. and carried a value indicating how much warmer or cooler that region was compared to the average. From these patterns, cosmologists could extract statistical information about the universe's age, composition, and geometry. The era of precision cosmology had arrived, moving beyond simple detection into careful parameter estimation. Then came Planck, launched by the European Space Agency in 2009. Planck was even more sensitive and observed the CMB at multiple frequencies, which allowed scientists to carefully separate the true cosmic background from foreground emissions like dust and gas in our own galaxy. The final Planck maps show an intricate pattern of fluctuations, each tiny colour difference corresponding to a small temperature variation of just a few hundred microkelvin. To the eye, when you see these maps in popular science articles, they look like colourful ovals with splotches of red, blue and yellow. To cosmologists, they're dense datasets from which you can extract power spectra, a compact, mathematically precise way of summarising the pattern of fluctuations across different angular scales. Planck's results refined the values of key cosmological parameters with impressive precision, narrowing down uncertainties that had been much larger just a decade before. Understanding how scientists convert a complex sky map into useful numbers requires a bit of explanation, but it's not as abstract as it sounds. Imagine you have a photograph of a textured surface, maybe a close-up of fabric or a section of wall. You could describe that texture in words, but a more precise way would be to measure how much the brightness varies at different scales. Are there large patches of similar colour, or is the variation mostly at small scales? The CMB analysis works the same way. Scientists compute what's called a power spectrum, which is essentially a graph showing how strong the temperature fluctuations are at different angular scales across the sky. These scales are labelled by something called the multipole number, which is just a way of quantifying the size of features. Low multipole numbers correspond to large-scale features spanning big chunks of the sky, while high multipole numbers correspond to small-scale features. The power spectrum is where the real information lives. It's not that every individual pixel on the sky map is unimportant, each one represents a real measurement, but the overall pattern is what tells you about the physics. The spectrum has peaks and troughs, and these aren't random. They reflect physical processes that were happening in the early universe, specifically acoustic waves in the hot plasma. Before recombination, the universe was filled with this plasma of photons, electrons and nuclei, and it behaved somewhat like a fluid. Regions of higher density would attract more matter through gravity, but the pressure from all those packed-in photons and particles would push back. This created oscillations, sound waves travelling through the plasma, with regions alternately compressing and expanding. When recombination happened and the photons decoupled from the matter, these oscillations were effectively frozen in place, leaving an imprint in the CMB as a pattern of slightly hotter and cooler spots. What were, once travelling sound waves became a static temperature map, like recording a song and then analysing its waveform long after the music has stopped playing. The positions and heights of the peaks in the power spectrum depend on several key parameters. The first peak, for instance, is sensitive to the total density of matter and energy in the universe, and to the curvature of space itself. If space is flat, the peak appears at a certain position. If space has positive or negative curvature, the peak shifts. The second and third peaks tell you about the balance between ordinary matter and dark matter, and about the physical conditions in the plasma, like how much pressure the photons were exerting. By fitting theoretical models to the observed power spectrum, scientists can infer the best fit values for things like the Hubble constant, the density of dark matter, the density of ordinary matter, the amount of dark energy, and the age of the universe. It's an inverse problem. You observe the pattern and work backward to figure out what combination of parameters would produce that pattern. The numbers that come out of this process are impressively precise. The universe is approximately 13.8 billion years old. About 68% of its total energy content is dark energy, 27% is dark matter, and only about 5% is the ordinary matter that makes up stars, planets, and people. Space appears to be flat or very close to it. Within the measurement uncertainties, these aren't wild guesses. They're constrained by the detailed shape of the power spectrum and by the consistency of the data with theoretical predictions. In the logbook, the CMB allows scientists to fill in a detailed summary, numbers extracted from analysing a faint hum. It's worth pausing to appreciate that the peaks in the power spectrum represent frozen sound waves. Before recombination, the universe was filled with plasma oscillating under the competing influences of gravity and radiation pressure. Dense regions would collapse inward due to gravity, but the pressure from tightly packed photons would resist and push back, causing the region to expand again. This created oscillations at different scales, with some regions going through one full cycle of compression and expansion, others going through 2 cycles, and so on. When recombination occurred, the photons suddenly streamed away, and the matter was left behind in whatever configuration it happened to be in at that moment. The CMB carries the imprint of those oscillations because the photons that decoupled from denser, hotter regions have slightly higher energy, and thus appear slightly warmer, than photons from less dense, cooler regions. Sound converted into a temperature map, a record of vibrations that happened nearly 14 billion years ago. Of course, the CMB signal isn't the only thing present in the microwave sky, and extracting the true cosmic background from everything else is a major challenge. Our own galaxy emits radiation at microwave frequencies, mostly from dust grains and electrons spiraling in magnetic fields. There are also point sources like distant galaxies and quasars. Missions like WMAP and Planck observe at multiple frequencies to distinguish the CMB from these foregrounds, since different physical processes have different spectral signatures. For example, dust emission has a spectrum that rises steeply at shorter wavelengths, while the CMB has its characteristic black-body shape. By comparing observations at different frequencies, you can model and subtract the foreground contributions. Data processing also involves masking regions where the foreground contamination is too strong, like the plane of the Milky Way, and carefully assessing noise from the instruments themselves. The beautiful CMB maps you see in publications are the result of extensive methodical cleaning, much like editing a long report for clarity, by removing extraneous details and focusing on the core information. The CMB doesn't stand alone as a source of cosmological information. Its parameter estimates can be compared with other independent measurements. Galaxy surveys map the large-scale structure of the universe and provide constraints on dark matter and dark energy through patterns like baryon acoustic oscillations, which are essentially the grown-up version of those early sound waves. Observations of distant supernovae measure the expansion history of the universe and the effects of dark energy. Measurements of gravitational lensing reveal how matter is distributed. The fact that these independent methods largely agree strengthens confidence in the standard cosmological model, often called lambda CDM, where lambda represents dark energy and CDM stands for cold, dark matter. Where there are tensions, like the current discrepancy between different measurements of the Hubble constant, they become topics of careful investigation. The CMB's role in all this is to act as a baseline, a set of early universe conditions that any viable theory must respect. There's also information in the polarization of the CMB light. Polarization refers to the orientation of the light waves, a property that can carry additional clues about how the light was scattered in the early universe. When photons scatter off electrons, they can become polarized depending on the geometry of the scattering. The CMB has 2 types of polarization patterns, called E modes and B modes. E modes are relatively easy to detect and provide additional constraints on cosmological parameters. B modes are much more subtle and can be produced by gravitational waves from the inflationary epoch, the brief period of exponential expansion thought to have occurred in the universe's first fraction of a second. Detecting primordial B modes would be a major discovery, offering direct evidence of inflation, but the signal is so faint that it requires extremely sensitive instruments and careful control of systematic errors. These polarization measurements add extra columns to the data set, refining our understanding of what happened in those earliest moments. It's important to remember that the CMB is not something that happened once and then ended. It's always present, bathing the universe in a faint microwave glow. If you built a perfect microwave detector and pointed it at any patch of sky far from bright sources, you would pick up this signal. It doesn't turn on or off, it's simply part of the environment, a constant low-level background tone. Our instruments sample it, map it, and reanalyze it with new techniques as technology improves, but the signal itself remains stable. For someone drifting off to the sound of rain and a black screen, the thought is almost soothing. While life goes on in one small corner of space, a very old light continues to travel, carrying a record of the universe's early days. It's been travelling for so long that its journey spans most of the history of the universe itself, and yet it's still here, still detectable, still quietly providing information. Closing out tonight's quality control check, the CMB has passed every major test of consistency with our best cosmological models. Its detailed structure has given us a clear, if incomplete, picture of the universe's birth and composition. The data may look like maps, graphs, and power spectra, technical outputs from satellites and ground-based telescopes, but behind those shapes is a single, ancient glow. When you strip away all the jargon and the mathematical formalism, what you're left with is light from a time when the universe was young, smooth, and just beginning to develop the structure that would eventually become galaxies, stars, and planets. That light has been stretched and cooled by the expansion of space, but it hasn't disappeared. It's still there, filling the universe, waiting to be measured by anyone with the right equipment and enough patience. The process of studying the CMB is methodical and cumulative. Each mission builds on the work of previous ones, improving resolution, reducing noise, and refining parameter estimates. COPE gave us the first clear detection of fluctuations. WMAP turned those fuzzy patches into a detailed map and extracted precise cosmological parameters. Planck pushed the measurements to even higher precision and explored polarization more thoroughly. Future missions and ground-based experiments continue to probe the faint signals, looking for subtle effects that earlier instruments couldn't detect. The work is ongoing, not because the CMB is changing, but because our ability to measure it keeps improving. There's a certain elegance to the fact that so much information can be extracted from such a simple signal. The CMB is, at its core, just a background glow, uniform to within 1 part in 100,000. But those tiny deviations from uniformity, those little ripples in temperature, encode a wealth of information about the universe's contents, age, and geometry. The power spectrum distills all that complexity into a single curve, and from that curve scientists can read off parameter values with impressive precision. It's a reminder that nature doesn't always reveal its secrets through dramatic, obvious phenomena. Sometimes the most profound insights come from carefully analysing the boring, persistent background hum that's always been there. What makes the CMB particularly valuable is its simplicity relative to other cosmological probes. Galaxy surveys are complicated by the messy physics of how galaxies form and evolve, processes involving star formation, supernova feedback, black hole growth, and gas dynamics, all of which are difficult to model from first principles. Supernovae are useful distance indicators, but there are questions about whether their properties have changed over cosmic time, and whether dust or other effects might systematically bias the measurements. The CMB, by contrast, comes from a time when the universe was much simpler. There were no stars yet, no galaxies, no complex structures, just hydrogen, helium, a trace of lithium, dark matter, photons, and neutrinos. The physics governing the CMB is linear, meaning small perturbations behave predictably without complicated interactions, and well understood. This makes the theoretical predictions robust and the interpretation of the data relatively clean. That said, even the CMB has its complications and limitations. One issue is something called cosmic variance, which is an irreducible uncertainty that comes from the fact that we only have one universe to observe. The large-scale features in the CMB, those corresponding to low multipole numbers, are particularly affected by this. There are only so many independent large-scale patches on the sky, so the statistical uncertainty in measuring their properties can never be reduced below a certain level, no matter how perfect your instruments are. It's like trying to estimate the average height of people in a city by measuring only 10 individuals. You might get unlucky and sample mostly tall or mostly short people. The CMB has the same problem at large scales. For small-scale fluctuations, there are many more independent regions, so the measurements are statistically more robust. Another limitation is that the CMB only gives us information about the universe at one particular moment in time, the epoch of recombination. It tells us what conditions were like when the universe was 380,000 years old, and from that we can extrapolate backward to infer what must have happened even earlier, during the first fraction of a second. But the CMB doesn't directly tell us about what happened afterward, how the first stars formed, when galaxies assembled, how cosmic structure evolved over billions of years. For those questions, we need other observations, like surveys of galaxies at different distances and thus different times in cosmic history. studies of the intergalactic medium, and measurements of the star formation history across cosmic time. The CMB also doesn't directly detect dark matter or dark energy. It infers their presence through their gravitational effects on the distribution and evolution of ordinary matter and radiation. The patterns in the CMB are sensitive to how much dark matter there is because dark matter affects the gravitational potential wells that ordinary matter falls into, and it affects how the acoustic oscillations behave. Dark energy shows up in the CMB through subtle effects on the geometry of space and the late-time integrated Sachs-Wolf effect, where photons gain or lose energy as they travel through evolving gravitational fields. These are indirect detections, powerful and convincing, but they don't tell us what dark matter and dark energy actually are. That remains one of the biggest open questions in physics. Still, within its domain, the CMB is extraordinarily informative. It has transformed cosmology from a field where order of magnitude estimates were considered good progress into one where percent-level precision is routinely achieved. The age of the universe is known to better than 1%. The density of dark matter is constrained to a few percent. The amplitude and tilt of the primordial power spectrum, parameters describing the initial seed fluctuations that grew into all cosmic structure, are measured with similar precision. These tight constraints have turned cosmology into a mature science, where new theories are judged not by whether they seem plausible, but by whether they can match the detailed quantitative predictions of the standard model. Looking forward, there are still things to learn from the CMB. Ground-based experiments are currently hunting for the faint B-mode polarization signal that would indicate gravitational waves from inflation. Space missions are being designed to push measurements to even higher precision, to probe finer angular scales, and to search for subtle deviations from the standard model that might hint at new physics. There's also interest in measuring distortions in the CMB spectrum, deviations from the perfect blackbody shape, that could arise from energy injection in the early universe, perhaps from decaying particles or other exotic processes. These spectral distortions would be incredibly faint, much harder to detect than the temperature and polarization fluctuations, but they would open a new window on the universe's first million years. Another frontier involves cross-correlating the CMB with other datasets. For example, as CMB photons travel toward us, they pass through the large-scale structure of the universe, and their paths are bent slightly by gravitational lensing. This lensing distorts the CMB pattern in subtle ways, and by measuring that distortion, scientists can map the distribution of matter along the line of sight. This lensing signal can then be cross-correlated with galaxy surveys to learn more about dark energy and the growth of structure. The CMB can also be cross-correlated with traces of hot gas in galaxy clusters through the Sunyaev-Zeldovich effect, where CMB photons gain energy by scattering off hot electrons. These cross-correlation studies squeeze additional information out of the CMB data and help connect the early universe to the late universe. Even with all these future possibilities, the core story of the CMB remains simple. It is light from the early universe, released when the cosmos became transparent, stretched and cooled by expansion, and now arriving at our detectors as a faint microwave glow. It carries in its pattern the memory of sound waves that rippled through the primordial plasma, and from that pattern we have learned the universe's age, composition, and geometry. It is one of the most important discoveries in the history of science, and yet it sits there quietly, a background hum that has been present for nearly the entire age of the universe, unnoticed by most of the matter and energy around it, simply propagating through space according to the rules of physics. For those settling into sleep, the CMB offers a sense of continuity and scale. It connects the present moment to a time nearly 14 billion years ago, a time before stars, before planets, before anything resembling the structures we see in the night sky. It reminds us that the universe has a history, one we can study and understand through careful observation and analysis. And it does all this not through grand gestures or dramatic events, but through the patient accumulation of data, the slow refinement of measurements, and the quiet confidence that comes from seeing the same answers emerge from multiple independent lines of evidence. The universe, it turns out, is willing to tell us its story. We just have to listen to the hum. The next story is about to begin. Please relax and enjoy. Tonight is not about dramatic explosions or colliding galaxies or theories of parallel universes. Tonight is just about checking the universe's numbers, carefully, patiently, the way an accountant might review a long ledger at the end of a quiet day. For decades, astronomers have kept a kind of cosmic logbook, filling in columns of data, distances to galaxies, their brightnesses, how much their light has shifted toward red. Simple measurements, neat rows of figures, and by filling in this ledger over many years, they discovered something unexpected. The universe isn't just expanding, it's speeding up. To make the mathematics work, to make the observations fit together, they had to add a new line to the cosmic budget, a smooth, invisible entry called dark energy. In the early 20th century, many of the faint smudges visible through telescopes were thought to be nearby clouds of glowing gas, tucked somewhere within our own Milky Way. Astronomers sketched them, catalogued them, gave them numbers. But as telescopes improved and spectroscopy became routine, those smudges turned out to be something far stranger. Entire galaxies, vast collections of stars lying millions or even billions of light years beyond our own. Each smudge was a new line in the logbook, a new entry with basic information: brightness, spectrum, rough distance. At this stage, no one expected these galaxies to reveal anything particularly odd about the universe. They were simply being organised, inventoried, the way a librarian might catalogue books on newly installed shelves. Among the tools astronomers used to measure distances were Cepheid variable stars. These are stars that brighten and dim in a regular cycle, their light rising and falling like a slow heartbeat. Henrietta Leavitt, working with photographic plates at Harvard, discovered that the period of a Cepheid's pulsation, the time it takes to go from bright to dim and back again, is tightly linked to its true luminosity. A Cepheid that pulses slowly is intrinsically brighter than one that pulses quickly. This meant that by measuring the period you could determine the star's true brightness. And by comparing that true brightness to how bright it appears from Earth, you could calculate its distance. Cepheids became standard candles, objects whose true luminosity is known, allowing astronomers to install the first reliable rulers across cosmic space. With these stars, fuzzy impressions of distance turned into measured entries, tick marks on a scale that stretched far beyond the Milky Way. But distance alone wasn't enough. Astronomers also needed to know how galaxies were moving. This came from studying redshift, the stretching of light as objects move away from us. When a galaxy recedes, the wavelengths of light it emits are stretched to longer, redder values, much like the pitch of a siren drops as an ambulance drives away. By measuring the positions of spectral lines in a galaxy's light and comparing them to laboratory values, astronomers could determine how much the light had been redshifted, and from that, infer the galaxy's recession speed. Now each galaxy had two numbers in the ledger, a distance, often derived from Cepheids, and a speed, measured from redshift. Two columns in a table. It doesn't sound like much, but putting those two numbers side by side would reshape our understanding of the cosmos. Edwin Hubble and his colleagues plotted these two quantities, recession speed versus distance, and found a roughly straight-line relationship. The farther away a galaxy was, the faster it appeared to be moving away from us. This did not mean Earth was at the centre of some explosion. Rather, it meant that space itself was expanding, stretching distances uniformly in all directions. Imagine dots on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot, not because they're racing across the surface, but because the surface itself is growing. The Hubble constant, the slope of that distance speed line, became a single number summarising the expansion rate. It was written at the top of the logbook like a header, a key figure that described how fast the universe was growing. The natural next question was, how does this expansion change over time? Matter exerts gravity, and gravity pulls things together. So over the vast stretches of cosmic history, the expansion should slow down. The universe began in a hot, dense state, and has been expanding ever since. But with all that matter pulling inward, the expansion rate should gradually decrease. Early cosmological models, based on general relativity and estimates of the universe's matter content, predicted a decelerating expansion, fast in the distant past, easing off more recently. For many decades, cosmologists assumed that with better measurements, they would eventually detect this slowing, written into the logbook as a gentle downward curve when plotting distance against redshift at very large scales. To measure this deceleration, Astronomers needed standard candles that could be seen at much greater distances than Cepheids alone could provide. Type Ia supernovae became those candles. These are exploding stars, specifically white dwarfs that accumulate matter from a companion star until they reach a critical mass and detonate. The explosion is violent but also remarkably uniform in brightness. Because the conditions that trigger a Type Ia supernova are fairly consistent, these explosions reach roughly the same peak luminosity. By observing these supernovae in distant galaxies, astronomers could extend their cosmic distance measurements much farther into space and farther back in time. Each supernova became a carefully measured entry: peak brightness, redshift, host galaxy, uncertainty. The spreadsheets grew longer, the data more refined. In the 1990s, two major research teams set out to measure the deceleration of the universe by observing distant type Ia supernovae. They expected to find that these supernovae, located billions of light years away, would appear either slightly brighter or slightly dimmer than predicted, depending on how much the expansion had slowed. The teams worked independently, checking each other's data, refining their calibrations. When the results came in, they found something no one had anticipated. The distant supernovae were dimmer than expected, not by a huge amount but consistently dimmer. This meant they were farther away than they should have been for their measured redshifts. The distance-redshift relationship curved, but in the wrong direction. Instead of slowing down, the expansion of the universe was speeding up. At first, there was skepticism. Could the dimness be caused by dust along the line of sight, absorbing some of the light? Could the supernova themselves evolve over cosmic time, becoming intrinsically fainter in the distant past? Astronomers checked these possibilities carefully. Dust typically reddens light, and the observed dimming didn't show the expected colour signature. Detailed studies of supernova properties at different redshifts suggested that evolution alone couldn't explain the effect. The simplest explanation, strange as it sounded, was that the universe really was accelerating. The logbook now contained a stubborn discrepancy that couldn't be erased by adjusting the usual parameters. To make the equations of general relativity match these observations, cosmologists had to reintroduce a term that Albert Einstein had once added to his equations and later reportedly called his greatest blunder: the cosmological constant. This term represents a uniform energy density that fills all of space, a kind of background tension or pressure. In practical terms, dark energy behaves like negative gravity, not pushing galaxies apart in the everyday sense, but causing the expansion of space itself to accelerate. It doesn't clump into galaxies or stars. It remains smooth and spread out, like a faint mist of energy present everywhere, unchanging over time. In the cosmic ledger, it appears as an extra column in the budget, not just ordinary matter and dark matter, but a new dominant entry labelled with the Greek letter lambda, representing the cosmological constant's contribution to the total energy density of the universe. When cosmologists add up the universe's contents, they now speak in terms of fractions of the total energy density. A small fraction is ordinary matter, atoms, the stuff of stars and planets and people. A larger fraction is dark matter, invisible material whose presence is inferred from its gravitational effects on galaxies and galaxy clusters. And the majority, roughly 70%, is dark energy. These numbers come from combining multiple independent observations: supernova distances, the distribution of galaxies on large scales, and the patterns in the cosmic microwave background. Together, they form a consistent picture. The universe's ledger looks like a pie chart with three main slices, and the largest slice belongs to dark energy, even though we detect it only through its subtle influence on the expansion rate. The cosmic microwave background provides some of the tightest constraints on dark energy. This is the cooled afterglow of the early universe, radiation left over from a time when the cosmos was hot and dense, about 380,000 years after the Big Bang. Today, this radiation has cooled to just a few degrees above absolute zero and appears as a faint microwave signal filling the sky. The CMB is not perfectly smooth. It has tiny temperature variations, fluctuations at the level of 1 part in 100,000. These fluctuations encode information about the universe's contents and geometry. By measuring the angular size and amplitude of these variations, plotting them as a power spectrum of peaks and troughs, cosmologists can infer how much ordinary matter, dark and dark energy the universe contains. Dark energy affects the geometry of space, influencing the apparent size of structures imprinted in the CMB. The data from satellites like WMAP and Planck fit best with a universe that includes a cosmological constant, adding another independent line of evidence to the logbook. Baryon acoustic oscillations offer yet another way to track cosmic expansion. In the hot, dense early universe, ordinary matter and radiation were tightly coupled, and pressure waves, sound waves, rippled through the plasma. These oscillations left a characteristic scale imprinted in the distribution of matter. Today we see a faint echo of those sound waves in how galaxies cluster. When astronomers map the positions of millions of galaxies and measure their clustering, they find a small excess of galaxy pairs separated by a specific distance, roughly 500 million light-years. This is the Baryon acoustic oscillation scale, a standard ruler imprinted by the physics of the early universe. By measuring the apparent size of this ruler at different redshifts, at different epochs in cosmic history, astronomers can track how the expansion rate has changed over time. The measurements agree with a universe dominated by dark energy, providing yet another column of evidence in the cosmic ledger. The standard cosmological model that emerges from all this data is called lambda CDM, where lambda represents the cosmological constant and CDM stands for cold dark matter. The model is described by a small set of parameters: the density of ordinary matter, the density of dark matter, the density of dark energy, the Hubble constant, and a few others related to the initial conditions of the universe. Fitting this model to observations is a careful process. Cosmologists adjust the parameters until the model's predictions, how supernovae should appear at various distances, what the CMB power spectrum should look like, how galaxies should cluster, line up with the measurements. It's a kind of curve fitting, but a powerful one, because a single, simple model accounts for many different types of data collected with different telescopes and techniques. So far, lambda CDM fits the logbook better than any known alternative. The numbers work. But what is dark energy really? There are a few possibilities, and none has been confirmed. It might be a true cosmological constant, a fixed energy density inherent to the vacuum of space itself, unchanging throughout cosmic history. Quantum field theory suggests that empty space is not truly empty, but filled with fleeting virtual particles, and this quantum vacuum might have an associated energy density. The problem is that naive calculations predict a vacuum energy far larger than what we observe, a discrepancy so enormous that it's known as the cosmological constant problem. Another possibility is that dark energy is not constant but slowly evolving, represented by a field that changes over time, sometimes called quintessence. If dark energy varies, its density might have been different in the past and could change in the future, leading to different expansion histories. A third idea is that dark energy is not a substance at all, but a sign that general relativity needs to be modified on very large scales. Perhaps the equations that describe gravity on cosmic scales are different from those we use in the solar system, and what we call dark energy is really a bookkeeping shortcut for more complex gravitational behaviour. These options live as neat columns of theories in the logbook, but the spaces under direct detection remain blank. The presence of dark energy affects the long-term future of the universe. If dark energy is a true cosmological constant, its density remains fixed even as the universe expands. Over billions of years, the accelerated expansion continues. Galaxies outside our local gravitationally bound group gradually move away faster and faster, eventually slipping beyond our cosmic horizon. The universe becomes more and more spread out, colder and emptier. On human timescales, this means nothing. The changes are imperceptibly slow. But extrapolating the trend far into the future suggests a universe that continues to expand indefinitely, with distant structures fading from view as space stretches between them. If dark energy evolves, other futures are possible. It might weaken over time, allowing gravity to regain influence, or it might strengthen, leading to more exotic scenarios. These are mathematical extrapolations, like projecting a trend line far beyond the current data, but they illustrate how sensitive the fate of the universe is to the nature of dark energy. Modern surveys are designed to refine our understanding by gathering vastly more data. Wide-field telescopes on mountaintops and in space are mapping millions of galaxies, measuring their redshifts, detecting thousands of supernovae, and charting the clustering of matter across the sky. Spectroscopic campaigns measure galaxy distances with high precision. Weak gravitational lensing surveys observe how the gravity of foreground structures subtly distorts the images of background galaxies, providing another way to map the distribution of matter and infer the effects of dark energy. Each survey adds many more lines to the cosmic logbook. The goal is not to overturn the lambda CDM model, but to test it rigorously, to tighten the error bars on dark energy's properties, to check whether its effects truly match a simple cosmological constant or show hints of something more complex. The measurements are becoming precise enough that even small deviations from the standard model might become visible. And so we arrive at a curious situation. Dark energy is not a vague idea or a speculative hypothesis. It is a well-constrained component of our cosmological model. Its density is measured, its effect on the expansion of the universe is clear, and it appears consistently across multiple independent observations. Yet its physical nature remains unknown. We have a precise number for how much of the universe's energy budget is dark energy, but we don't know what that energy actually is. It's an unusual kind of mystery. The numbers are clear, the phenomenon is robust, but the underlying explanation is pending. For now, dark energy remains a carefully recorded but unexplained line in the universe's accounting, a placeholder in the equations that works beautifully but offers no insight into the mechanism behind it. The logbook stays open. Every night, telescopes continue their work. On remote mountaintops and aboard satellites in orbit, instruments collect light from distant galaxies. Spectrographs split that light into rainbows, revealing redshifts. Cameras capture the brief flare of supernovae, recording their brightening and fading over weeks. Software pipelines process the data, flagging candidates, measuring distances, adding entries to spreadsheets. Teams of astronomers review the numbers, checking for systematic errors, comparing results from different surveys. Slowly, entry by entry, the cosmic ledger grows more detailed. Each new measurement narrows the possibilities for what dark energy can be. Each tightened error bar rules out certain models, constrains certain parameters. The universe itself seems indifferent to our questions. Space continues to stretch, pulling distant galaxies farther away whether or not we understand the mechanism. The acceleration continues, a slow, steady increase in the expansion rate that will play out over billions of years. On a single human night, the change is immeasurably small. The distant galaxies we see tonight are in nearly the same places they were yesterday, their redshifts unchanged to any precision we can detect. But over cosmic time, the effect is profound. Galaxies that are already far away will move farther, their light redshifting into the infrared and beyond, eventually becoming undetectable. The observable universe will, in a sense, shrink, not because space itself contracts, but because the expansion carries distant objects beyond the reach of light that can ever reach us. For those who find comfort in mystery, dark energy offers a particularly pure example. It is not hidden in the sense of being inaccessible. We see its effects clearly in the data. It is hidden in the sense that we do not yet know what it is made of, why it exists, or whether it is truly a property of space itself or a sign of something deeper. The history of physics is full of such mysteries. Electromagnetism was once a collection of curious phenomena, magnets, sparks, chemical reactions, before Maxwell unified it into a single framework. Radioactivity was a strange glow from certain rocks before it revealed the structure of the atomic nucleus. Dark energy may be similar, a well-measured effect awaiting a theoretical explanation that will, in hindsight, seem natural. Until that explanation arrives, cosmologists continue the work of refining the logbook. They cross-check measurements, compare supernovae at different redshifts, search for subtle variations in the baryon acoustic oscillation scale, scrutinize the polarization patterns in the cosmic microwave background. They develop more sophisticated models, testing whether dark energy could have varied slightly over time, or whether alternative theories of gravity might fit the data just as well. They propose new missions, space telescopes designed to observe thousands more supernovae, ground-based surveys to map the distribution of galaxies in unprecedented detail, experiments to measure the cosmic expansion rate with independent methods. Each of these efforts is a line item in the ongoing audit of the universe, a check on the numbers, a search for discrepancies that might hint at new physics. There is something calming about this work. It is meticulous, patient, cumulative. It does not promise immediate revelation or sudden breakthroughs, though those can happen. Instead, it proceeds by adding one measurement at a time, comparing one dataset against another, gradually building a more complete picture. The universe is large, ancient, and indifferent to human timescales, but it is also surprisingly willing to reveal its properties to anyone willing to look carefully and keep careful records. The logbook is not a secret document. The data are published, shared, scrutinized by researchers around the world. The process is open, transparent, and collaborative, a collective effort to understand the cosmos through observation and reason. And so, as the rain falls outside and the night deepens, we can imagine those telescopes continuing their quiet work. A supernova flares in a distant galaxy, its light travelling for billions of years before finally reaching a detector on Earth. The signal is recorded, time-stamped, added to a catalogue. In a few weeks, follow-up observations will measure its peak brightness, confirm its type, determine its redshift. Another entry in the ledger. Somewhere else, a survey telescope scans a patch of sky, collecting spectra from hundreds of galaxies in a single exposure. The data are transmitted to computers, processed through pipelines, and distilled into measurements of galaxy positions and redshifts. Another set of points on a plot, another constraint on the expansion history. And in an office or a lab, an astronomer examines the latest results, comparing them to predictions, noting where the model fits well and where tensions remain. Another day's work in the long project of understanding the universe. Dark energy is still there, filling space, gently accelerating the expansion. It does not announce itself with fireworks or fanfare. It is simply part of the universe's structure, woven into the fabric of space-time, present in every cubic meter of emptiness between galaxies. We infer its presence from the dimming of distant supernova, from the geometry encoded in the cosmic microwave background, from the clustering of galaxies on the larger scales. We give it a name and assign it a fraction of the cosmic energy budget. We write down equations that include it, and those equations match the observations. But we do not yet know what it is. Perhaps one day, a new theory will emerge that makes dark energy seem obvious. Perhaps a clever experiment will detect some property of the vacuum that explains the cosmological constant. Perhaps a refinement in observations will reveal that dark energy is not quite constant, that it evolves in a way that points to a specific underlying field. Or perhaps dark energy will remain a mystery for generations, a well-measured number in the cosmic ledger, a confirmed phenomenon that resists deeper explanation, reminding us that the universe is under no obligation to make itself comprehensible to us. For tonight, though, we can let the questions remain open. The logbook will be there tomorrow, with new entries added, new measurements recorded. The universe will still be expanding, and the acceleration will still be there. Subtle and steady, a fact of nature that we have learned to measure even if we do not yet understand its cause. The rain continues to fall, the screen stays dark, and somewhere, far overhead, light from distant galaxies continues its long journey toward Earth, carrying information about the expansion of space, about the stretching of wavelengths, about the gentle, persistent influence of dark energy. And someone, somewhere, is quietly updating the numbers. It's worth pausing to consider just how strange this situation is from a historical perspective. For most of human history, the universe was thought to be static, unchanging, eternal. The stars wheeled overhead in their predictable patterns, the planets wandered among the constellations, but the overall structure of the cosmos seemed fixed. Even Einstein, when he first applied his theory of general relativity to the universe as a whole, found that his equations predicted either expansion or contraction. To force them to describe a static universe, he added the cosmological constant as a kind of mathematical fix, a repulsive term to balance gravity's attraction. When Hubble's observations revealed that the universe was actually expanding, Einstein reportedly abandoned the cosmological constant, considering it unnecessary. The universe could simply be coasting outward from some initial state, slowing down under its own gravity but still expanding. For decades, that was the working picture. The universe began in a hot, dense state, the Big Bang, and had been expanding ever since, gradually decelerating. The main question was whether there was enough matter to eventually halt the expansion and cause a collapse, leading to a big crunch, or whether the expansion would continue forever, gradually tapering off toward a static state. Both scenarios assumed deceleration. The idea that the expansion might be accelerating, that something was actively driving galaxies apart faster and faster, was not seriously considered. It seemed to violate common sense. Where would the energy come from? What mechanism could possibly overpower gravity on cosmic scales? And yet, when the supernova data came in during the late 1990s, that's exactly what they showed. The universe wasn't just expanding, it was accelerating. Einstein's discarded cosmological constant had to be brought back, not as a mathematical trick to create a static universe, but as a genuine physical component, dark energy, that dominated the universe's energy budget. In a way, Einstein's intuition had been correct. There was an additional term in the equations. He just had the sign wrong, or rather, the context wrong. He wanted it to balance gravity and create stasis. Instead, it overwhelms gravity on large scales and drives acceleration. This historical twist adds a layer of irony to the story. The cosmological constant was introduced for the wrong reasons, abandoned when observations contradicted those reasons, and then reintroduced when different observations demanded it. It's a reminder that science doesn't always proceed in a straight line. Ideas are proposed, tested, discarded, and sometimes resurrected in new forms when new data arrive. The logbook of science, like the cosmic logbook, has its share of crossed-out entries, marginal notes, and second thoughts. What matters is not the elegance of the path, but the accuracy of the destination. The discovery of cosmic acceleration also highlights the importance of precision in astronomy. The effect is subtle. The distant supernovae were only about 25% dimmer than expected in a decelerating universe. That's not a dramatic difference. It required careful calibration, multiple independent observations, and rigorous checks for systematic errors. If the measurements had been just slightly less precise, the signal might have been lost in the noise, attributed to uncertainties or unaccounted for effects. But because the observations were good enough, because the teams cross-checked their work, the signal came through clearly. It's a testament to the power of patient, careful measurement. Sometimes the most profound discoveries come not from seeing something spectacular, but from noticing that the numbers are slightly off from what you expected, and taking that discrepancy seriously. The role of technology in this story cannot be overlooked. The discovery of dark energy required sensitive digital cameras capable of detecting faint supernovae in distant galaxies, automated telescopes that could survey large swathes of sky, and software pipelines to process vast amounts of data. It required international collaboration, with teams sharing data, techniques, and insights. It required decades of prior work building the cosmic distance ladder, calibrating standard candles, and refining cosmological models. No single observation or single insight made the discovery possible. It emerged from the cumulative effort of many people using the best tools available, building on the work of earlier generations. The logbook was filled in page by page, year by year, with each generation adding its contribution. There's also something humbling about dark energy. It reminds us how little we know about the universe. We've identified the basic components: ordinary matter, dark energy. But we only truly understand one of them. Ordinary matter, the stuff of atoms and molecules, is well described by the standard model of particle physics. We know how it behaves, how it interacts, what it's made of. Dark matter remains mysterious, but at least we have plausible candidates, hypothetical particles that interact weakly with ordinary matter, perhaps detectable in underground experiments or particle colliders. Dark energy is more elusive. It doesn't clump, doesn't form structures, doesn't interact with matter in any obvious way except through its effect on space-time itself. It's the least tangible component of the universe, yet it makes up the largest share of the total energy. This imbalance between what we know and what exists is a recurring theme in cosmology. Before galaxies were understood, most of the universe by mass was a mystery. Once galaxies were mapped, most of the mass within them turned out to be dark matter, another mystery. Now, with dark energy included, the mysterious components, dark matter and dark energy together, make up about 95% of the universe's total energy content. We live in a universe where the familiar is a tiny minority. It's as if we've been studying a vast library and have so far only learned to read 5% of the books. The rest remain in languages we don't yet understand. their content inferred only from their weight and the space they occupy on the shelves. But this is not a reason for despair. It's an invitation. Each mystery is an opportunity for discovery, each gap in the logbook a place where new knowledge might be written. The history of astronomy is full of surprises. No one expected to find galaxies beyond the Milky Way. No one anticipated that the universe was expanding. No one predicted dark matter or dark energy. Each discovery opened new questions, new avenues of inquiry. The fact that we don't yet understand dark energy doesn't mean we never will. It means we're still in the early stages of a longer investigation. Consider how the search for dark energy has evolved. The initial discovery came from supernovae, but subsequent measurements have used entirely different methods. The cosmic microwave background encodes information from when the universe was less than 400,000 years old, long before the first stars formed. Baryon acoustic oscillations probe the large-scale structure of matter, the way galaxies are distributed across billions of light years. Weak gravitational lensing measures how the cumulative gravity of all matter, dark and ordinary, distorts the paths of light from distant sources. Each of these methods provides an independent check on the others. The fact that they all point to the same conclusion, that dark energy makes up about 70% of the universe's energy density, is powerful evidence that the phenomenon is real, not an artifact of one particular measurement technique or a subtle error in one dataset. This convergence of evidence is how confidence builds in science. A single striking result, like the supernova observations, raises eyebrows and prompts further investigation. But when multiple independent methods, using different instruments, different physical principles, and different sources of data, all arrive at consistent answers, the case becomes compelling. The universe is not trying to deceive us. It's telling us the same story through multiple channels. Our job is to listen carefully, compare the accounts, and extract the underlying truth. The current generation of surveys is pushing this even further. Projects like the Dark Energy Survey, the Sloan Digital Sky Survey, and upcoming missions like the Euclid Satellite and the Vera C. Rubin Observatory are designed to measure dark energy's properties with unprecedented precision. They will observe millions of galaxies, thousands of supernovae, and map the distribution of matter across vast volumes of space. They will measure how the expansion rate has changed over billions of years, looking for any hint that dark energy is not truly constant. Even a small variation, a few % change in dark energy's density over cosmic time, would be a major clue, potentially pointing toward a specific theoretical model. These surveys are also searching for tensions in the data, places where different measurements don't quite agree. One such tension involves the Hubble constant, the current expansion rate of the universe. Measurements based on the cosmic microwave background predict one value, while measurements based on nearby supernovae and Cepheids give a slightly different value. The discrepancy is small, only a few %, but it persists even as both measurements become more precise. This could be a sign of unaccounted for systematic errors, or it could hint at new physics. Perhaps dark energy evolves in a way not captured by the standard model, or perhaps there's an additional component of the universe we haven't yet included in the ledger. Resolving this tension is one of the priorities of modern cosmology. There are also more speculative ideas floating in the theoretical literature. Some models propose that dark energy is connected to extra dimensions of space, hidden from ordinary experience but influencing the large-scale behavior of the universe. Others suggest that dark energy might be related to the cosmological event horizon, the boundary beyond which objects recede faster than light and become forever unobservable. Still others explore whether dark energy could decay over time, gradually converting into other forms of energy, or whether it might interact with dark matter in subtle ways we haven't yet detected. These ideas are mostly untested, waiting for observations precise enough to distinguish them from simpler models. They live in the margins of the logbook, speculative annotations pending confirmation or refutation. One thing that makes dark energy particularly challenging is that it has no direct laboratory analogue. We can't create a patch of dark energy in a lab and study its properties. We can't bottle it, measure its temperature, or probe its structure. All our information comes from its effect on the expansion of the universe, a phenomenon that plays out over billions of light years and billions of years. This makes dark energy a fundamentally cosmological problem, one that can only be studied through astronomy. We have to wait for light from distant galaxies, decode the information it carries, and infer the properties of dark energy from patterns in redshifts, brightnesses, and clustering. It's detective work on the grandest possible scale, with the universe itself as the only laboratory. Yet despite these challenges, progress is being made. The parameters describing dark energy are being measured with increasing accuracy. The equation of state, the relationship between dark energy's pressure and its density, is being constrained to within a few percent of the simplest model, a true cosmological constant. Future surveys promise even tighter constraints, potentially revealing subtle deviations that could point to the true nature of dark energy. It's painstaking work, requiring patience and precision, but it's work that steadily narrows the range of possibilities, ruling out some models and focusing attention on others. In the meantime, the universe continues its expansion, indifferent to our efforts to understand it. Dark energy pervades every cubic meter of space, its influence steady and unrelenting. Galaxies move apart, their distances increasing year by year, century by century. The effect is too slow to notice in a human lifetime, but it's there, written into the structure of space-time itself. And we, brief sparks of consciousness on a small planet orbiting an ordinary star, have found a way to measure it, to quantify it, to add it as an entry in our cosmic logbook. That achievement, however incomplete our understanding, is worth acknowledging. We may not yet know what dark energy is, but we know it exists, we know how much there is, and we know what it does. That's not nothing. That's a foothold, a starting point for deeper inquiry. The story of dark energy is still being written. New chapters will be added as new data come in, as new telescopes come online, as new theoretical ideas are proposed and tested. Perhaps the mystery will be solved within a generation. Perhaps it will take longer. Either way, the logbook will continue to grow, line by line, number by number, each entry a small piece of the larger puzzle. And somewhere, on some quiet night, an astronomer will notice a pattern in the data, or a theorist will have an insight that ties disparate observations together, and another piece of the cosmic story will fall into place. Until then, we wait, we measure, and we think. The universe is patient. We try to be patient too. The next story is about to begin. Please relax and enjoy. Tonight we are conducting a census of alien worlds, and there is nothing particularly thrilling about it. This is administrative work, the slow and methodical task of counting planets that happen to orbit stars other than our own sun. Imagine an astronomer seated at a desk scrolling through columns of data, star names, orbital periods, planetary radii, a few sparse notes about detection confidence. Each discovery is logged, verified, cross-referenced, and added to an ever-growing table. The work resembles that of a patient clerk processing immigration forms or updating property records, except the entries describe worlds separated from us by light years rather than city blocks. Exoplanets are no longer the subject of wild speculation or rare headlines. They have become routine catalogue entries, and the catalogue itself has grown so large that no single person can hold all the details in memory. Instead, the information lives in databases, sortable and searchable, each row representing a distant world reduced to a handful of numbers and flags. For most of human history, the idea that other stars might host planets was pure conjecture, a philosophical exercise with no supporting evidence. People reasoned by analogy. Our sun has a family of worlds circling it, so perhaps other suns do as well. This seemed reasonable, even elegant, but remained entirely speculative. Telescopes improved, astronomy advanced, yet no one could point to a specific star and say with confidence that it harboured planets. The tools simply were not sensitive enough. Even into the middle of the 20th century, exoplanets belonged more to the realm of imagination than measurement. The census form existed only as an idea, blank columns waiting for the first real entries. Philosophers and scientists could sketch what such a form might look like. Fields for orbital distance, planetary mass, perhaps atmospheric composition. But every line remained empty, awaiting the moment when technology would catch up to curiosity. The breakthrough came not from seeing planets directly, but from detecting their influence on the stars they orbit. Consider the basic mechanics. When a planet circles a star, both objects actually orbit their shared centre of mass, a point called the barycenter. For a star much more massive than its planet, This point lies close to the star's core but not exactly at the centre. As a result, the star wobbles slightly as it moves through space, tracing a small repeating loop. This wobble is minor, but it produces a detectable effect. As the star moves toward us, the light we receive shifts slightly toward the blue end of the spectrum, and as it moves away, the light shifts toward red. These are Doppler shifts, the same phenomenon that changes the pitch of a siren as an ambulance drives past. Astronomers began monitoring the light from nearby stars, splitting it into spectra and measuring these tiny shifts night after night. Over weeks and months, patterns emerged, gentle, repeating waves in the spectral data, like a slow heartbeat encoded in light. Each stable wave represented a planet tugging its star in a predictable rhythm. The planet itself remained invisible, but its signature appeared on the page as a series of measurements, a wobble recorded in wavelengths and translated into a claim. A planet exists here, with this mass, at this distance, completing an orbit in this many days. The first confirmed exoplanet around a Sun-like star was announced in the mid-1990s, and it immediately became the first real entry in the census, a single line in what would soon become a very long list. What surprised astronomers was not simply that planets existed elsewhere, but that many of the first discoveries contradicted expectations derived from our own solar system. The early entries in the census featured so-called hot Jupiters, giant planets comparable in size to Jupiter, but orbiting extremely close to their stars, often closer than Mercury orbits our Sun. These worlds completed their years in just a few Earth days, subjected to searing temperatures that would vaporize metals. In our solar system, gas giants live in the cold outer regions, far from the Sun's heat. The discovery of hot Jupiters suggested that planetary systems do not all follow the same blueprint. Rather than causing alarm or confusion, these strange entries simply expanded the census categories. Astronomers added new columns and notes, close-in giants, ultra-short periods, extreme temperatures. The universe, it turned out, does not organise itself according to the one example we knew best. The filing system had to grow to accommodate worlds that did not fit the original template. While the radial velocity method continued to find planets by measuring stellar wobbles, another technique began to dominate the census work, the transit method. This approach is elegant in its simplicity. When a planet passes directly between its star and our line of sight, it blocks a tiny fraction of the star's light, causing a brief, shallow dip in brightness. If the planet's orbit is aligned just right, this dimming happens at regular intervals, once per orbit. Astronomers monitor stars continuously, recording their brightness over time and producing what are called light curves, smooth lines tracing the star's output. Most of the time, the line stays flat, but when a planet transits, a small notch appears, a gentle downward dip followed by a return to baseline. The depth of the dip reveals the planet's size relative to the star, and the spacing between dips gives the orbital period. Each transit is like a checkbox on a survey form, a repeating signal that confirms the presence of a planet and allows its basic properties to be inferred. With enough transits recorded, the light curve becomes an attendance sheet for the planetary system, each world marking its presence with a predictable pattern of dimming. The transit method brought a new level of efficiency to the census. A single telescope, staring at thousands of stars simultaneously, could detect multiple planets at once simply by watching for these periodic dips. The task became almost mechanical: collect light curves, search for repeating patterns, flag candidates, verify with additional observations or different methods. Each confirmed transit added another row to the database, and the rows began to accumulate rapidly. But the transit method also revealed subtleties that hinted at hidden complexity. In systems with multiple planets, the gravitational pull between worlds can cause slight variations in the timing of transits. A planet might arrive at its expected transit a few minutes early or late, tugged by the gravity of an unseen companion. These transit timing variations show up as small deviations in an otherwise regular schedule, like margin notes scribbled on a form indicating that something else is present in the system. By carefully modelling these timing shifts, astronomers can infer the existence of additional planets, even those that do not transit. These indirect detections fill in gaps, adding extra lines to the census based on the gravitational fingerprints left in the data. In rare cases, astronomers manage to take direct images of exoplanets, capturing actual photons reflected or emitted by the planet itself. This requires blocking out the star's overwhelming glare using specialized instruments and analyzing what remains, a faint point of light offset from the star. Direct imaging works best for planets that are large, far from their stars, and often young and still radiating heat from their formation. The resulting images are not dramatic photographs of swirling clouds or colourful landscapes. They are subtle, carefully processed spots, pixels that have been teased out of noise and identified as separate from the star. Each direct image is a profile picture in a database, otherwise dominated by graphs and numbers, a visual confirmation that adds texture to an entry, but does not fundamentally change the nature of the sensor's work. These images are rare because the conditions required, bright planet, dim or blocked star, favourable geometry, are difficult to achieve. Most planets remain invisible, known only through their effects on light and motion. One mission in particular transformed the scale of the census. A space telescope launched to stare at a single patch of sky for years, monitoring over 100,000 stars continuously. The mission's task was straightforward but demanding. Watch for the tiny repeating dips in starlight that indicate transiting planets. Each star became a line in the survey. Either it exhibited transit signals, or it did not. The telescope recorded brightness measurements with exquisite precision, sending the data back to Earth where teams of scientists processed it, cleaned it, and searched for patterns. Over time, the catalogue of candidate planets grew into the thousands. Some candidates required follow-up observations to confirm their planetary nature and rule out false positives. But the sheer volume of detections established a new reality. Planetary systems are common. The mission did not explore strange new worlds in the narrative sense. It simply stared and counted, adding entry after entry to the galactic spreadsheet. The work was repetitive, methodical, and enormously productive, demonstrating that patience and precision could map the sky one light curve at a time. Following that mission, newer surveys expanded the approach, scanning nearly the entire sky, but focusing on bright nearby stars. These are follow-up census rounds, trading deep focus on one region for broader coverage across many regions. The goal is to catalogue planets around stars close enough for detailed follow-up study, where future telescopes might analyse atmospheres or search for signs of habitability. Each new survey finds more planets, adding variety to the catalogue, some with short orbits, others with longer periods, single planets and multi-planet systems, hot worlds and cooler ones. The spreadsheet grows steadily, each mission contributing a new batch of rows, occasional corrections to earlier entries, and updates to detection confidence levels. As the census expanded, patterns emerged in the types of planets being discovered. Astronomers developed a rough classification system based on size and composition, though the boundaries are fuzzy and many planets fall into intermediate categories. Hot Jupiters are the gas giants orbiting close to their stars, easily detected because their large size causes deep transits and their proximity produces strong radial velocity signals. Mini-Neptunes are smaller, roughly between Earth and Neptune in size, likely with thick atmospheres of hydrogen and helium surrounding a rocky or icy core. Super-Earths are more massive than Earth but smaller than Neptune, potentially rocky or water-rich, though their exact compositions remain uncertain without direct atmospheric measurements. Many of these categories do not exist in our own solar system, which meant that new labels were needed. The classification process resembles a librarian sorting books into genres. Radius goes in one column, mass in another, density calculated from the two, and from these numbers, a tentative type assigned. The catalogue reveals that certain sizes are common. Mini-Neptunes and super-Earths populate the lists in large numbers, while others, like true Earth analogues, remain relatively rare in the current data, possibly due to detection biases rather than actual scarcity. Some planetary systems are tightly packed, with several worlds orbiting close to their star in orderly configurations. Observations show systems where 5 or 6 planets complete their orbits within a distance smaller than Mercury's orbit around our Sun. In some cases, the planets are locked in orbital resonances, meaning their periods form simple ratios. One planet might complete exactly 2 orbits for every 3 of its neighbours. These resonances stabilise the system, preventing close encounters and collisions. From an observer's perspective, such systems produce a series of transit dips, each with its own depth and timing overlapping like entries in a ledger. The light curves become layered schedules, multiple planets checking in at different intervals. These compact systems demonstrate that gravity can arrange planets in configurations very different from the widely spaced giants and inner rocky worlds of our solar system. They are not exotic or dramatic in themselves, they are simply efficient solutions to the equations of motion, alternative ways for matter to organise around a star. The concept of the habitable zone is often invoked in discussions of exoplanets, but it is a calm, technical definition, rather than a guarantee of life. The habitable zone is the range of orbital distances from a star where a rocky planet with a suitable atmosphere could, in principle, maintain liquid water on its surface. The zone's location depends on the star's brightness. Hotter stars have habitable zones farther out, cooler stars have them closer in. Being in the habitable zone does not mean a planet is habitable, only that its temperature might allow for liquid water, which is considered a key ingredient for life as we know it. Planets in this zone still need the right atmospheric pressure, composition, and other factors. In the census, habitable zone planets receive a small extra annotation in their entry, a note that says the temperature conditions are potentially moderate, neither too hot nor too cold. This is useful for prioritising follow-up observations, but it remains a preliminary flag, not a final verdict. When a planet transits, astronomers have the opportunity to study its atmosphere if it has one. As the planet crosses in front of the star, a tiny fraction of the starlight filters through the planet's atmosphere before reaching us. By carefully analysing the spectrum of this transmitted light, researchers can detect the presence of certain gases, water vapour, hydrogen, methane, or other molecules that leave distinct absorption features. These observations are technically challenging, requiring large telescopes, long observation times, and sophisticated data analysis to tease out faint signals from noise. The resulting spectra are often ambiguous, with detections at low confidence levels, but each hint of an atmosphere adds another column to the database. The census expands from simple size and orbit to include atmospheric ingredients, at least for the brightest and most favourable cases. The process feels like reading faint handwriting on an old document, deciphering one careful measurement at a time, building up a picture from fragments. The data from all these surveys and methods are compiled into online catalogues, public databases where each confirmed exoplanet is listed with its properties: host, star coordinates, orbital period, radius, mass, when available, detection method, discovery date, and confidence metrics. For astronomers, these tables are the primary interface to alien worlds. A researcher interested in mini-Neptunes can filter the catalogue by size, export a list, and analyse trends. Someone studying tightly packed systems can sort by the number of planets per star. The catalogue is a living document, updated as new discoveries are confirmed, refined as follow-up data improve initial estimates, and corrected when errors are identified. Each entry is a planet reduced to a row, and the table itself is a map of the sky's planetary population, incomplete but growing. A casual observer browsing these catalogues sees numbers, flags, and references to scientific papers, a far cry from colourful illustrations or artists' concepts. But this is the real substance of the census, data organised for analysis, not spectacle. The census is incomplete and biased by the methods used to detect planets. Transit surveys are most sensitive to planets with short orbital periods because these transit more frequently and are easier to catch during limited observation windows. They also favour planets around small stars because a given planet causes a deeper dimming relative to a smaller star's light. Radial velocity surveys are best at finding massive planets close to their stars where the gravitational tug is strongest. Direct imaging favours large, distant and young planets that shine brightly in infrared light. As a result, the catalogue is weighted towards certain types of worlds and underrepresents others. Small planets in long orbits, for example, are difficult to detect and remain largely uncounted. Astronomers are aware of these biases and work to correct for them statistically, estimating how many planets are likely to exist based on the fraction they can detect. The true census includes not only the thousands of confirmed planets, but also the carefully calculated estimates of missing entries, the planets we have not yet seen but can infer from the patterns in the data. The overarching lesson from this decades-long effort is that planets are common. With thousands of confirmed exoplanets and many more candidates awaiting verification, The evidence strongly suggests that most stars host at least one planet, and many host several. Planetary systems are not rare exceptions, but standard features of stellar evolution, as ordinary as the stars themselves. Our solar system, once the only known example and the template for all speculation, is now a single entry in a vast catalogue, neither typical nor particularly unusual, simply one configuration among many. The story of exoplanet discovery is not one of dramatic revelations or singular breakthroughs, but of steady accumulation, observations piling up, methods improving, catalogues expanding. The work continues, methodical and patient, adding row after row to the spreadsheet of alien worlds. The process of confirming an exoplanet candidate involves layers of verification, each step adding confidence that what has been detected is genuinely a planet and not some other phenomenon masquerading as one. A single transit signal might be caused by a background eclipsing binary star system aligned by chance with the target star, or by instrumental noise, or by stellar activity such as star spots rotating across the star's face. To distinguish planets from imposters, astronomers perform follow-up observations using different techniques. They might take spectra to check for the radial velocity wobble that should accompany a transiting planet. They might use high-resolution imaging to see if the star has a nearby companion that could be the real source of the signal. They might observe additional transits to verify the periodicity and depth remain consistent. Only after these checks are satisfied does a candidate receive the designation of confirmed planet, and only then does it earn a permanent place in the catalogue. The confirmation process is unglamorous, a series of cross-checks and statistical tests, but it is essential to maintaining the integrity of the census. Each confirmed planet represents not a single observation, but an accumulation of evidence from multiple sources. The stars themselves vary widely, and this variation affects the planets around them. Hot, bright stars burn through their fuel quickly and have short lifetimes, while cool, dim stars can shine for trillions of years. The most common stars in the galaxy are red dwarfs, small and cool with habitable zones located very close in. Planets orbiting red dwarfs complete their orbits in days or weeks, and because they orbit so close they often become tidally locked, with one side perpetually facing the star and the other in permanent darkness. These worlds present a different kind of environment, potentially habitable but subject to strong stellar flares and unusual temperature gradients. The census includes many planets around red dwarfs because these stars are numerous and their close inhabitable zones make planets easier to detect. Larger, sun-like stars are less common, and massive blue stars are rarer still. The catalogue reflects this distribution. Most entries list host stars that are smaller and cooler than our Sun, which means that the typical exoplanet orbits a star quite different from the one we know. The masses of exoplanets, when they can be measured, provide clues about composition. A planet's mass combined with its radius gives its average density. High density suggests a rocky composition, similar to Earth or Venus. Low density indicates a substantial gaseous envelope, like Jupiter or Saturn. Intermediate densities might point to water-rich worlds, planets with deep oceans or thick layers of ice, though distinguishing between a water world and a rocky planet with a thick hydrogen atmosphere is difficult without additional data. For many planets, especially smaller ones, detected only by transits, mass remains unknown or poorly constrained, leaving composition as an open question. The census thus contains entries with varying levels of completeness. Some planets have well-measured radii, masses, orbital parameters, and atmospheric hints. Others have only a radius and orbital period, the bare minimum. This unevenness is characteristic of an ongoing survey, where not every target can receive equal attention, and where observing time is allocated based on scientific priorities. Stellar activity complicates the census work. Stars are not static light sources. They have spots, flares, and oscillations that can mimic or obscure planetary signals. A dark star spot rotating across the visible face of a star causes a dip in brightness that might be mistaken for a transit. Distinguishing between these false signals and genuine planets requires careful analysis of the light curve's shape and timing, as well as knowledge of the star's rotation period and activity level. Young, active stars are particularly challenging targets because their variability can swamp the subtle signals of transiting planets. Older, quieter stars provide cleaner data, but even they are not perfectly steady. Astronomers have developed statistical methods and machine learning algorithms to filter out stellar noise and identify the periodic, symmetric dips characteristic of transits. These tools have become essential as the census has grown, allowing large datasets to be processed efficiently without manually inspecting every light curve. Some planetary systems exhibit unusual dynamical arrangements. Planets in highly eccentric orbits, for example, follow elongated ellipses rather than near-circular paths, swinging close to their stars at one point in their orbit and receding to much greater distances at another. These eccentric orbits can result from gravitational interactions, either between planets in the same system or with external companions. They add complexity to the census, requiring more detailed modelling to accurately determine the planet's properties. Other systems contain planets on inclined orbits, tilted relative to each other or to the star's equatorial plane. Such configurations suggest a history of dynamical upheaval, perhaps involving planet-planet scattering or the influence of a distant stellar companion. The census captures these systems as outliers, entries with unusual parameter values that prompt further investigation. The search for planets around binary star systems introduces another layer of complexity. In a binary system, two stars orbit each other, and planets can form either around one of the stars individually or in a circumbinary orbit, circling both stars together. Detecting planets in binary systems is challenging because the light curves and radial velocity signals must account for the motion of both stars. Nevertheless, several circumbinary planets have been confirmed, their transits appearing as dips in the combined light of the binary pair. These planets add variety to the catalogue, demonstrating that planetary formation is robust even in environments with multiple gravitational anchors. The orbital dynamics of such systems are intricate, with the planet's orbit influenced by the changing gravitational field as the two stars move. Yet the census treats them with the same procedural care as any other entry: orbital period, size, host star details, and notes on the detection method. Ground-based observatories contribute to the census alongside space telescopes. Networks of small, automated telescopes scan the sky for transits, while larger facilities follow up on candidates with high-resolution spectroscopy and imaging. Ground-based radial velocity surveys have been particularly productive, using instruments mounted on telescopes in Chile, Hawaii, and other sites with clear, stable skies. These surveys monitor hundreds of stars over many years, accumulating velocity measurements with precision of a meter per second or better. The combination of space-based transit surveys and ground-based radial velocity follow-up creates a complementary workflow. Space telescopes find the candidates, and ground-based instruments confirm and characterize them. The census is thus a collaborative effort, drawing on data from many sources and integrating measurements taken in different wavelengths and using different methods. The question of how planets form remains an active area of research, informed by the census data. According to current models, planets coalesce from disks of gas and dust that surround young stars. Small particles stick together, growing into larger clumps, which eventually become planetesimals and then protoplanets. Gas giants form when a core becomes massive enough to gravitationally capture hydrogen and helium from the surrounding disk. Rocky planets form closer to the star, where temperatures are too high for volatile materials to condense. However, the diversity of exoplanets challenges these models. Hot Jupiters likely formed farther out and migrated inward, their orbits altered by interactions with the disk or with other planets. Super-Earths and mini-Neptunes, common in the catalogue but absent from our solar system, suggest formation pathways that depend sensitively on disk conditions and timing. The census provides the raw material for testing these models: distributions of planet sizes, orbital periods, and multiplicities that theorists compare with predictions from simulations. Each new entry refines the constraints, helping to distinguish between competing scenarios. Red dwarf stars, because of their abundance and the ease of detecting planets around them, have become a major focus of the census. The nearest exoplanets are found around red dwarfs, some only a few light-years away. These stars are dim, so their habitable zones lie close in, and planets in these zones transit frequently, making them accessible to current instruments. Several rocky planets in the habitable zones of red dwarfs have been confirmed, and these are considered promising targets for atmospheric characterization. However, red dwarfs are prone to violent stellar flares that could strip away planetary atmospheres or sterilize their surfaces with radiation. The census notes these systems without judgment, simply recording the parameters and leaving questions of actual habitability to future investigation. The architecture of multi-planet systems reveals regularities that hint at underlying physical processes. Many systems show planets with similar sizes, sometimes called peas-in-a-pod configurations, where neighbouring planets differ in radius by only a few percent. This uniformity suggests that planets within a system share a common formation environment and have experienced similar evolutionary histories. Other systems exhibit a wider range of sizes, possibly indicating different formation times or locations within the protoplanetary disk. The spacing between planets also follows patterns, with most systems showing regular, nearly evenly spaced orbits in logarithmic terms. These statistical regularities, extracted from the census, guide models of planet formation and migration, offering clues about how the initial chaotic disk of material settles into an ordered planetary system. Measurements of planetary obliquity, the tilt of a planet's spin axis relative to its orbital plane, are possible for a few transiting planets using a technique called the Rossiter-McLaughlin effect. When a planet transits, it blocks light from different parts of the rotating star at different times, causing a subtle distortion in the star's spectral lines that reveals the orientation of the planet's orbit relative to the star's rotation. Some hot Jupiters are found on highly tilted or even retrograde orbits, moving opposite to the star's spin. This suggests violent dynamical histories, possibly involving close encounters with other planets that ejected them into misaligned orbits. These measurements add another column to the census, obliquity values that enrich the dynamical picture of each system. The concept of occurrence rates quantifies how common different types of planets are. By accounting for detection biases, astronomers estimate the fraction of stars that host planets of various sizes and orbital periods. Current estimates suggest that small planets, particularly those in the super-Earth and mini-Neptune size range, are extremely common, with most Sun-like stars hosting at least one. Gas giants are less common, found around perhaps 10 to 20% of Sun-like stars. Rocky planets in Earth-like orbits, similar size, similar distance from a Sun-like star, are harder to detect and thus less well constrained, but preliminary estimates suggest they might be present around a significant fraction of stars. These occurrence rates transform the census from a list of individual discoveries into a statistical portrait of the galaxy's planetary demographics. The numbers allow astronomers to estimate the total number of planets in the Milky Way, a figure that runs into the hundreds of billions, making planets more numerous than stars. Future missions will push the census into new territory. Next-generation space telescopes with larger mirrors and more sensitive instruments will be able to detect smaller planets, including true Earth analogues, and characterize their atmospheres in greater detail. Ground-based extremely large telescopes, with mirrors tens of meters across, will obtain high-resolution spectra of exoplanet atmospheres, searching for gases that might indicate biological activity. These future observations will add new columns to the database: atmospheric biosignature detections, surface temperature maps, measurements of day-night temperature contrasts. The census will deepen and broaden, filling in gaps and extending into parameter spaces currently inaccessible. Yet the fundamental nature of the work will remain the same: careful observation, patient data collection, statistical analysis, and catalogue updates. The human element of the census involves thousands of researchers across many countries, each contributing expertise in instrumentation, data analysis, theoretical modelling, or statistical interpretation. Teams coordinate their efforts, sharing data through public archives and collaborating on follow-up campaigns. When a particularly interesting planet is discovered, multiple groups may study it independently, combining their results to build a more complete picture. The scientific papers that announce new planets or refine known properties are densely technical, filled with tables, figures, and equations. These papers are the formal record of the census, each one adding to the collective knowledge. For those involved in the work, the satisfaction comes not from any single discovery, but from the gradual accumulation of understanding, the sense that the galaxy's planetary population is being mapped with increasing precision. The cultural impact of the census is quiet but profound. Knowing that planets are common shifts the context for thinking about life in the universe. If most stars have planets, And if many of those planets reside in conditions that might allow liquid water, then the potential sites for life are numerous. This does not prove that life is common, but it changes the calculation from one where habitable planets are rare and precious, to one where they are abundant. The next question becomes not whether habitable worlds exist, but whether life arises on them, a question the census alone cannot answer. Yet the census lays the groundwork, providing the targets for future searches and the statistical framework for estimating how many worlds might host biology. Imagine falling asleep while the census is still underway. New missions are being planned and launched, equipped with more sensitive instruments capable of detecting smaller planets, longer orbits, and fainter atmospheric signals. Some future entries may describe rocky worlds in temperate orbits around quiet stars, places where conditions might, in principle, support life. But from the perspective of this story, they will remain what all exoplanets are in the census: cells in a table, coordinates and periods and radii, notes and confidence intervals. The listener drifts off with the image of a vast unfinished spreadsheet, rows extending beyond the screen, each one a world documented but not visited, known but not explored. Somewhere, a telescope is pointing at a star, collecting photons, waiting for the next tiny dip in brightness. The data will be downloaded, processed and analysed. If a pattern is found, a new row will be added. The census of alien worlds continues quietly, methodically, while we sleep, one light curve at a time, the galaxy revealing its population not in a burst of discovery but in the slow, patient accumulation of entries in an ever-growing catalogue. The next story is about to begin. Please relax and enjoy. Tonight we're going through the universe's paperwork, and the numbers don't quite add up. It's not a dramatic discrepancy, nothing that sets off alarms or suggests fraud, just a persistent gap that shows up whenever astronomers try to reconcile what they can see with what gravity tells them must be there. They can count stars, measure the glow of gas clouds, estimate the mass of dust scattered between galaxies. They can weigh these components with reasonable confidence. Then they watch how things move, how stars orbit galactic centers, how galaxies wheel around each other in clusters, how light bends around massive objects, and the motion always implies more mass than the visible inventory can account for. Over decades, this gap has been given a name: dark matter. It's not a particularly romantic term, more like a placeholder in a ledger for an entry that hasn't been filled in yet. Something is there, exerting gravitational pull, shaping the architecture of the cosmos, but it doesn't emit light, doesn't absorb it, doesn't interact with electromagnetic radiation in any way we can detect. It simply pulls. The tools for weighing the sky are surprisingly straightforward. Light tells us about visible matter. Stars shine, gas glows when heated, dust absorbs and re-emits radiation. By measuring brightness and temperature, astronomers can estimate how much ordinary matter is present in a given region. But light only goes so far. To understand the total mass, they turn to motion. When an object orbits another, its speed depends on the gravitational force holding it in place, which in turn depends on how much mass lies inside its orbit. A planet circling the Sun moves at a speed determined by the Sun's mass. If the Sun were suddenly more massive, the planet would need to move faster to avoid being pulled in. If the Sun lost mass, the planet could afford to slow down. This relationship between orbital speed and enclosed mass is a quiet but reliable witness. Even when mass is invisible, its gravitational signature appears in the motion of things around it. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a dense congregation of galaxies bound together by their mutual gravity. He measured how fast individual galaxies were moving within the cluster, zipping around the cluster's center like bees in a swarm. The speeds were alarmingly high. With only the visible mass from stars accounted for, the cluster should have flown apart long ago. There simply wasn't enough gravitational glue from the light-emitting matter to hold such fast-moving galaxies together. Zwicky calculated that the cluster needed far more mass than could be seen, perhaps hundreds of times more. He called it missing mass, a dry, accountant-like phrase that would echo through the decades. At the time, many dismissed his findings as an anomaly or an error in measurement. The idea that most of a galaxy cluster's mass could be invisible seemed implausible, almost absurd. But the numbers kept not adding up. The discrepancy became harder to ignore in the 1960s and 70s when Vera Rubin and her collaborators turned their attention to the rotation of spiral galaxies. They measured how fast stars and gas clouds orbit the centers of these galaxies at various distances from the core. The expectation was straightforward. Most of a galaxy's visible mass, its stars and gas, is concentrated toward the center, so objects farther out should orbit more slowly, just as Neptune plods along its orbit more leisurely than Mercury races around the Sun. But that's not what they found. Instead, the rotation curves, graphs plotting orbital speed against distance from the galactic center, stayed flat. Stars at the outer edges of galaxies were moving just as fast as those closer in, as if there were additional mass spread throughout the galaxy, extending far beyond the visible disk. This wasn't a small effect. The implied extra mass was enormous, often several times the mass of all the visible stars and gas combined. The rotation curves became a recurring line item in the cosmic ledger. More mass than light implies. Galaxy clusters, revisited with more modern instruments, told the same story from a different angle. Between the galaxies in a cluster sits vast amounts of hot gas, so hot it emits X-rays. By observing these X-rays, astronomers could weigh the gas and add it to the count of visible matter. They also measured the motions of galaxies within the cluster, as Zwicky had, but with better precision. And they studied the pressure and temperature of the gas itself, which must be held in place by the cluster's gravity. All three methods, light from stars, X-rays from gas and dynamics from motion, converged on the same conclusion. There is far more mass present than can be accounted for by anything that shines or glows. The extra mass doesn't emit light, doesn't heat up detectably, but it pulls relentlessly and consistently. Gravitational lensing added yet another layer of confirmation. According to Einstein's general relativity, mass warps spacetime, and light travelling through curved spacetime bends. A massive object like a galaxy cluster acts as a lens, distorting the images of more distant galaxies behind it. The shapes of these background galaxies appear stretched, smeared into arcs or multiple images, in patterns that depend on the total mass of the foreground cluster. By carefully measuring these distortions, astronomers can map the distribution of mass in the cluster, regardless of whether that mass emits any light at all. Time and again, lensing maps reveal mass concentrations that don't align neatly with the visible galaxies or gas. There's a gravitational landscape sculpted by something unseen, a topography recorded in the bending of light. The lensing studies don't care whether the mass is bright or dark, they simply measure where spacetime curves, and the curvature is always stronger than visible. Matter alone can explain. One particular collision between galaxy clusters provided an especially clear case. The bullet cluster is the name given to a system where two clusters have smashed into each other and partially passed through. The hot gas in each cluster, being made of ordinary matter, interacts electromagnetically. As the clusters collided, the gas clouds slowed down, colliding and heating up further, leaving a glowing blob of X-ray emitting gas lingering in the middle of the system. The galaxies themselves, being mostly empty space with stars far apart, passed through each other largely unscathed. But the gravitational lensing maps told a different story. The main concentrations of mass, as revealed by the bending of background light, were not centered on the hot gas, but rather on the clusters of galaxies themselves, which had sailed through the collision. This spatial separation was a smoking gun. Most of the mass in the system was in a component that didn't interact or slow down like normal matter. It felt gravity. It exerted gravity, but it didn't collide or radiate. It behaved exactly as dark matter should, invisible, non-interacting except through gravity, and dominant in the mass budget. Zooming out to the larger scales, the structure of the universe itself offers evidence. Galaxies are not scattered randomly across space, but are arranged in a cosmic web of filaments and sheets surrounding vast, nearly empty voids. This structure grew from tiny density fluctuations in the early universe, regions that were slightly denser than average, and gradually pulled in more matter through gravity. Computer simulations can model this growth, starting from the conditions shortly after the Big Bang and evolving forward through billions of years. When these simulations include only ordinary matter, the resulting structures grow too slowly and remain too diffuse. The universe ends up smoother and less clumpy than what we observe. But when dark matter is added, an invisible component that doesn't interact with light or itself except through gravity, the simulations suddenly match reality. The dark matter collapses first, forming a gravitational scaffolding, and ordinary matter flows along this invisible framework, gathering in the densest regions to form galaxies and clusters. The cosmic web is essentially a map of dark matter's distribution, with galaxies as bright tracers lighting up the nodes and filaments of an otherwise invisible skeleton. The cosmic microwave background provides yet another line of evidence, perhaps the most precise. This faint glow of microwave radiation fills the entire sky, the cooled remnant of the hot plasma that filled the universe when it was only a few 100,000 years old. Tiny temperature variations across the sky, spots slightly warmer or cooler than average, carry information about the density fluctuations that seeded all structure in the universe. These fluctuations also encode information about the composition of the universe, how much ordinary matter, dark matter, and dark energy there is. Decades of observations from satellites and ground-based telescopes have measured these temperature variations with extraordinary precision. The data are then fit to theoretical models that predict the pattern of fluctuations based on different cosmic ingredients. The best-fitting model is remarkably consistent across independent measurements and includes roughly 5% ordinary matter, about 27% dark matter, and the remainder in dark energy. Dark matter isn't just a footnote in this accounting, it's a dominant component, several times more abundant than all the atoms in all the stars, planets, and gas clouds put together. The cosmic microwave background is like a cosmic census form, filled out by the universe itself, and it clearly lists dark matter as a major entry. Given all this evidence, it's natural to ask whether dark matter might simply be ordinary matter that's too dim to see. Faint stars, cold gas, black holes, or other compact objects made of normal atoms. These possibilities have been carefully examined and largely ruled out. If dark matter were made of dim stars or cold gas, it would still interact with light in subtle ways, absorbing or emitting radiation at certain wavelengths, or leaving fingerprints in the abundances of light elements forged in the Big Bang. None of these signatures match what we observe. Surveys have also looked for compact dark objects like black holes or brown dwarfs by watching for microlensing events, brief brightenings of distant stars caused when a dark object passes in front of them and temporarily magnifies their light. While some such objects have been detected, they are far too rare to account for all the missing mass. The numbers just don't work. Most of the dark matter must be something fundamentally different from ordinary atomic matter, something that doesn't participate in electromagnetic interactions at all. The behavior of dark matter in the early universe offers another clue. Particles can be classified by how fast they were moving when the universe was young. Hot dark matter consists of particles that were relativistic, moving at or near the speed of light, during the era when structures began to form. If dark matter were hot, it would have smoothed out small-scale density fluctuations, preventing galaxies and smaller structures from forming until much later. Simulations with hot dark matter produce a universe that's too smooth, with fewer galaxies and a different large-scale structure than we see. Light neutrinos, for example, would be a form of hot dark matter, and while neutrinos do exist and have a small mass, they cannot account for all the dark matter. Cold dark matter, by contrast, consists of particles that were moving slowly in the early universe, allowing them to clump together efficiently on all scales. Simulations with cold dark matter reproduce the observed cosmic web, the abundance of galaxies, and the hierarchy of structures remarkably well. Warm dark matter lies somewhere in between. This classification, hot, cold, warm, is another piece of the paperwork, narrowing down the properties of whatever dark matter is. If dark matter is made of particles, what might those particles be? One leading candidate is called a WIMP, short for weakly interacting massive particle. These hypothetical particles would have mass, comparable to heavy atomic nuclei, and would interact with ordinary matter only through gravity and the weak nuclear force, the same force responsible for certain types of radioactive decay. WIMPs would mostly pass through ordinary matter without leaving a trace, but very rarely. One might collide with an atomic nucleus, producing a detectable signal. WIMPs are appealing because they arise naturally in extensions to the standard model of particle physics designed to solve other problems, such as the hierarchy problem related to the mass of the Higgs boson. Another candidate is the axion, a much lighter particle proposed to solve a puzzle in the theory of the strong nuclear force. Axions would interact even more weakly than WIMPs, but under the right conditions they could be detected through their conversion into photons in the presence of a strong magnetic field. Sterile neutrinos, hypothetical cousins of the known neutrinos but even more aloof, are another possibility. Each of these candidates is not pulled from thin air, but is grounded in attempts to resolve multiple puzzles in fundamental physics, making them plausible entries on the list of suspects. Detecting dark matter directly is extraordinarily difficult. If dark matter particles rarely interact with ordinary matter, you need a very large detector and a very long time to catch even a single event. Direct detection experiments are built deep underground in mines or tunnels to shield them from cosmic rays and other background radiation that could mimic a dark matter signal. These detectors often use tanks filled with ultra-pure liquids like liquid xenon or argon, cooled to extremely low temperatures. The idea is simple. Wait for a dark matter particle to collide with a nucleus in the liquid, causing the nucleus to recoil and produce a tiny flash of light or a small amount of charge. Years can pass with only a handful of candidate events, and even those are often ambiguous, potentially explainable by residual background radiation or detector noise. It's painstaking work, like auditors listening for the faintest click in a vast, mostly silent archive. So far, despite decades of effort and increasingly sensitive detectors, no clear, unambiguous dark matter signal has been confirmed. Particle colliders offer a complementary approach. At facilities like the Large Hadron Collider, protons are smashed together at enormous energies, briefly recreating conditions similar to those in the early universe. If dark matter particles can be produced in these collisions, they would immediately escape the detector without leaving a trace, but their presence could be inferred from missing energy and momentum. The total energy and momentum before a collision must equal the total after, so if some goes missing, it suggests invisible particles carried it away. Researchers have searched extensively for such signatures, but so far no convincing evidence for dark matter production has emerged. Indirect detection efforts take yet another tack, watching the sky for excess gamma rays, positrons or other particles that could result from dark matter particles annihilating each other or decaying. Some tantalizing hints have appeared over the years: an excess of gamma rays from the centre of the Milky Way, an unexpected abundance of positrons in cosmic rays, but none have withstood scrutiny as definitive proof. Each potential signal either fades with better data or finds a more mundane explanation. Not everyone is convinced that dark matter exists as particles at all. Some researchers have proposed that instead of adding invisible matter, we should modify our understanding of gravity. On scales the size of galaxies and larger, perhaps the force law that Newton and Einstein described breaks down or changes form. One well-known proposal is modified Newtonian dynamics, or MOND, which suggests that at very low accelerations, far below what we experience on Earth, gravity becomes stronger than Newton's law predicts. MOND can fit the rotation curves of many galaxies quite well, without invoking dark matter. It's an elegant idea. Instead of adding a new, unseen component to the universe, you adjust the rules. But MOND and related theories struggle with other observations. They have difficulty explaining galaxy clusters, where the missing mass problem is even more severe than in individual galaxies. They don't naturally account for the patterns seen in the cosmic microwave background, or the success of large-scale structure simulations that include dark matter. The bullet cluster, with its clear spatial separation between ordinary matter and the gravitational mass, is particularly hard to explain without invoking an actual dark component that can pass through collisions unscathed. Modified gravity theories remain a minority view, not because they're wrong by default, but because dark matter, despite being unseen, provides a single, consistent explanation for a wide range of phenomena, while modified gravity often requires different tweaks for different contexts. Focusing back on individual galaxies, dark matter is thought to form vast halos that extend far beyond the visible disk of stars and gas. These halos are roughly spherical, or somewhat elongated, and they contain the bulk of a galaxy's mass. The exact distribution of dark matter within these halos is a subject of ongoing debate. Simulations of cold dark matter typically produce halos with a dense central cusp, where the density rises steeply, toward the centre. But observations of some galaxies, particularly small dwarf galaxies, suggest flatter central densities, a core rather than a cusp. This discrepancy has sparked extensive discussion. It might indicate a problem with the cold dark matter model, or it might reflect the complex interplay between dark matter and ordinary matter. Supernova, energetic outflows from massive stars, can blast gas out of a galaxy's center, and the changing gravitational potential can redistribute dark matter, smoothing out the central cusp. Star formation, gas inflows, and feedback processes all leave imprints on the dark matter distribution. These are the fine print details of the inventory, the nuances that don't undermine the overall picture but add texture and complexity. So where do things stand? Observations from many independent lines of evidence support the presence of a dominant invisible mass component. Rotation curves, galaxy clusters, gravitational lensing, the cosmic web, and the cosmic microwave background all point in the same direction. There is far more mass in the universe than we can see, and this extra mass behaves like cold, non-baryonic matter that interacts with ordinary matter almost exclusively through gravity. The numbers are precise. Cosmological models can pin down the amount of dark matter to within a few % of the total mass energy budget of the universe. The problem is firmly established. The missing entry on the balance sheet has a name, and its influence is mapped across cosmic scales. Yet the true identity of dark matter remains unknown. We know what it does, how much of it there is, how it clumps, how it shapes galaxies and clusters, but we don't know what it is. This is a rare situation in science, where the problem is well defined and the evidence overwhelming, yet the answer remains elusive. It's as if the universe handed us a detailed invoice with one line item labelled only as miscellaneous, but that miscellaneous item accounts for most of the total. Living with this uncertainty is part of modern cosmology. Researchers continue to build more sensitive detectors, refine simulations, search for new particles at colliders, and scan the sky for indirect signals. Each null result narrows the parameter space, ruling out certain masses or interaction strengths for hypothetical particles. Each new observation of galaxy dynamics or large-scale structure adds another data point to the map. The search is incremental, methodical, and patient. There's no guarantee that dark matter will reveal itself in the next decade or even the next century. It might be composed of particles so weakly interacting that direct detection remains forever out of reach, knowable only through its gravitational effects. Or it might be something entirely unexpected, a phenomenon or particle type not yet imagined by current theories. The universe has surprised us before. For now, the ledger remains open. Dark matter behaves consistently, predictably, across every scale we can measure. It holds galaxies together, binds clusters, guides the growth of structure, and leaves its fingerprint in the ancient light of the cosmic microwave background. It is as much a part of the universe's architecture as stars and gas, even if it never emits a single photon. The fact that we cannot yet see or touch it directly does not diminish the confidence with which we trace its influence. Gravity is a faithful record keeper, and dark matter's presence is recorded in the motions of galaxies, the shapes of light bent around clusters, and the subtle ripples in the radiation from the early universe. These are not ambiguous hints, but clear, repeated signals, all pointing to the same conclusion. As the rain continues outside and the screen stays black, the thought settles in quietly. Most of the universe's matter is invisible to our eyes. It doesn't shine in any wavelength, doesn't heat up, doesn't leave trails we can follow directly. But it is there, shaping the cosmos, a quiet partner to the bright matter we see. The story of dark matter is not one of mystery in the sense of lacking evidence. It's a mystery in the sense of knowing a thing exists, measuring its effects with precision, yet still waiting to meet it face to face. It's a balance sheet with a placeholder, a line waiting to be filled in. The universe's accounting is incomplete, but not chaotic. The numbers, though, they don't quite add up in the way we'd like, are consistent, robust, and reliable. Dark matter is real in every way that matters, except visibility. And so we wait, patiently, for the day when the inventory is complete, when the missing entry finally gets a full name and description, when the ledger closes and the universe's balance sheet is reconciled. Until then, the rain falls, the galaxies spin, and the invisible mass holds everything together, unseen but undeniable. As the rain continues outside and the screen stays black, the thought settles in quietly. Most of the universe's matter is invisible to our eyes. It doesn't shine in any wavelength, doesn't heat up, doesn't leave trails we can follow directly. But it is there, shaping the cosmos, a quiet partner to the bright matter we see. The story of dark matter is not one of mystery in the sense of lacking evidence. It's a mystery in the sense of knowing a thing exists, measuring its effects with precision, yet still waiting to meet it face to face. It's a balance sheet with a placeholder, a line waiting to be filled in. The universe's accounting is incomplete, but not chaotic. The numbers, though they don't quite add up in the way we'd like, are consistent, robust, and reliable. Dark matter is real in every way that matters, except visibility. The implications ripple through everything we understand about cosmic history. In the earliest moments after the Big Bang, when the universe was a hot, dense soup of particles and radiation, dark matter was already there, woven into the fabric from the beginning. As the universe expanded and cooled, ordinary matter remained tightly coupled to radiation, unable to clump together because photons kept jostling atoms apart. But dark matter, immune to electromagnetic forces, could begin collapsing under its own gravity immediately. It started forming the first structures while ordinary matter was still a smooth, glowing fog. By the time the universe cooled enough for atoms to form and light to travel freely, the moment captured in the cosmic microwave background, dark matter had already created gravitational wells, pockets of enhanced density scattered across space. These were the seeds. When ordinary matter finally decoupled from radiation and could respond to gravity, it fell into the wells dark matter had prepared, like water flowing into depressions in the ground. The first stars formed in these dark matter halos. The first galaxies assembled where dark matter had already gathered. Every luminous structure in the universe, from the smallest dwarf galaxy to the largest supercluster, owes its existence to the invisible scaffolding dark matter provided. This dependence goes deeper than just structure formation. The timing of when galaxies formed, how quickly stars ignited, the evolution of cosmic chemistry, all of it is tied to dark matter's presence and properties. If dark matter were slightly warmer, moving faster in the early universe, small halos would have been erased, and the first galaxies would have formed later and been more massive. If there were less dark matter overall, structures would grow more slowly, and the universe today would be a lonelier, emptier place. If there were more, galaxies would be denser, more tightly packed, and perhaps less stable. The specific amount and behaviour of dark matter that observations point to are what allow the universe to produce the rich tapestry of galaxies we see, including ones like our own Milky Way, a spiral galaxy of moderate size, old enough and stable enough to harbour planets and the chemistry of life. It's a sobering thought. We exist not despite dark matter, but because of it. The invisible component isn't some extraneous detail, it's foundational, a necessary condition for everything that followed. Our own galaxy swims through a dark matter halo that extends hundreds of thousands of light years beyond the visible disk, far past the orbit of the outermost stars. The Sun, in its journey around the galactic centre, moves through this halo, and at any given moment countless dark matter particles are passing through the Earth, through the walls of buildings, through our bodies. If dark matter is made of WIMPs or similar particles, trillions upon trillions flow through each square centimetre every second, utterly unnoticed. The Earth is transparent to them, offering no more resistance than air offers to neutrinos. This constant, invisible rain of dark matter particles is one reason direct detection is so challenging. The interaction probability for any single particle is vanishingly small. A WIMP might pass through light years of lead without interacting once. Detectors must be large, patient, and extraordinarily sensitive to catch even a single collision, and even then distinguishing that collision from background noise is difficult. It's like trying to hear a whisper in a stadium full of noise, except the whisper happens only once a year, and you're not entirely sure what it sounds like. Some experiments have reported tantalizing signals over the years, candidate events that looked like they might be dark matter interactions. In the late 1990s and early 2000s, the DEMA experiment in Italy observed an annual modulation in their detection rate, a signal that rose and fell with the seasons in a way that could be explained by Earth's motion through a dark matter halo. As Earth orbits the Sun, it sometimes moves in the same direction as the Sun's motion through the galaxy, encountering a higher flux of dark matter, and sometimes moves against that motion, encountering less. This would produce a predictable annual variation. The Dama result has persisted for decades, but other experiments using different detector materials and techniques have not seen consistent signals in the same parameter space. The lack of independent confirmation has left the field cautious. Dark matter detection is an arena where extraordinary claims require extraordinary evidence, and single experiments, no matter how carefully conducted, are not enough. Reproducibility and consistency across multiple detection methods are essential, and so far that consensus has not materialized. The community has also grappled with smaller-scale puzzles that might hint at gaps in the cold dark matter model, or at least in how we simulate it. One such puzzle involves the abundance of satellite galaxies around large galaxies like the Milky Way. Simulations predict that dark matter halos should host hundreds or even thousands of smaller subhalos, remnants of the hierarchical assembly process where small structures merge to form larger ones. Each subhalo could, in principle, host a small satellite galaxy, but observations show far fewer satellite galaxies than predicted subhalos. For a long time, this missing satellites problem was seen as a potential crisis for cold dark matter. However, more recent work suggests that the discrepancy may not be a failure of the dark matter model, but rather a reflection of how difficult it is for small halos to form stars. If a halo is too small, it may lack the gravitational pull to retain gas after the first supernovae explode, or it may be stripped of gas by the ultraviolet radiation from nearby galaxies. In other words, not every dark matter subhalo needs to light up as a visible galaxy. Many could remain dark, invisible clumps of matter with no stars. Recent discoveries of extremely faint dwarf galaxies around the Milky Way, detected only because they pass in front of background stars or are caught in deep imaging surveys, have begun to fill in the expected population. The missing satellites may not be missing after all, just very dim. Another puzzle concerns the structure of dark matter halos on the smallest scales. Some simulations predict that halos should contain dense, smaller clumps within them, a graininess at scales far below what we can currently observe directly. If true, these clumps might leave subtle signatures, perhaps through their gravitational lensing effects on distant quasars, or through perturbations in stellar streams, long rivers of stars torn from disrupted dwarf galaxies. Researchers are actively searching for these signs, hoping that the fine structure of dark matter halos can reveal properties of the dark matter particle itself, such as its mass or interaction cross-section. So far the data are consistent with smooth halos, but sensitivity is improving, and future surveys may detect the predicted substructure or rule it out, refining the picture further. There is also the question of whether dark matter interacts with itself, even weakly. Most models assume dark matter is collisionless, meaning particles pass through each other as easily as they pass through ordinary matter. But some researchers have explored the possibility of self-interacting dark matter, where dark matter particles do occasionally collide with each other, exchanging momentum and energy. This would affect the shapes and density profiles of dark matter halos, potentially solving some of the small-scale puzzles like the core cusp problem. If dark matter self-interacts, collisions in the dense centers of halos could transfer energy outward, puffing up the core and creating a flatter density profile. Observations of galaxy clusters, where collisions between clusters can separate the dark matter and gas in measurable ways, provide constraints on how much self-interaction is allowed. The bullet cluster itself places limits, but other clusters studied in detail have added to the picture. Current evidence suggests that if self-interaction exists, it's quite weak, but the door remains open, and the question is far from settled. The search for dark matter has also prompted physicists to consider increasingly exotic possibilities. What if dark matter isn't a single type of particle, but a whole hidden sector, a dark ecosystem with multiple particle species that interact with each other through forces we don't yet know? Just as ordinary matter includes protons, neutrons, electrons, and is governed by electromagnetism and the nuclear forces, dark matter might have its own complexity, its own periodic table, its own version of chemistry. If true, dark matter could form structures within structures, dark atoms, dark molecules, perhaps even dark planets or dark stars, objects made entirely of dark matter that exist alongside our own visible universe, but remain invisible and intangible to us. These ideas are speculative, but they're grounded in the recognition that we should not assume dark matter is simpler than the ordinary matter we know. Nature has surprised us with complexity before, and humility suggests we should be prepared for it again. Some theories even propose that dark matter might decay very slowly, over timescales comparable to the age of the universe. If dark matter particles are unstable, they would gradually transform into lighter particles, potentially releasing photons or other radiation in the process. Such signals would be faint, diffuse, and difficult to detect, but they could appear as subtle excesses in the spectrum of light from galaxies or clusters. A few anomalies, like an unexplained emission line at a specific energy seen in X-ray observations of galaxy clusters, have been tentatively attributed to dark matter decay, but alternative explanations involving known atomic processes are also possible. These hints are intriguing but not conclusive, and the search continues for a smoking gun, an unambiguous signal that can only be explained by dark matter doing something other than just pulling. The relationship between dark matter and dark energy, the other mysterious component of the universe's inventory, adds yet another layer. Dark energy is even stranger than dark matter, a form of energy that fills all of space and drives the accelerated expansion of the universe. Unlike dark matter, which clumps and forms structures, dark energy appears to be perfectly smooth, a uniform background that doesn't change over time or space. Together, dark matter and dark energy make up about 95% of the universe's total mass energy content. Ordinary matter, the stuff of stars, planets, and people, is a mere 5%, a rounding error in the cosmic ledger. The interplay between these components determines the fate of the universe. Dark matter slows the expansion through its gravitational pull, while dark energy accelerates it. The balance between them shapes the ultimate destiny of galaxies, clusters, and the cosmic web. If dark energy continues to dominate as current observations suggest, the universe will expand forever, growing colder, emptier, and darker as galaxies drift apart and stars burn out. Dark matter, despite its abundance, cannot prevent this. It can only slow the inevitable, shaping the structures that exist while they can. Reflecting on the journey so far, it's striking how the evidence for dark matter has accumulated through such diverse methods. No single observation proves its existence beyond all doubt, but the convergence of independent lines of evidence creates a powerful case. Rotation curves from hundreds of galaxies, X-ray observations of dozens of clusters, gravitational lensing maps from multiple systems, the large-scale distribution of galaxies across billions of light-years, the precise measurements of the cosmic microwave background from satellites separated by decades, all tell the same story, all point to the same invisible component. This is the hallmark of a robust scientific conclusion. When many different experiments, using different techniques, performed by different teams, over many years, all arrive at the same answer. That answer is very likely to be correct, even if the underlying explanation is not yet fully understood. Dark matter is in this category. Its existence is supported by a web of evidence so dense and interconnected that removing it would require explaining away not just one puzzling observation, but an entire suite of them, each individually strong and collectively overwhelming. What remains is the identity question, and that question is genuinely open. The dark matter particle, if it is a particle, has not yet appeared in our detectors. The theoretical candidates remain hypothetical, their properties constrained but not confirmed. This is not a failure of science, but a reflection of how difficult the problem is. Dark matter is elusive by its nature, interacting so weakly that detecting it requires pushing technology to its limits and beyond. The experiments are marvels of engineering, operating at the edge of what's possible, waiting in silence for a signal that may come tomorrow or may never come in our lifetimes. The work is slow, methodical, and requires patience, qualities not always celebrated in a world that values quick answers and immediate results. But science, at its best, is patient. It's willing to sit with uncertainty, to live with open questions, to continue searching even when the path forward is unclear. And so, the universe's ledger remains open, the balance sheet incomplete. Dark matter is recorded on every line, in every equation, its presence undeniable, and its influence pervasive. It holds galaxies together, guides the formation of structure, and makes the universe as we know it possible. Yet it remains a name without a face, a force without a form, a mass without light. The search continues in underground laboratories, at particle colliders, in observatories scanning the sky, in computer simulations exploring parameter space, in theoretical workshops where physicists imagine new possibilities. Each effort adds a small piece to the puzzle, narrows the range of options, rules out another corner of possibility. Progress is incremental but real. The mystery is patient, and so are we. The rain continues to fall outside, steady and unhurried, as the galaxies spin through space, held together by something we cannot see but know must be there, waiting quietly to be understood. The next story is about to begin. Please relax and enjoy.